Welcome to Quantum Mechanics. My name is Brant Carlson. Since this is the first lecture on quantum mechanics, we ought to have some sort of an introduction. And what I want to do to introduce quantum mechanics is to explain, first of all, why it's necessary, and second of all, to put it in historical context to, I'll show one of the most famous photographs in all of physics that really gives you a feel for the brain power that went into the construction of this theory. And hopefully we'll put it in some historical context as well, so you can understand where it fits in the broader philosophy of science. But the main goal of this lecture is about the need for quantum mechanics, which I really ought to just have called, Why Do We Need Quantum Mechanics? This subject has a reputation for being a little bit annoying, so why do we bother with it? Well, first off, for some historical context, imagine yourself back in 1900. Turn of the century, science has really advanced a lot. We have electricity, we have all this fabulous stuff that electricity can do, and even almost 100 years before that, physicists thought they had things figured out. There's a famous quote from Laplace, "Given for one instant an intelligence which could comprehend all the forces by which nature is animated, and the respective position of the beings which compose it, nothing would be uncertain, and the future, as the past, would be present to its eyes." Now, maybe you think intelligence which can comprehend all the forces of nature is a bit of a stretch. And maybe such a being which can know all the respective positions of everything in the universe is a bit of a stretch as well. But the feeling at the time was that if you could do that, you would know everything. If you had perfect knowledge of the present, you could predict the future. And of course you can infer what happened in the past. And everything is connected by one unbroken chain of causality. Now, in 1903, Albert Michelson, another famous quote from that time period, said, "The more important fundamental laws and facts of physical science have all been discovered. Our future discoveries must be looked for in the sixth place of decimals." Now, this sounds rather audacious. This is 1903, and he thought that the only thing that we had left to nail down was the part in a million level precision. Well, to be fair to him, he wasn't talking about never discovering new fundamental laws of physics. He was talking about really astonishing discoveries like the discovery of Uranus on the basis of orbital perturbations of Neptune. Never having seen the planet Uranus before, they figured out that it had to exist just by looking at things that they had seen. That's pretty impressive. And Michelson was really onto something. Precision measurements are really, really useful, especially today. But back in 1903, it wasn't quite so simple, and Michelson probably regretted that remark for the rest of his life. The attitude that I want you guys to take when you approach quantum mechanics, though, is not this sort of 1900s notion that everything is predicted. It comes from Shakespeare. Horatio says, "One, oh day and night, but this is wondrous strange." To which Hamlet replies, one of the most famous lines in all of Shakespeare, "And therefore as a stranger give it welcome. There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy." So that's the attitude I want you guys to take when you approach quantum mechanics. It is wondrous strange, and we should give it welcome. There are some things in quantum mechanics that are deeply non-intuitive, but if you approach them with an open mind, quantum mechanics is a fascinating subject. There's a lot of really fun stuff that goes on. Now, to move on to the necessity for quantum mechanics, there were some dark clouds on the horizon, even at the early 20th century. Michelson wasn't quite having a big enough picture in his mind when he said that everything was down to the sixth place of decimals. The dark clouds on the horizon, at least according to Kelvin here, were a couple of unexplainable experiments. One, the black body spectrum. Now, a black body you can just think of as a hot object. And a hot object, like, for example, the coils on an electrical stove, when they get hot, will glow. And the question is, what color do they glow? Do they glow red? Do they glow blue? What is the distribution of radiation that is emitted by a hot object? Another difficult to explain experiment is the photoelectric effect. If you have some light, and it strikes a material, electrons will be ejected from the surface. And, as we'll discuss in a minute, the properties of this experiment do not fit what we think we know about, or at least what physicists thought they knew about the physics of light and the physics of electrons at the turn of the 20th century. The final difficult experiment to explain is bright line spectra. For example, if I have a flame coming from, say, a Bunsen burner, and I put a chunk of something, perhaps sodium, in that flame, it will emit a very particular set of frequencies that looks absolutely nothing like a black body. We'll talk about all of these experiments in general, or in a little bit more detail in a minute or two, but just looking at these experiments now, these are all experiments that are very difficult to explain, knowing what we knew at the turn of the 20th century about classical physics. And they're also experiments that involve light and matter. So we're really getting down to the details of what stuff is really made of and how it interacts with the things around it. So these are some pretty fundamental notions, and that's where quantum mechanics really got its start. So let's pick apart these experiments in a little more detail. The blackbody spectrum, as I mentioned, you can think of as the light that's emitted just by a hot object. And while hot objects have some temperature associated with them, let's call that T. The plot here on the right is showing very qualitatively, I'll just call it the intensity of the light emitted as a function of the wavelength of that light. So short wavelengths, high energy, long wavelengths, low energy. Now if you look at T equals 3500 Kelvin curve here, it has a long tail to long wavelengths, and it cuts off pretty quickly as you go to short wavelengths, so it doesn't emit very much high energy light. Whereas if you have a much hotter object, 5500 Kelvin, it emits a lot more high energy light. The red curve here is much higher than the black curve. Now if you try to explain this, knowing what early 20th century physicists knew about radiation and about electrons and about atoms and how they could possibly emit light, you get a prediction. And it works wonderfully well up until about here, at which point it blows up to infinity. Infinities are bad in physics. This is the Rayleigh-Jeans law, and it works wonderfully well for long wavelengths, but does not work at all for short wavelengths. That's called the ultraviolet catastrophe, if you've heard that term. On the other end of things, if you look at what happens down here, well, it's not so much a prediction but an observation, but there's a nice formula that fits here. So on one side we have a prediction that works well on one end but doesn't work on the other. And on the other hand we have a sort of empirical formula called Wien's law that works really well at the short wavelengths, but, well, also blows up to infinity at the long wavelengths. Both of these blowing up things are a problem. The question is, how do you get something that explains both of them? This is the essence of the blackbody spectrum and how it was difficult to interpret in the context of classical physics. The next experiment I mentioned is the photoelectric effect. This is sort of the opposite problem. It's not how a material emits light, it's how light interacts with the material. So you have light coming in, and the experiment is usually done like this. You have your chunk of material, typically a metal, and when light hits it, electrons are ejected from the surface, hence the electric part of the photoelectric effect. And you do all this in a vacuum, and the electrons are then allowed to go across a gap to some other material, another chunk of metal, where they strike this metal. And the experiment is usually done like this. You connect it up to a battery. So you have your material on one side and your material on the other, and you have light hitting one of these materials and ejecting electrons. And you tune the voltage on this battery such that your electrons, when they're ejected, never quite make it. So the electric field produced by this voltage is opposing the motion of the electrons. When that voltage is just high enough to stop the motion of the electrons, keep them from completely making it all the way across, we'll call that the stopping voltage. Now, it turns out that what classical E&M predicts, as I mentioned, doesn't match what actually happens in reality. But let's think about what does classical E&M predict here. Well, classical electricity and magnetism says that electromagnetic waves here have electric fields and magnetic fields associated with them, and these are propagating waves. If I increase the intensity of the electromagnetic wave, that means the magnitude of the electric field involved in the electromagnetic wave is going to increase. And if I'm an electron sitting in that electric field, the energy I acquire is going to increase. That means V stop is going to increase, because I'll have to have more voltage to stop a higher energy electron, as would be produced by a higher intensity beam of light. The other parameter of this incoming light is its frequency. So we can think about varying the frequency. If I increase the frequency, I have more intense light. Now, that doesn't say anything about the string, if I increase the frequency, I don't necessarily have more intense light. The electric field magnitude is going to be the same, which means the energy and the stopping voltage will also be the same. Now, it turns out what actually happens in reality does not match this at all. In reality, when the intensity increases, the energy, which I should really write as V stop, the stopping voltage necessary, doesn't change. And when I increase the frequency, the voltage necessary to stop those electrons increases. So this is sort of exactly the opposite. What's going on here? That's the puzzle in explaining the photoelectric effect. Just to briefly check your understanding, consider these plots of stopping voltage as a function of the parameters of the incident light, and check off which you think shows the classical prediction for the photoelectric effect. The third experiment that I mentioned is bright line spectra. And as I mentioned, this is what happens if you take a flame or some other means of heating a material, like the bar of sodium I mentioned earlier. This will emit light, and in this case, the spectrum of light from red to blue of sodium looks like this. Actually, I'm sorry, that's not sodium, that's mercury. These are four different elements: hydrogen, mercury, neon, and xenon. And instead of getting a broad, continuous distribution, like you would from a black body, under these circumstances where you're talking about gases, you get these very bright regions. It's the spectrum, instead of looking like a smooth curve like this, looks like spikes. Those bright lines are extraordinarily difficult to explain with classical physics, and this is really the straw that broke the camel's back, broke classical physics' back, that really kicked off quantum mechanics. How do you explain this? This is that famous photograph that I mentioned. This is really the group of people who first built quantum mechanics. Now, I mentioned three key experiments. The black body spectrum. This guy figured that out. This is Planck. The photoelectric effect. This guy, who I hope needs no introduction, this is Einstein, figured that out. This is the paper that won Einstein the Nobel Prize. And as far as the bright line spectra of atoms, it took a much longer time to figure out how all of that fit together. And it took a much larger group of people. But they all happen to be present in this photograph. There's this guy, and this guy, and these two guys, and this guy. This photograph is famous because these guys worked out quantum mechanics. But that's not the only, these aren't the only famous people in this photograph. You know this lady as well. This is Marie Curie. This is Lorentz, which if you studied special relativity, you know Einstein used the Lorentz transformations. Pretty much everyone in this photograph is a name that you know. I went through and looked up who these people were, these were all of the names that I recognized, which doesn't mean that the people whose names I didn't recognize weren't also excellent scientists. For example, C.T.R. Wilson here, one of my personal favorites, inventor of the cloud chamber. This is the brain trust that gave birth to quantum mechanics, and it was quite a brain trust. You had some of the most brilliant minds of the century working on some of the most difficult problems of the century. And what's astonishing is they didn't really like what they found. They discovered explanations that made astonishingly accurate predictions, but throughout the history you keep seeing them disagreeing, like, no, that can't possibly be right. Not necessarily because the predictions were wrong or they thought there was a mistake somewhere, but because they just disliked the nature of what they were doing. They were upending their view of reality. Einstein, in particular, really disliked quantum mechanics to the day that he died, just because it was so counterintuitive. And so with that introduction to a counterintuitive subject, I'd like to remind you again of that Shakespeare quote, "There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy." Try to keep an open mind, and hopefully we'll have some fun at this. Knowing that quantum mechanics has something to do with explaining the interactions of light and matter, for instance, in the context of the photoelectric effect, or blackbody radiation, or bright line spectra of atoms and molecules, one might be led to the question of when is quantum mechanics actually relevant? The domain of quantum mechanics is unfortunately not a particularly simple question. When does it apply? Well, on the one hand, you have classical physics, and on the other hand, you have quantum physics. And the boundary between them is not really all that clear. On the classical side, you have things that are certain, whereas on the quantum side, you have things that are uncertain. What that means in the context of physics is that on the classical side, things are predictable. They may be chaotic and difficult to predict, but in principle they can be predicted. While on the quantum side, things are predictable too, but with a caveat. In the classical side, you determine everything. Basically, every property of the system can be known with perfect precision, whereas in quantum mechanics what you predict are probabilities. And learning to work with probabilities is going to be the first step to getting comfortable with quantum mechanics. The boundary between these two realms, when the uncertain and probabilistic effects of quantum mechanics start to become relevant, is really a dividing line between things that are large and things that are small. And that's not a particularly precise way of stating things. Doing things more mathematically, quantum mechanics applies, for instance, when angular momentum L is on the scale of Planck's constant, or the reduced Planck's constant, h bar. Now, h bar is the fundamental scale of quantum mechanics, and it appears not only in the context of angular momentum. Planck's constant has units of angular momentum, so if your angular momentum is of order Planck's constant or smaller, you're in the domain of quantum mechanics. We'll learn more about uncertainty principles later as well, but uncertainties in this context have to do with products of uncertainties. For instance, the uncertainty in the momentum of a particle times the uncertainty in the position of the particle. This, if it's comparable to Planck's constant, is also going to give you the realm of quantum mechanics. Energy and time also have an uncertainty relation, again, approximately equal to Planck's constant. Most fundamentally, the classical action, when you get into more advanced studies of classical mechanics, you'll learn about a quantity called the action, which has to do with the path a system takes as it evolves in space and time. If the action of the system is of order Planck's constant, then you're in the quantum mechanical domain. Now, Planck's constant is a really small number. It's 1.05 times 10 to the negative 34 kilogram meters squared per second. times 10 to the negative 34 is a small number. So if we have really small numbers, then we're in the domain of quantum mechanics. In practice, these guys are the most useful, whereas this is the most fundamental. But we're more interested in useful things than we are in fundamental things, after all. For example, the electron in the hydrogen atom. Now, you know from looking at the bright line spectra that this should be in the domain of quantum mechanics. But how can we tell? Well, to use one of the uncertainty principles as a calculation, consider the energy. The energy of an electron in a hydrogen atom is, let's say about 10 electron volts. If we say that's p squared over 2m, using the classical kinetic energy relation between momentum and kinetic energy, that tells us that the momentum, p, is going to be about 1.7 times 10 to the minus 24th kilogram meters, kilogram, where'd it go? Where's my eraser? Kilogram meters per second. Now, this suggests that the momentum of the electron is, non-zero. But if a hydrogen atom itself is not moving, we know the average momentum of the electron is 0. So if the momentum of the electron is going to be 0, with still some momentum being given to the electron, this is more the uncertainty in the electron momentum than the electron momentum itself. The next quantity, if we're looking at the uncertainty relation between momentum and position, is we need to know the size of, or the uncertainty in the position of the electron, which has to do with the size of the atom. Now, the size of the atom, that's about 0.1 nanometers, which, if you don't remember the conversion from nanometers, is 10 to the minus 10th meters. So let's treat this as delta x, our uncertainty in position, because we don't really know where the electron is within the atom, so this is a reasonable guess at the uncertainty. Now, if we calculate these two things together, delta p, delta x, you get something, and I should say this is approximate because this is very approximate, 1.7 times 10 to the negative 34th, and if you plug through the units, it's kilogram meter squared per second. This is about equal to h bar. So this tells us that quantum mechanics is definitely important here. We have to do some quantum in order to understand this system. As an example of another small object that might have quantum mechanics relevant to it, this is one that we would actually have to do a calculation. I don't know intuitively whether a speck of dust in a light breeze is in the realm of quantum mechanics or classical physics. Now, I went online and looked up some numbers. For a speck of dust, let's say the mass is about 10 to the minus 6th kilograms, a microgram. It has a velocity in this light breeze of, let's say, 1 meter per second. And make myself some more space here. The size of this speck of dust is going to be about 10 to the minus 5 meters. So these are the basic parameters of this speck of dust in a light breeze. Now we can do some calculations with this. For instance, momentum. Well, the momentum is just the mass times the velocity. So P is going to be about equal to 10 to the minus 9 kilogram meters per second. Better make that 10 to the minus 6th kilogram meters per second. My notes are backwards here. The uncertainty in the momentum then is, we could say it's 10 to the minus 6 kilogram meters per second, but let's say it's a little smaller than 10 to the minus 6 kilogram meters per second. Let's say 10 to the minus 8 kilogram meters per second. Now the position uncertainty that's going to be a function of the size of the object. If we know the size of the object, the position uncertainty is probably not all that much larger than the size of the object. In fact, it's probably smaller. We can measure where a speck of dust is to better than the diameter of the speck of dust, just by putting it in a microscope, for example. So, let's say the position uncertainty here is going to be about 10 to the minus 6th meters. Now, if we run that calculation, delta p delta x comes out to be 10 to the 6th times 10 to the minus 8th, which is 10 to the minus 14th kilogram meters squared per second. This is a good factor of 10 to the 20th larger than h bar. So this is solidly in the realm of classical physics. So even something really small, like a speck of dust in a light breeze, is still going to be classical. So the size of something here, the smallness of it, is something that you might have to calculate until you start getting a feel for it. Just some basic examples to put things in context a little further. Quantum mechanics is most likely going to be important if you're dealing with single particles, atoms, molecules, single electrons, single photons, small systems of electrons and photons. It's also going to be very, very relevant if you're talking about semiconductors. The quantum mechanical properties of semiconductors are what makes them into such spectacularly useful electronic devices. Lasers are another situation where quantum mechanics is crucially important. Without quantum mechanics, there would be no lasers. And finally, if you're talking about very low temperature physics, temperatures less than about 100 Kelvin, well, those are going to be quantum mechanical as well. So single particles, weird materials, crystals, lasers, low temperatures, they're kind of an exotic set of phenomena, but we're adding more all the time. Quantum mechanics allows us to do things that we wouldn't be able to do in the classical world. Consequently, it's in our best interest to try and push quantum mechanics as far as we can take it. So, to check your understanding, this is a short question about the uncertainty in, the relevant parameters of interaction between two helium atoms, and what temperature scale these interactions become important, or become quantum mechanical at. In order to understand quantum mechanics, there's some basic vocabulary that I need to go over. So let's talk about the key concepts in quantum mechanics. Thankfully, there are only a few. There's really only 3, and the first is the wave function. The wave function is, and always has been, written as psi, the Greek letter. My handwriting gets a little lazy sometimes, and it'll end up just looking like this, but technically, it's supposed to look something like that. Details are important, provided you recognize the symbol. Psi is a function of position, potentially in 3 dimensions, x, y, and z, and time. And the key facts here is that psi is a complex function, which means that while x, y, z, and t here are real numbers, psi, evaluated at a particular point in space, will potentially be a complex number with both a real and imaginary part. What is subtle about the wave function, and we'll talk about this in great detail later, is that while it represents the state of the system, it doesn't tell you with any certainty what the observable properties of the system are. It really only gives you probabilities. So for instance, if I have a coordinate system, something like this, where say this is position in the x direction, psi, with both real and imaginary parts, might look something like this. This could be the real part of psi, and this could be, say, the complex or the imaginary part of psi. what is physically meaningful is the squared magnitude of psi, which might look something like this in this particular case. And that is related to the probability of finding the particle at a particular point in space. As I said, we'll talk about this later, but the key facts that you need to know about the wave function is that it's complex and it describes the state of the system, but not with certainty. The next key concept in quantum mechanics is that of an operator. Now, operators are what connect psi to observable quantities. That is one thing operators can do. Just a bit of notation, usually we use hats for operators. For instance, x hat or p hat are operators that you'll encounter shortly. Operators act on psi. So if you want to apply, for instance, the x hat operator to psi, you would write x hat psi. As if this were something that as it appears on the left of psi, the assumption is that x acts on psi. If I write psi x hat, doesn't necessarily mean that x hat acts on psi. You assume operators act on whatever lies to the right. Likewise, of course, p hat psi. Now, we'll talk about this in more detail later, but x hat, the operator, can be thought of as just multiplying by x. So if I have psi as a function of x, x hat psi is just going to be x times psi of x. So if psi was a polynomial, you could multiply x by that polynomial. The p operator, p hat, is another example, is a little bit more complicated. This is just an example now, and technically this is the momentum operator, but we'll talk more about that later. It's equal to minus h bar times the derivative with respect to x. So this is again something that needs a function, needs the wave function to actually give you anything meaningful. Now the important thing to note about the operators is that they don't give you the observable quantities either. But in quantum mechanics, you can't really say the momentum of the wave function. For instance, p hat psi is not, and I'll put this in quotes because you won't hear this phrase very often, the momentum of psi. It's the momentum operator acting on psi, and that's not the same thing as the momentum of psi. The final key concept in quantum mechanics is the Schrödinger equation. And this is really the big equation. So I'll write it big. I, h bar, partial derivative of psi with respect to time is equal to h hat, that's an operator, acting on psi. Now h hat here is the Hamiltonian, which you can think of as the energy operator. So the property of the physical system that H is associated with is the energy of the system. And the energy of the system can be thought of as a kinetic energy. So we can write a kinetic energy operator plus a potential energy operator together acting on psi. And it turns out the kinetic energy operator can be written down. This is going to end up looking like minus h bar squared over 2m partial derivative of psi with respect to, second partial derivative of psi with respect to position, plus, and then the potential energy operator is going to look like the potential energy as a function of position, just multiplied by psi. So this is the Schrödinger equation. Typically, you'll be working with it in this form. So I h bar times the partial derivative with respect to time is related to the partial derivative with respect to space, and then multiplied by some function. The basic quantum mechanics that we're going to learn in this course mostly revolves around solving this function and interpreting the results. So to put these in a bit of a roadmap, we have operators. we have the Schrödinger equation. And we have the wave function. Now operators act on the wave function, and operators are used in the Schrödinger equation. Now the wave function that actually describes the state of the system is going to be the solution to the Schrödinger equation. Now I mentioned operators acting on the wave function. What they give you when they act on the wave function is some property of the system, some observable perhaps. And the other key fact that I mentioned so far is that the wave function doesn't describe the system perfectly, it only gives you probabilities. So that's our overall concept map. To put this in the context of the course outline, the probabilities are really the key feature of quantum mechanics, and we're going to start this course with the discussion of probabilities. We'll talk about the wave function after that and how the wave function is related to those probabilities, and we'll end up talking about operators and how those operators and the wave functions together give you probabilities associated with observable quantities. That will lead us into a discussion of the Schrödinger equation, which will be most of the course, really. The bulk of the material before the first exam will be concerned with various examples. Solution to the Schrödinger equation under various circumstances. This is really the main meat of quantum mechanics in the beginning. After that, we'll do some formalism. And what that means is we'll learn about some advanced mathematical tools that make keeping track of all the details of how all of this fits together a lot more straightforward. And then we'll finish up the course by doing some applications. So those are our key concepts and a general roadmap through the course. Hopefully now you have the basic vocabulary necessary to understand phrases like the momentum operator acts on the wave function, or the solution to the Schrödinger equation describes the state of the system, and that sort of thing. Don't worry too much if these concepts haven't quite clicked. In order to really understand quantum mechanics, you have to get experience with them. These are not things that you really have any intuition for based on anything you've seen in physics so far. So bear with me, and this will all make sense in the end, I promise. Complex numbers, or numbers involving, conceptually you can think about it as the square root of -1, I, are essential to understanding quantum mechanics, since some of the most fundamental concepts in quantum mechanics, for instance the wave function, are expressed in terms of complex numbers. Complex analysis is also one of the most beautiful subjects in all of mathematics, but unfortunately, in this course I don't have the time to go into the details. Lucky you, perhaps. Here's what I think you absolutely need to know to understand quantum mechanics, from the perspective of complex analysis. First of all, there's basic definition. I squared is equal to -1, which you can think of also as I equals the square root of -1. In general, a complex number, z, then, can be written as the sum of a purely real part, x, and a purely imaginary part, I times y. Note, in this expression, z is complex, x and y are real, where I times y is purely imaginary. The terms purely real or purely imaginary, in the context of this expression like this, x plus iy, something is purely real if y is 0, something is purely imaginary if x is 0. As far as some notation for extracting the real and imaginary parts, typically mathematicians will use this funny calligraphic font to indicate the real part of x plus iy or the imaginary part of x plus iy, and that just pulls out x and y. Note that both of these are real numbers. When you pull out the imaginary part, you get x and y. You don't get iy, for instance. Another one of the most beautiful results in mathematics is e to the I pi plus 1 equals 0. This formula kind of astonished me when I first encountered it, but it is a logical extension of this more general formula that e raised to a purely imaginary power, iy, is equal to the cosine of y plus I times the sine of y. This can be shown in a variety of ways, in particular involving the Taylor series. If you know the Taylor series for the exponential, the Taylor series for cosine of y, and the Taylor series for sine of y, you can show quite readily that the Taylor series for complex exponential is the Taylor series of cosine plus the Taylor series of sine. And while that might not necessarily constitute a rigorous proof, it's really quite fun if you get the chance to go through it. At any rate, the trigonometric functions here, cosine and sine, should be suggestive, and there is a geometric interpretation of complex numbers that we'll come back to in a minute. But for now, know that while we have rectangular forms like this, x plus iy, where x and y, the nomenclature there is chosen on purpose, you can also express this in terms of r e to the I theta, where you have now a radius and an angle. The angle here, by the way, is going to be the arctangent of y over x. And we'll see why that is in a moment when we talk about the geometric interpretation. But given these rectangular and polar forms of complex numbers, what do the basic operations look like? How do we manipulate these things? Well, addition and subtraction in rectangular form is straightforward. If we have two complex numbers, a plus ib plus, and we want to add to that a second complex number, c plus id, we just add the real parts, a and c, and we add the imaginary parts, b and d. This is just like adding in any other sort of algebraic expression. Multiplication is a little bit more complicated. You have to distribute, and you distribute in the usual sort of draw a smiley face kind of way. A times c and b times d are going to end up together in the real part. And the reason for that is, well, a times c, a and c both being real numbers, a times c will be real. Whereas ib times id, both being purely complex numbers, you'll end up with b times d times I squared, and I squared is minus 1. So you just end up with minus bd, which is what we see here. Otherwise, the complex part is perhaps a little more easy to understand. You have I times b times c, and you have a times I times d, both of which end up with plus signs in the complex part. Division, in this case, is like rationalizing the denominator, except instead of involving radicals, you have complex numbers. If I have some number a plus ib divided by c plus id, I can simplify this by both multiplying and dividing by c minus id. Note the sign change in the denominator here. C plus id is then prompting me to multiply by c minus id over c minus id. Now, when you do the distribution there, for instance, let's just do it in the denominator, c plus id times c minus id, my top eyebrows here of the smiley face, c squared times id, or c squared plus, now, id times minus id, which is, well, I'll just write it out, I times minus id, which is going to be d squared times I times minus I. So I squared times minus 1, and I squared is minus 1. So I have minus 1 times minus 1, which is just 1, so I can ignore that. I've just got d squared. So what I end up with in the denominator is just c squared plus d squared. What I end up with in the numerator, well, that's the same sort of multiplication thing that we just discussed. So the simplified form of this has no complex part in the denominator, which helps keep things a little simple and a little easier to interpret. Now, in polar form, addition and subtraction, well, they're complicated. Under most circumstances, if you have two complex numbers given in polar form, it's easiest just to convert to rectangular form and add them together there. Multiplication and division, though, in polar form have very nice expressions. q e to the I theta times r e to the I phi. Well, these are just all real numbers multiplying together, and then I can use the rules regarding multiplication of exponentials, meaning if I have two things like e to the I theta and e to the I phi, I can just add the exponents together. It's like taking x squared times x to the fourth and getting x to the sixth. But qr e to the I theta plus phi. So that was easy. We didn't have to do any distribution at all. The key fact here is that you add the angles together. In the case of division, it's also quite easy. You simply divide the radii, q over r, and instead of adding, you subtract the angles. So polar complex numbers expressed in polar form are much easier to manipulate in multiplication and division, while complex numbers represented in rectangular form are much easier to manipulate for addition and subtraction. Taking the magnitude of a complex number, usually we'll write that as something like z, if z is a complex number, just using the same notation for absolute value of a real number, usually is expressed in terms of the complex conjugate. Now, the complex conjugate, notationally speaking, is usually written by whatever complex number you have, here in this case x plus iy, with a star after it. And what that signifies is you flip the sign on the complex part, on the imaginary part. X plus iy becomes x minus iy. The squared magnitude then, which is always going to be a real and positive number, this absolute value squared notation, is what you get from multiplying a number by its complex conjugate. And that's what we saw earlier with c plus id. Say I take the complex conjugate of c plus id and multiply it by c plus id. Well, the complex conjugate of c plus id is c minus id times c plus id. And doing the distribution, like we did when we calculated the denominator, when we were simplifying the division of complex numbers in rectangular form, just gave us c squared plus d squared. This should be suggestive if you have something like x plus iy, that's really messy, x plus iy, and I want to know the squared absolute magnitude. Thinking about this as a position in Cartesian space should make this formula, c squared plus d squared, in this case, just make a little more sense. You can also, of course, write that in terms of real and imaginary parts. But let's do an example. If w is 3 plus 4i, and z is minus 1 plus 2i, first of all, let's find w plus z. Well, w plus z is 3 plus 4i plus minus 1 plus 2i. That's straightforward. If you can keep track of your terms, 3 minus 1 is going to be our real part, so that's 2. And 4i plus 2i, which is plus 6i, is going to be our complex part. Sorry, our imaginary part. Now, w times z, 3 plus 4i times minus 1 plus 2i. For this, we have to distribute, like usual. So from our top eyebrow terms here, we've got 3 times minus 1, which is minus 3, and 4i times 2i, both positive. So I have 4 times 2, which is 8, and I times I, which is minus 1, minus 8. Then, for my imaginary part, I guess the mouth and the chin, if you want to think about it that way, I have 4i times minus 1, minus 4 with the I out front, will just be minus 4 inside the parentheses here. And 3 times 2i is going to give me 6i plus 6 inside. And the end result you get here is 8, or minus 8 minus 3 is minus 11, and minus 4 plus 6 is going to be 2. So I get minus 11 plus 2i for my multiplication here. I guess if I'm going to circle that answer, I should circle this answer as well. Now, slightly more complicatedly, w over z. W is 3 plus 4i, and z is minus 1 plus 2i. And you know when you want to simplify an expression like this, you multiply by the complex conjugate of the denominator, divided by the complex conjugate of the denominator. So minus 1 minus 2i divided by minus 1 minus 2i. And if we continue the same sort of distribution, I'll do the numerator first. Same sort of multiplication we just did here, only the signs will be flipped a little bit. We'll end up with minus 3 plus 8 instead of minus 3 minus 8. And for the imaginary part, we'll end up with minus 4 minus 6 instead of minus 4 plus 6. And you can work out the details of that distribution on your own if you want. the denominator is not terribly complicated. Since we know we're taking the absolute magnitude of a complex number by multiplying a complex number by its complex conjugate, we can just write this out as the square of the real part, 1, plus the square of the imaginary part, minus 2, which squared is 4. So if I continue this final step, this is going to be 5. This is going to be minus 10i, and our denominator here is just going to be 5. So in the end, what I'll end up with is going to be 1 minus 2i. So it actually ended up being pretty simple in this case. Now for the absolute magnitude of w, 3 plus 4i, you can think of this as w times w star square root. You can think of this as the square root of the real part of w plus the imaginary part of w. Sorry, square root of the squared of the real part plus the square of the imaginary part, which is perhaps a little easier to work with in this case, so you don't have to distribute out complex numbers in that way. Real part is 3, imaginary part is 4, so we end up with the square root of 3 squared plus 4 squared, which is 5. Now this was all in rectangular form. Let me move this stuff out of the way a little bit. And let's do it again, at least a subset of it, in polar form. In polar form, w, 3 plus 4i, we know the magnitude of w, that's 5. So that's going to be our radius, 5. And our e to the I theta, where theta is, like I said, the arctan of, in this case, not 4/4, 4/3. So that's the polar form of the complex number w. Now if you plug this into your calculator to figure out what the arctan of 4/3 is, you'll get 5 e to the I 0.927. If you do the same thing for z, you'll end up with the square root of 5 times e to the I 2.03. And for instance, if I wanted to calculate w over z, I would just have, well, the radius associated with w divided by the radius associated with z times e to the I difference of the angles. And if you take 0.927 and subtract 2.03, you end up with minus 1.1, give or take. And if you actually go through and check, you will find out that these two numbers are equal to each other. So that's an example of manipulating complex numbers, just in a very simple way. In order to check your understanding, here's another example for you to work through on your own. Now, the geometric interpretation I've been alluding to is, whoops, I wanted to do this in black, is in 2 dimensions, hopefully not too surprising. I kept mentioning the rectangular form and the polar form. Well, instead of the rectangular form being rectangular coordinates x and y, we're going to talk about the rectangular form being the real and imaginary parts of a complex number. So if we have some complex number here, let's call it z, we can think of that as being composed of some real part of z and some imaginary part of z. That's the rectangular form of the complex number z. If you want to think about the polar form of z, well, this would be the radius associated with that, and this would be the angle associated with that z. So if I want to say z equals r e to the I theta, this is the distance I'm talking about for r, and this is the angle I'm talking about for theta. Now in the geometric interpretation, addition and multiplication do pretty much what you would expect. Or sorry, addition and subtraction do pretty much what you would expect. If I have a complex number here, say w, and another complex number here, say z, I can treat these as vectors and just add them tip to tail. So one vector is going in this direction, one vector is going in this direction. The vector sum will just put me out here, w plus z. Same thing for subtraction, but with the sign flip on whatever is being subtracted. This is for addition. If you want to multiply, the multiplication rule, or the geometric interpretation, also has a nice way of treating multiplication. If I have some complex number, again, say w, some complex number, say z, the best way of thinking about this is in polar form, where I have, say, a vector with one angle here. I'll call that theta. Let's call it theta 1. And another vector here with an angle theta 2. Theta 2. Sorry for the small font. I hope this is legible. When you multiply these two complex numbers together, you know you have to multiply the radii. Maybe that will put you out, somewhere at large radii. And you have to add the angles together. In this case, theta 1 is going upwards, and theta 2 is going downwards. So if I go up theta 1 and then add, going back down, theta 2, I'll end up somewhere out here, say, where the distance I've gone is the magnitude of w times the magnitude of z, and the angle I'm at now here is theta 1 plus theta 2, where theta 2 is negative. So addition and multiplication have nice geometric interpretations as well. Especially useful in visualizing multiplication is this notion of rotating your complex vector. I have effectively rotated down theta 2 from the vector to w in order to get in the direction from the origin towards the product w times z. So hopefully that's reasonably clear. The geometric interpretation can help a lot when it comes to visualizing what actually happens with with complex numbers, especially in the context of quantum mechanics when you're dealing with complex functions. At any rate, here's another example where I'm going to draw out what these things actually look like. So I have two complex numbers, 3 plus 4i and minus 1 plus 2i. Let me draw myself a nice big coordinate system here. And I'll put some tick marks on it. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. More or less. Now, first of all, draw w, z, and w plus z. So w is 3 plus 4i. So my real part is 3. 1, 2, 3. My imaginary part is 4. So I go 1, 2, 3, 4. So I am up here. That's where w would be. Now, z is minus 1 plus 2i. So minus 1 plus 2i is z. So z is going to be there. Now, if I treat these both as vectors, I have a vector to w, and I have a vector to z, and I add the vectors the way I would normally add vectors, tip to tail, I'll end up here at w plus z. Now, it's easy to see this in Cartesian coordinates as well. If I'm adding w and z, I'm going to end up with 3 minus 1 for the real part, or 2, up here, and 4i plus 2i, or 6i, 1, 2, 3, 4, 5, 6, for the imaginary part. Now, w times z. If you actually go through and work out what w times z is, you'll find out it has quite a large magnitude. It has a magnitude a little bit larger than 11 point something. But what I really want to emphasize here is the geometric interpretation. And in that case, you need to know the angles involved. So I have an angle here, theta 1, and I have an angle here, theta 2. And it turns out if I add these two angles together, say going up theta 1 and then going over theta 2, I end up somewhere along this in this direction. And you actually have to go out quite a ways. You have to go all the way to minus 11 plus, what was it, plus 2i, I think? Yes, minus 11 plus 2i is the answer for w times z. And if you just look at the angles here, adding theta 1 and theta 2 is going to point you in that direction. So you know it's going to have a negative real part and a positive imaginary part, but perhaps a small positive imaginary part, just by eyeballing the angles, which is not really all that bad. W divided by z is the same sort of situation, except now instead of adding theta 2 to theta 1, you're going to subtract theta 2 from theta 1. So I'm going to go up theta 1 and then back down theta 2. And where you end up is actually here at 1 minus 2i. But just by eyeballing the angles, you can get a good feel for what part of the complex plane you're in, where typically, this is the real axis of the complex plane, and this is the imaginary axis of the complex plane. In Cartesian coordinates, you have 2 degrees of freedom, x and y. In the complex plane, you have 2 degrees of freedom, the real part and the imaginary part. The last thing that I need you to understand about complex numbers from the perspective of quantum mechanics is complex functions. Now, the theory of complex functions is a lot of fun, but beyond the scope of a quantum course. To give you an idea for how complex these things can be, f of z is a complex function. Now, z as a complex number, f of z, if f is a complex function, is going to be complex, meaning I can think about this as some real part function plus some imaginary part function times I. So my one function of a complex variable can actually be, complex function of a complex variable can actually be thought of as 2 separate functions. Separate real functions, mind you, so this is a slightly simpler way of thinking about things. But you have a real part and an imaginary part. Now in the case of true complex functions like f of z, z itself has 2 degrees of freedom. So you can think of this as f real of the real part of z and then the imaginary part of z as 2 separate arguments to that function. And then plus I times f imaginary times the same thing, the real part of z and the imaginary part of z. So we have, instead of one function of one variable, we have 2 functions of 2 variables. And that makes things very difficult to visualize. Thankfully, in quantum mechanics, what we're typically working with is the wave function psi. And psi, for a lot of the problems that we're going to be thinking about, is only a function of one coordinate. So you can think about this as psi of x, where x is a coordinate. So psi, well, psi of x is complex. X is real. So while we have to think about the real and imaginary parts of psi, we don't have to worry about the real and imaginary parts of x. We can just think about this as x, a single argument. In terms of how to visualize complex functions like this, you can think about plotting both the real and imaginary parts of this function as a function of whatever you're working with. In this case, let's say we have to deal with psi of x. So this is going to be the x-axis, and we'll have something, maybe it looks like this, for the real part of psi of x, and something maybe it looks like this for the imaginary part of psi. So think about plotting 2 separate functions, the real and imaginary parts, of this effectively single function as a function of, in the case of this, x, it's rather simple to visualize. Now I have some more advanced visualizations that use color to represent the angle in the polar interpretation of psi as a complex function, and they get a little bit psychedelic and you start hallucinating after a while if you look at them too much. But for now, try to keep in mind that complex numbers have real and imaginary parts and can be interpreted both as x and y in the complex plane, the real part and the imaginary part in a two-dimensional Cartesian plane, or a radius and an angle in a polar representation of the same two-dimensional complex plane. That's about it for quantum mechanics. Like I said, that's about it for complex analysis as needed for quantum mechanics. Like I said, complex analysis is a very deep, very beautiful topic, and I encourage you to study it further in the future. But for now, I think that's all you need to know. Since complex numbers are so important to quantum mechanics, let's do a few more examples. In this case, I'm going to demonstrate how to manipulate complex numbers in a more general way, not so much just doing examples with numbers. First example, simplify this expression. You have two complex numbers multiplied in the numerator, and then a division. First of all, the first thing to simplify is this multiplication. You have x plus iy times ic. This is pretty easy. It's a simple sort of distribution. We're going to have x times ic. That's going to be a complex part. So I'm going to write that down a little bit to the right, ixc. And then we're going to have iy times ic, which is going to be minus yc. That's going to be real. We also have a real part in the numerator from the d here. So I'm going to write this as d minus yc plus ic. That's the result of multiplying this out. That's then going to be divided by f plus ig. Now, in order to simplify this, we have a complex number in the denominator. You know you need to multiply by the complex conjugate and divide by the complex conjugate. So f minus ig divided by f minus ig. Now, expanding this out is a little bit messier, but fundamentally you've seen this sort of thing before. You have real part, and imaginary part in the numerator, and then you're going to have imaginary part, and real part, imaginary part. And what you're going to end up with from this first term, you get f times d minus yc. From the second term, you have minus ig times ixc, which is going to give you xcg. We have a minus I times an I, which is going to give us a plus. Incidentally, if you're having trouble figuring out something like minus I times I, think about it in the geometric interpretation. This is I in the complex plane. This is minus I in the complex plane. So I have one angle going up, one angle going down. If I'm multiplying them together, I'm adding the angles together. So I essentially go up and back down, and I just end up with 1 equals I times minus I. Otherwise, you can keep track of I squareds equals minus 1s and just count up your minus signs. This, then, is the real part. Suppose I should write that in green, lest my fonts get too confusing. Excuse me. So that's the real part. The imaginary part, then, is what you get from these terms here. I'm going to write an I out front, and now we have xc times f, so xcf with an I from here. And then we have d minus yc times ig, which I'll just write as g d minus yc. In the denominator, we're now multiplying a number by its complex conjugate. You know what to do there. F squared plus g squared. This is just the magnitude of this complex number. Sorry, squared magnitude. Now, this doesn't necessarily look more simple than what we started with, but this is effectively fully simplified. You could further distribute this and distribute this, but it's not really going to help you very much. The thing to notice about this is that the denominator is purely real. We've also separated out the real part of the numerator and the imaginary part of the numerator. Yeesh. My handwriting is getting messier as I go. imaginary part of the numerator. So we can look at this numerator now and say, this is the complex number, real part, imaginary part, and then it's just divided by this real number, which effectively is just a scaling. It's a relatively simple thing to do, to divide by a real number. As a second example, consider solving this equation for x. Now this is the same expression that we had in the last problem, only now we're solving it for it equal to 0. So from the last page, I'm going to borrow that first simplification step we did, distributing this through. We had d minus yc for the real part, plus ixc for the imaginary part, and that was divided by f plus ig. If we're setting this equal to 0, the nice part about dealing with complex expressions like this is that 0, treated as a complex number, is 0 plus 0i. It has a real part and an imaginary part as well. It's just kind of trivial. And in order for this complex number to be equal to 0, the real part must be 0 and the imaginary part must be 0. So we can think of this as d minus yc plus ixc. This has to equal 0 and this has to equal 0 separately. So we effectively have two equations here, not just one, which is nice. We have d minus yc equals 0 and xc equals 0, which, unless c equals 0, just means x equals 0. That's the only way that this equation can hold, is if x equals 0. The key fact here is to keep in mind that in order for two complex numbers to be equal, both the real parts and the imaginary parts have to be equal. As a slightly more involved example, consider finding the cubed roots of 1. Now, 1 cubed is 1. That's a good place to start. We'll see that fall out of the algebra pretty quickly. What we're trying to do is solve the equation z cubed equals 1, which you can think of as x plus I y, where x and y are real numbers, cubed, equals 1. Now, if we expand out this cubic, you get x cubed plus 3x squared times iy plus 3x times iy squared plus iy cubed. And this is going to have to equal 1. Excuse me. Equal 1. Now, looking at these expressions, here we have an iy, here we have an iy squared. This is going to give me an I squared, which is going to be a minus sign. And here I have an iy cubed. This is going to give me an I cubed, which is going to be minus I. So I have two complex parts and two real parts. So I'm going to rewrite that. X cubed, and then now a minus sign from the I squared, 3xy squared, plus, pulling an I out front, the imaginary part then is going to come from this 3x squared y and this y cubed. So I've got a 3x squared y here, and then a minus y cubed, minus coming from the I squared. And this is also going to have to equal 1. Now, in order for this complex number to equal this complex number, both the real parts and the imaginary parts have to be equal. So let's write those two separate equations. X cubed minus 3xy squared equals the real part of, this is the real part of the left-hand side, has to equal the real part of the right-hand side, 1. And the imaginary part of the left-hand side, 3x squared y minus y cubed, has to equal the imaginary part of the right-hand side, 0. So those are our two equations. This one in particular is pretty easy to work with. We can simplify this. This is, we can factor a y out. This is y times 3x squared minus y squared equals 0. One possible solution then is going to come from this. You have a product like this is equal to 0. Either this is equal to 0 or this is equal to 0. And saying y equals to 0 is rather straightforward. So let's say y equals 0. And let's substitute that into this expression. That's going to give us x cubed equals 1. which might look a lot like the equation we started with, z cubed equals 1, but it's subtly different because z is a general complex number, whereas our assumption in starting the problem this way is that x is a purely real number. So a purely real number, which when cubed gives you 1, that means x equals 1. So x equals 1, y equals 0, that's one of our solutions. Z equals 1 plus 0I, or just z equals 1. Now, we could have told me that right off the bat, z cubed equals 1. Well, one possible solution is that z equals 1, since 1 cubed is 1. The other thing we can do here is we can say 3x squared minus y squared is equal to 0. This means that, I'll just cheat a little bit and simplify this, 3x squared equals y squared. Now I can substitute this y squared, into this expression as well. And what you end up with is x cubed minus 3x, and then y squared was equal to 3x squared. So 3x squared is going to go in there. That has to equal 1. Now let's move up here. What does that leave us with? That says x cubed minus 9x cubed equals 1. So minus 8x cubed equals 1. This means x, again being a purely real number, is equal to minus 1/2. Minus 1/2 times minus 1/2 times minus 1/2 times 8 times minus 1 is equal to 1. You can check that pretty easily. Now, where does that leave us? Where did I go? That leaves us substituting this back into this expression, which tells us that 3x squared equals y squared. X equals minus 1/2, so 3 minus 1/2 squared equals y squared, which tells you that y equals plus or minus the square root of 3/4 if you finish your solution. So now we have two solutions for y here coming from one value for x, and that gives us our other two solutions to this cubic. We have a cubic equation. We would expect there to be three solutions, especially when we're working with complex numbers like this. And this is our other solution. Z equals minus 1/2 plus or minus the square root of 3/4 I. So those are our three solutions. Now, finding the cubed roots of 1 to be these complex numbers is not necessarily particularly instructive. However, there's a nice geometric interpretation. The cubed roots of unity like this, the nth roots of unity, doesn't have to be a cubed root. All lie on a circle of radius 1 in the complex plane. And if you check the complex magnitude of this number and the complex magnitude of this number, you will find that it is indeed unity. To check your understanding of this, a slightly simpler problem is to find the square roots of I. Put another way, you've got z, some generic complex number here, equals to x squared plus x plus iy. Quantity squared, if that's going to equal y, we'll expand this out, solve for x and y in the two equations that will result from setting real and imaginary parts equal to each other. And same as with the cubed roots of 1, the square roots of I will also fall on a circle of radius 1 in the complex plane. So those are a few examples of how complex numbers can actually be manipulated. In particular, finding the roots of unity, there are better formulas for that than the approach that we took here, but I feel this was hopefully instructive.
If probability is at the heart of quantum mechanics, what does that actually mean? Well, the fundamental source of probability in quantum mechanics is the wave function, psi. Psi tells you everything that you can in principle know about the state of the system, but it doesn't tell you everything with perfect precision. How that actually gives rise to probability distributions in observable quantities like position or energy or momentum is something that we'll talk more about later, but from the most basic perspective, psi can be thought of as related to a probability distribution. But let's take a step back and talk about probabilistic measurements in general first. If I have some space, let's say it's position space. Say this is the floor of a lab, and I have a ball that is somewhere on the floor. I can measure the position of that ball. Maybe I measure the ball to be there on the floor. If I prepare the experiment in exactly the same way, attempting to put the ball in the same position on the floor and measure the position of the ball again, I won't always get the same answer because of perhaps some imprecision in my measurements or some imprecision in how I'm reproducing the system. So I might make a second measurement there, or a third measurement there. If I repeat this experiment many times, I'll get a variety of measurements at a variety of locations. And maybe they cluster in certain regions, or maybe they're very unlikely in other regions. But this distribution of measurements, we can describe that mathematically with a probability distribution. A probability distribution, for instance, I could plot P of x here, and P of x tells you roughly how many, or how likely you are to make a measurement. So I would expect P of x as a function to be larger here, where there's a lot of measurements, and 0 here where there's no measurements, and relatively small here where there's few measurements. So P of x might look something like this. So the height of P of x here tells us how likely we are to make a measurement in a given location. This concept of a probability distribution is intimately related to the wave function. So the most simple way that you can think of probability in quantum mechanics is to think of the wave function psi of x. Now psi of x, you know, is a complex function, and a complex number can never really be observable. What would it mean, for example, to measure a position of, say, 2 plus 3i meters? This isn't something that's going to occur in the physical universe. But the fundamental interpretation of quantum mechanics that this book in particular, that most physicists think of, is the interpretation that psi, in the context of a probability distribution, the absolute magnitude of psi squared is related to the probability of finding the particle described by psi. So if the squared magnitude of psi is large at a particular location, that means it is likely that the particle will be found at that location. Now the squared magnitude here means that we have to take the squared magnitude of psi. We can't just take psi itself. So for instance, in the context of the plot that I just made on the last page, if this is x and our y-axis here is psi has real and imaginary parts. So the real part of psi might look something like this, and the imaginary part might look something like this. And the squared magnitude would look something like, well, what you can imagine the squared magnitude of that function looking like. And you can think of the squared magnitude of psi as the probability distribution. Let me move this up a little bit, give myself some more space. The squared magnitude of psi then can be thought of as a probability distribution in the likelihood of finding the particle at a particular location, like I said. Now, what does that mean mathematically? Mathematically, suppose you had two positions, A and B, and you wanted to know what the probability of finding the particle between A and B was. Given a probability distribution, you can find that by integrating the probability distribution. So the probability that the particle is between A and B is given by the integral from A to B of the squared absolute magnitude of psi dx. You can think of this as a definition. You can think of this as an interpretation. but fundamentally this is what the physical meaning of the wave function is. It is related to the probability distribution of position associated with this particular state of the system. Now, what does that actually mean? And that's a bit of a complicated question. It's very difficult to answer. Suppose I have a wave function, which I'm just going to write as the square, plot as the squared magnitude of psi now. Suppose it looks something like this. Now that means I'm perhaps likely to measure the position of the particle somewhere in the middle here. So suppose, wrong color. So suppose I do that. Suppose I measure the position of the particle here. So I've made a measurement now. Messy handwriting. I've made a measurement, and I've observed the particle to be here. What does that mean in the context of the wave function? Now, everything that I can possibly know about the particle has to be encapsulated in the wave function, so after the measurement, when I know the particle is here, you can think of the wave function as looking something like this. It's not going to be infinitely narrow because there might be some uncertainty. The width of this is related to the precision of the measurement. But the wave function before the measurement was broad, like this, and the wave function after the measurement is narrow. What actually happened here? What about the measurement caused this to happen? This is one of the deep issues in quantum mechanics that is quite difficult to interpret. So what do we make of this? Well, one thing that you could think, just intuitively, is that, well, this probability distribution wasn't really all the information that was there. Really, the particle was there. Let's say this is point C. One interpretation is that the particle really was at C all along. That means that this distribution reflects ignorance on our part as physicists, not fundamental uncertainty in the physical system. This turns out to not be true, and you can show mathematically and in experiments that this is not the case. The main interpretation that physicists use is to say that this wave function psi here, also shown here, collapses. Now that's a strange term. Collapses. But it's hard to think of it any other way. Suppose you were concerned with the wave function's value here. Before the measurement, it's non-zero, whereas after the measurement, it's 0. So this decrease in the wave function out here is, it's reasonable to call that a collapse. What that wave function collapse means is subject to some debate, and there are other interpretations. One interpretation that I'll mention very briefly, but we won't really discuss very much, is the many worlds interpretation, and that's that when you make a measurement like this, the universe splits. So it's not that the wave function all of a sudden decreases here, it's that for us, in our tiny little chunk of the universe, the wave function is now this, and there's another universe somewhere else where the wave function is this, because the particle is observed to be here. Don't worry too much about that, but the interpretation issues in quantum mechanics are really fascinating once you start to get into them. You can think about this as the universe splitting into, splits. The universe, you can think about this as the universe splitting into many little sub-universes where the probability of where the particle is observed at a variety of locations. One location per universe, really. This question of how measurements take place is really fundamental, but hopefully this explains a little bit of where probability comes from in quantum mechanics. The wave function itself can be thought of as a probability distribution for position measurements. And unfortunately, the measurement process is not something that's particularly easy to understand, but that's the fundamental origin of probability in quantum mechanics. To check your understanding, here is a simple question about probability distributions and how to interpret them. Since probability is so essential to quantum mechanics, it's good to go back and review to make sure we're all on the same page as far as probability. The fundamental concepts of probability, aside from probability itself, are probability distributions and what their properties are. So let's review probability. There are two main kinds of probability, discrete and continuous. Discrete probability is what you get if you have only a specific set of outcomes. Sort of, well, hence the word discrete. You have a discrete set of outcomes. And these outcomes can be anything. They can be the outcomes of a measurement, they can be responses in a survey, they can be any sort of data set. For example, if this is your data set, 0, 0, 1, 1, 1, 2, 2, 3, 4, 5, 2 zeros, 3 ones, 2 twos, and 1 each of 3, 4, and 5. For instance, suppose you go out and you ask 10 members of the general public how many sexual partners they've had. You might get a data set something like this. The way to think of this in the context of a probability distribution, well, I like to plot things. So let's make a plot of this probability distribution. We have our outcomes, 0, 1, 2, 3, 4, and 5. Extend my axis a little there. We have 2 people who answered 0. So if we make a y-axis here, 1, 2, I can put a bar here at 0 that goes up to 2. There were 3 people that answered 1, so I should make a bar that goes up to 3 above the 1. 5, 3 above the 1. Likewise for 2, there were 2 answers for 2, and there were 1 each for 3, 4, and 5. 1 there, 1 there, and 1 there. Now, our probability distribution looks like this when you plot it. What are we actually plotting here? We're plotting the number of people who responded for each particular answer here. We can make a table then of the probabilities. Either we have, on the left we have the value, and on the right we have the probability. Now what is the probability under these circumstances? We have a discrete set of outcomes, 6 different numbers, 0 through 5, and the probability of, say, 3 is just the number of 3's that appear in this data set divided by the total number of entries in the data set. So, for instance, if I want to know the probability of the value 1, well, there were let's start with 0. If I want to know the probability of the value 0, there were 2 respondents, so that would be 2 divided by 10. 2 people out of 10. So if I chose one of these at random, not looking at the numbers, the likelihood that I would choose 0 is, well, 2 out of 10. 2 times in 10, I would choose a 0 probability, on average. And you can do the same thing for 1, 3 out of 10, 2, 2 out of 10 again, 3, 4, and 5, all 1 out of 10. And some things you should notice about this, let me move it up slightly, to move everything up. The numbers here, if I add these up, 2 plus 3 plus 2 plus 1 plus 1 plus 1, it adds up to 10 out of 10. So the total probability of drawing any number is 1, and that is sort of a certainty. If you draw a number, you will draw a number. So if you only have a discrete set of outcomes, for instance, the integers like this, you're dealing with the discrete probability distribution, and the sum of the probabilities in a discrete probability distribution have to sum to 1. And it's a straight sum if I add up these numbers. The other class of probability distribution is a continuous probability distribution. Continuous probability distributions are what you work with when you have a range of values. A range of values, not a list of values.
So for instance, suppose you got this set of numbers. This might be what you would get if you talked to 10 people who'd just gotten off the phone with Comcast tech support and asked them, for instance, how long did Comcast put you on hold, say in hours. We can look at this probability distribution graphically as well, only it's slightly more complicated. Suppose the x-axis now here is my time in hours, and I have 1 and 2 to give a scale on my axis. Now if I plot this data set, I've got one at like 0.7 or 0.07, one at 0.11, one at 0.23, 0.55, 0.79, 1.09, 1.7, probably about there, 1.8, 1.88, and 2.16, something like that. So these discrete answers, each answer here is only a specific number on this axis. So if I want to make a meaningful plot, I can either pretend that my probability distribution is discrete, or I can attempt to guess at what the probability distribution looks like. Since I know what the answer is here, let's call this rho of x is typically the name given to a continuous probability distribution, and it would look something like this in this case. So we have what's called a probability density function, or just a probability density, rho of x. Now the reason we have a probability density like this, rho of x, is because x is a continuous variable now. It can be anything, in this case, say from 0 to infinity. What does that mean? If I evaluate rho of x at, say, x equals 1, you might think, well, okay, that's the probability of 1. But, well, one of the three fundamental facts of continuous probability distributions is that the probability that x is exactly equal to 1 is going to be 0. The example given in the text is, suppose you walked up to a random person on the street and asked, is your age 18 years, 3 months, 12 days, 18 minutes, 16 seconds, 52 microseconds, etc. If you precisely specify the exact answer you want, the probability that you'll get that exact answer is going to be 0. The only reason, or the only way that makes sense for a continuous variable or continuous probability is for the probability to be specified between limits. Suppose I had A and B, and I want to know the probability that the number that you're drawing from this distribution, or the random probability of amount of time that you would like to have to spend on hold with Comcast between, say, 45 minutes and an hour and 45 or an hour and a half. You could calculate that knowing this function, and the way you calculate it is by integrating. Put mathematically, the probability that, say, x is between A and B is the integral from A to B of rho of x dx. You can think of this more or less as the definition of the probability density function. If you have a way of calculating probabilities for x's and ranges, that is the probability density function. Probability density functions also have to sum to 1, but instead of having a sum, in the case of a discrete probability distribution, we have an integral. So the other property here is that the integral from minus infinity to infinity, the entire possible range of values, rho of x dx, has to equal, not 0, has to equal 1. The answer, the question that this equation here answers is, what is the probability of drawing a number in between negative infinity and positive infinity? And that had better be unity. This is the equivalent of the sum of the probabilities in a discrete probability distribution being equal to 1. Now, in this case, the probability distribution, to give you a feel for what these things look like, rho of x in this case is 0 if x is less than 0,
and is equal to e to the minus x if x is greater than or equal to 0. So this is an example of a probability distribution function, or probability density. That's actually the distribution I used when I drew these numbers. So that's continuous probability. If you have a continuous range of outcomes, you have to deal with probability distributions and your probability density functions, and you have to do some integrals if you want to calculate properties. Now, what are those properties? Well, the most basic properties that you can think of is probably the most likely outcome. Now, in the case of a discrete probability distribution, this is just the most probable. What that means is that you've got the highest probability. And in this case, that means it's just the outcome that occurs the most times. In this case, 1. So our most probable outcome here is 1. In the case of a continuous distribution, it's slightly more complicated. If I plot the distribution function from before, the exponential, turn off the ruler. If I plot the probability distribution from before, looks something like this. The most probable is actually going to be 0. Now, you might think, what are the odds that Comcast puts me on hold for 0 minutes? Well, 0. That's our rule that the probability that x is exactly equal to 0 is 0. It only makes sense to make a statement like the probability that, say, x is greater than 0 and x is less than, say, 5 minutes. And that you can calculate with your integral, like on the last page. But in the case of the most probable value, the peak of the distribution is indeed 0 here, in spite of the fact that 0 will effectively never happen. Any exact value will effectively never happen, but 0 is the most likely. The next property is the median. Median is not something that appears very often in physics, but it appears a lot in statistics, so we need to mention it. The median is essentially the middle of the data set. So you've got half are smaller and half are larger than the median. So here I have 10 numbers. The median is going to be something that falls in between 1 and 2. Half the data set, 0, 0, 1, 1, 1, is smaller, and 2, 2, 3, 4, 5 are all larger. Typically, what statisticians do when they define the median here, when there's no exact number that is the median, is to just put it halfway between the numbers. So in this case, the median would be 1.5. In the context of a continuous probability distribution, the median is the number such that your probability adds up, or the probability adds up to a half. So if I integrate from minus infinity, the lower possible limit that you could possibly have, up to the median, rho of x dx, I would get 0.5. So in the case of this probability distribution function, e to the minus x, I can write that out. This is integral from 0 to, I'll just call the median m now. E to the minus x is rho of x dx. Now I constructed this integral from 0 to m instead of from minus infinity to m because this probability distribution is 0 for x less than 0, just to make sure that it's clear why I used 0 here. And that's not actually a 6, that's a 0. So if you do this integral, you know the integral of e to the minus x is minus e to the minus x. Hopefully. If you don't, you need to review some calculus. There will be a lot of integrals like this in quantum mechanics, evaluated between 0 and m, and that has to be equal to 0.5. Plugging in the limits here, you get, well, I'll just simplify it and skip a step here. You get 1 minus e to the minus m equals 0.5, which, if you solve it for m, gives you that m equals the log of 2. Now, if I get sloppy and say log here, I really mean natural log. Log, if I ever need a log base 10, I'll write log base 10.
Most of the time we'll be using natural logs in quantum mechanics. So that's the median. The next property, and this is one that will be very common, is the mean. The symbol that we use for the mean is mu, and in the case of a discrete probability distribution, mu is the sum over all of your outcomes of the outcome, x sub I, times the probability that, say, x is x sub I. Sometimes this is just written as the probability of x sub I, which makes sense in the context of a discrete probability distribution. So what this looks like in the case of the discrete probability that I gave you earlier is, well, there's 0, that's x sub I, times the probability that x equals 0, which was 2/10, plus 1, that's x sub I, times the probability that x equals 1, which was 3/10, plus 2, x sub I, times probability that x is equal to 2, which is 2/10. And you can keep going, plus 3 times 1/10 plus 4 times 1/10 plus 5 times 1/10, for 3, 4, and 5, all of which have probability 1/10. And if you run through the numbers, you'll find this is equal to 1.9. If you remember from an earlier class that the mean is the sum of the values divided by the total number of values that you added up, that's the same formula as this if you, say, factor the 1/10 out. All of these numbers have a 1/10, and if we factor that out, we'll get 0 plus 0 plus 1 plus 1 plus 1 plus 2 plus 2 plus 3 plus 4 plus 5, which is what you would get if you added all this up. And you get the same answer. So there's no black magic there. The reason I'm writing this way is this format here, where you have something times the probability of that something is something that shows up repeatedly. In the context of a continuous distribution, for example, the mean mu, now instead of a sum, we have to have an integral. And instead of a sum over all possible values, we'll have an integral over all possible values, minus infinity to infinity, of x times the probability density, rho of x, dx. Now if I plug in this example, we'd be integrating again from 0 to infinity, so that I don't have to worry about, if I integrate from minus infinity to 0, the probability density is going to be 0 for that entire range. So I can ignore that and just start my integral at 0, and then I would have x e to the minus x dx. Now whenever you see an integral like this, hopefully you think integration by parts. The way I like to do integration by parts is to try and figure out, probably just by trial and error, which pieces of this equation are going to become which of the parts that I'm going to use. In this case, let's say u equals x and dv equals e to the minus x dx. Now, you differentiate this, du equals dx, and you integrate this, v equals minus e to the minus x. Now in integration by parts, the forms that don't have any differentials in them, that's your leading term. So we would have this integral is equal to x e to the minus x with a minus sign, evaluated at the limits 0 and infinity. Then we have a minus sign, and the integral part of the integration by parts result, which are these bottom pieces. So the integral now of e to the minus x with a minus sign, so I'm going to change this minus out front into a plus, and then this part just dx, from 0 to infinity. Now, what do we do with the endpoints on this? Well, at infinity, e to the minus infinity, that's 1 over e to the infinity, that's 0. And that's a really emphatic 0, if you think about it in the context of a limit. The limit as x e to the minus x the limit of x e to the minus x as x goes to infinity is 0. So our upper limit here is 0, and then we subtract what we get if we plug in 0 for this. Now e to the minus 0 is just 1, and x, well, x is 0, so we have effectively 0 minus a negative 0, 0 plus 0, whatever. It's still 0. This term vanishes. And what we're left with here is the integral of e to the minus x dx from 0 to infinity. And hopefully you know how to do that. That just, in the end, is going to equal 1. So that's our mean. Mean is also called expectation value, especially in quantum mechanics. It's not necessarily the value that you expect to get. It is it's this mathematical expression that tells you the value that is sort of in the middle of your distribution of possible values. The reason expectation value is perhaps a better term than mean, especially in quantum mechanics, is that we can apply it more easily to functions, for instance, f of x. The notation we use for the expectation value, or the mean value, of some function is to put that in brackets. So this is read as the expected value, or the expectation value of x, or perhaps just the expectation of f. Excuse me, f, not x. And this, in the context of a discrete probability distribution, looks a lot like the formula for the mean, except instead of x sub I in the sum, we have f of x sub I times the probability that x is x sub I. So suppose the function I wanted to work with was f of x equals x squared. What's the probability of x squared? Well, just applying this formula, you would have 0 squared from f of x with x sub I being 0 times the probability of 0, which was 2/10, plus 1 squared times 3/10. Now this is 1 squared times the probability of 1, plus 2 squared times 2/10, plus 3 squared times 1/10, plus 4 squared times 1/10, plus 5 squared times 1/10. And if you plug all the numbers in here, this is a fairly simple thing to do. Hopefully you can get the right answer on your calculator. It comes out to 6.1. To keep with my format from earlier, I should do this in color. The expected value of f is 6.1. You might also see this written as the expected value of x squared, just saving or compacting the notation a little bit and ignoring the definition of f. Same thing. For the case of a continuous distribution, the pattern by now is hopefully reasonably clear. The expected value of f in the continuous distribution case is equal to the integral from minus infinity to infinity of f of x times rho of x dx. And the integral in this case, for the example function here, is going to be equal to integral from 0 to infinity again, because rho of x is 0 for x less than 0. F of x is x squared, rho of x, e to the minus x dx. Now again, you see an integral like this, I want you to think integration by parts. Alternatively, I want you to think, oh, I should go plug this integral into Wolfram Alpha, or I should go look this up in a table of integrals, or whatever tool, if you have like a TI-89 or a TI-92, they can do integrals like this. Whatever technique you want to use to solve integrals is okay with me. But in this case, integration by parts will work, and it's not terribly difficult. So again, u is going to be x squared, and dv is, here's my eraser, dv equal to e to the minus x dx. Sorry, I'm running out of space there. Let me do this slightly more legibly. dv equals e to the minus x dx. Now, differentiate this. Du equals 2x dx, and v equals minus e to the minus x. In our integration by parts then, the term out front, without the integral, is going to be x squared times minus e to the minus x, evaluated at the limits, 0 and infinity. And for the same reasons this term vanished in the last case, it's going to vanish here as well. If I evaluate this at infinity, this is going to be 0. If I evaluate this at 0, this is going to be 0. So this term will vanish. The second part of our integration by parts is minus the integral from 0 to infinity of, just for the sake of neatness, 0 to infinity. The parts here with the differentials in them. 2x dx e to the minus x with a minus sign, so I'm going to change this minus sign to a plus sign. This integral, I'm going to pull the 2 out front. 2 times the integral from 0 to infinity of x e to the minus x dx. And this integral, you hopefully remember because we just did it. This integral was equal to 1. That was what we did on the last page. So this overall is going to equal 2. So the expected value of x squared under this continuous probability distribution is 2. To check your understanding, here's a sample problem. The probability density function in this case, I'll plot it just to make things a little more intuitive. If this is 0 and this is 1 and 2, the probability density is 0 if x is less than 0. It's also 0 if x is greater than 1. And for x between 0 and 1, it's equal to 2x. So our probability density function looks something like this, and your task is to find the mean of x under this probability distribution, and the expected value of f of x equals the square root of x. So 2 tasks here to accomplish with this sample probability distribution. Variance and standard deviation are properties of a probability distribution that are related to the uncertainty. Since uncertainty is such an important concept in quantum mechanics, we need to know how to quantify how uncertainty results from probability distributions. So let's talk about the variance and the standard deviation. These questions are related to the shape of a probability distribution. So if I have a set of coordinates, let's say this is the x-axis, and I'm going to be plotting then the probability density function as a function of x. Probability distributions come in lots of shapes and sizes. You can have probability distributions that look like this, probability distributions that look like this. You can even have probability distributions that look like this, or probability distributions that look like this. And these are all different. The narrow peak here versus the broad distribution here. The distribution with multiple peaks, or multiple modes. In this case it has 2 modes, so we call this distribution bimodal, or multimodal. And then this distribution, which is asymmetric, has a long tail in the positive direction and a short tail in the negative direction. We would say this distribution is skewed. So distributions have lots of different shapes, and if what we're interested in is the uncertainty, you can think about that roughly as the width of the distribution. For instance, if I'm drawing random numbers from the orange distribution, the narrow one here, they'll come over roughly this range. Whereas if I'm drawing from the blue distribution, they'll come over roughly this range. So if this were, say, the probability density for position, say this is the squared magnitude of the wave function for a particle, I know where the particle represented by the orange distribution is much more accurately than the particle represented by the blue distribution. So this concept of width of a distribution and the uncertainty in the position, for instance, are closely related. The broadness is related to the uncertainty. This is fundamental to quantum mechanics, so how do we quantify it? In statistics, the broadness of a distribution is called the variance. Variance is a way of measuring the broadness of a distribution, for example. So, suppose this is my distribution. The mean of my distribution is going to fall roughly in the middle here. Let's say that's the expected value of x, if this is the x-axis. Now, if I draw a random number from this distribution, I won't always get the expected value. Suppose I get a value here. If I'm interested in the typical deviation of this value from the mean, that will tell me something about how broad this distribution is.
So let's define this displacement here to be delta x. Delta x is going to be equal to x minus the expected value of x. And first of all, you might think, well, if I'm looking for the typical values of delta x, let's just try the expected value of delta x. Well, what is that? Unfortunately, the expected value of x doesn't really work for this purpose because delta x is positive if you're on this side of the mean and negative if you're on this side of the mean. So the expected value of delta x is 0. Sometimes it's positive, sometimes it's negative, and they end up canceling out. Now, if you're interested in only positive numbers, the next guess you might come up with is let's use not delta x, but let's use the absolute value of delta x. What is that? Well, absolute values are difficult to work with since you have to keep track of whether a number is positive or negative and keep flipping signs if it's negative. So this turns out to just be kind of painful. What statisticians and physicists do in the end then is instead of taking the absolute value of a number to make it positive, we square it. So you calculate the expected value of the squared deviation, sort of the mean squared deviation. This has a name in statistics. It's written as sigma squared, and it's called the variance. To do an example, let's do a discrete example. Suppose I have two probability distributions, all with equally likely outcomes. Say the outcomes of one distribution are 1, 2, and 3, while the outcomes for the second distribution are 0, 2, and 4. Put it graphically, these numbers are more closely spaced than these numbers. So I would expect the broadness of this distribution to be larger than the broadness of this distribution. You can calculate this out by calculating the mean squared deviation. So first of all, we need to know the mean. The expected value of x is 2 in this case, and also in this case. Knowing the expected value of x, you can calculate the deviations. So let's say delta x here is going to be minus 1, 0, and 1 are the possible deviations from the mean for this probability distribution, whereas in this case it's minus 2, 0, and 2. Then we can calculate the delta x squareds that are possible, and you get 1, 0, and 1 for this distribution, and 4, 0, and 4 for this distribution. Now when you calculate the mean of these squared deviations, in this case, the expected value of the squared deviation is 2/3, whereas in this case, the expected value of the squared deviation is 8/3. So indeed, we did get a larger number for the variance in this distribution. So you can think of that as the definition. This is not the easiest way of calculating the variance, though. It's actually much easier to calculate the variance as an expected value of a squared quantity and minus the square of the expected value of the quantity itself. So the mean of the square minus the square of the mean, if that helps you to remember it. You can see how this results fairly easily by plugging through some basic algebra. So given our definition, the expected value of delta x squared, we're calculating an expected value. So suppose we have a continuous distribution now. The continuous distribution expected value has an integral in it, so we're going to have the integral of delta x squared times rho of x dx. Now delta x squared, we know what delta x is. Delta x is x minus the expected value of x, so we can plug that in here, and we're going to get the integral of x minus expected value of x squared times rho of x dx. I can expand this out, and I'll get integral of x squared minus 2x expected value of x plus expected value of x quantity squared rho of x dx. And now I'm going to split this integral up into three separate pieces. First piece, integral of x squared rho of x dx. Second piece, integral of 2x expected value of x rho of x dx. And the third piece, integral of expected value of x squared rho of x dx. Now this integral you recognize right away. This is the expected value of x squared. This integral, I can pull this out front since this is a constant. This is just a number. This is the expected value. So this integral is going to become 2, I can pull the 2 out of course as well, 2 times the expected value of x, and then what's left is the integral of x, rho of x, dx, which is just the expected value of x. This integral, again this is a constant, so I can pull it out front, and when I do that, I end up with just the integral of rho of x dx. And we know the integral of rho of x dx over the entire domain. I should specify that this is the integral from minus infinity to infinity now. All of these are integrals from minus infinity to infinity. The integral of minus infinity to infinity of rho of x dx is 1. So this, after I pull the expected value of x quantity squared out, is just going to be the expected value of x quantity squared. So this is expected value of x squared. This is, well, I can simplify this as well. This is the expected value of x quantity squared as well. So I'm going to erase that and say squared there. So I have this minus twice this plus this. And in the end, that gives you expected value of x squared minus the expected value of x squared. So mean of the square minus the square of the mean. To check your understanding of how to use this formula, I'd like you to complete the following table. Now, I'll give you a head start on this. If your probability distribution is given by 1, 2, 4, 5, and 8, all equally likely, you can calculate the mean. Now, once you know the mean, you can calculate the deviations, x minus the mean, which I'd like you to fill in here. Then square that quantity and fill it in here, and take the mean of that squared deviation. Same as what we did when we talked about the variance as the mean squared deviation. Then, taking the other approach, I'd like you to calculate the squares of all of the x's and calculate the mean square. You know the mean square. You can calculate this quantity, mean of the square minus the square of the mean, and you should get something that equals the mean squared deviation. That's about it for variance, but just to say a little bit more about this, variance is not the end of the story. It turns out there's more. I mentioned the distributions that we were talking about earlier on the first slide here. Keep forgetting to turn my ruler off. The distributions that look like this versus distributions that look like this. This is a question of symmetry, and the mathematical name for this is skew, or skewness. There's also distributions that look like this versus distributions that look like this. And this is mathematically, this is called kurtosis, which kind of sounds like a disease or perhaps a villain from a comic book. Kurtosis has to do with the relative weights of things near the peak versus things in the tails. Now, mathematically speaking, you know the variance, let me go back a little further. You know the mean, that was related to the integral of x, rho of x, dx. We also just learned about the variance, which was related to the integral of x squared, rho of x, dx. It turns out the skewness is related to the integral of x cubed, rho of x, dx, and the kurtosis is related to the integral of x to the fourth rho of x dx. At least those are common ways of measuring skewness in kurtosis. These are not exact formulas for skewness and kurtosis, nor is this an exact formula for the variance, of course, so I'm taking some liberties with the math. But you can imagine, well, what happens if you take the integral of x to the fifth rho of x dx? You could keep going, and you would keep getting properties of the probability distribution that are relevant to its shape. Now, you won't hear very much about skewness and kurtosis in physics, but I thought you should know that this field does sort of continue on. For the purposes of quantum mechanics, what you need to know is that variance is related to the uncertainty, and we will be doing lots of calculations of variance on the basis of probability distributions derived from wave functions in this class. We talked a little bit about the probabilistic interpretation of the wave function psi. That's one of the really remarkable aspects of quantum mechanics, that there are probabilities rolled up in your description of the physical state. We also talked a fair amount about probability itself, and one of the things we learned was that probabilities had to be normalized, meaning the total sum of all of the probable outcomes, the probabilities of all of the outcomes in a probability distribution has to equal 1. That has some implications for the wave function, especially in the context of the Schrödinger equation, so let's talk about that in a little more detail. Normalization in the context of a probability distribution just means that the integral from minus infinity to infinity of rho of x dx is equal to 1. You can think about that as the sort of extreme case of the probability that, say, x is between a and b, being given by the integral from a to b of rho of x dx. In the context of the wave function, that statement becomes the probability that the particle is between a and b is given by the integral from a to b of the squared magnitude of psi of x integrated between a and b. So this is the same sort of statement. You're integrating from a to b, and in the case of the probability density, you have just the probability density. In the case of the wave function, you have the squared absolute magnitude of the wave function. This is our probabilistic interpretation. We're sort of making an analogy between psi, squared magnitude, and a probability density. This normalization condition, then, has to also hold for psi, if the squared magnitude of psi is going to be treated as a probability density. So, integral from minus infinity to infinity of squared absolute magnitude of psi dx has to equal 1. This is necessary for our statistical interpretation of the wave function. This brings up an interesting question, though, because not just any function can be a probability distribution. Therefore, this normalization condition, treating psi as a probability density, means there are some conditions on what sorts of functions are allowed to be wave functions. This is a question of normalizability. Suppose, for instance, I had a couple of functions that I was interested in. Say one of those functions looks sort of like this, keeps on rising as it goes to infinity. If I wanted to consider the squared magnitude of this function, this is our possible psi. This is our possible psi squared. Sorry about the messy there. This function, since it's going to, it's continuing to increase as x increases, both in the negative direction and in the positive direction, its squared magnitude is going to look something like this. I can do a little better there, sorry. If I tried to, say, calculate the integral from minus infinity to infinity of this function, I've got a lot of area out here from, say, 3 to infinity, where the wave function is positive. This would go to infinity, therefore. What that means is that this function is not normalizable. Not all functions can be normalized. If I drew a different function, for example, something that looked maybe something like this, its squared magnitude might look something like this.
there is a finite amount of area here. So if I integrated the squared magnitude of the blue curve, I would get something finite. What that means is that whatever this function is, I could multiply or divide it by a constant such that this area was equal to 1. I could take this function and convert it into something such that the integral from minus infinity to infinity of the squared magnitude of psi equaled 1, and it obeyed our sort of statistical constraint on the probability distribution. In order for this to be possible, psi has to have this property, and the mathematical way of stating it is that psi must be square integrable. And all this means is that the integral from minus infinity to infinity of the squared magnitude of psi is finite. You don't get 0, you don't get infinity. In order for this square integrability to hold, for example, though, you need a slightly weaker condition that psi goes to 0 as x goes to either plus or minus infinity. It's not possible to have a function that stays non-zero or goes to infinity itself as x goes to infinity and still have things be integrable. Like I said, if this holds, if this integral here is finite, you can convert any function into something that is normalized by just multiplying or dividing by a constant. Is that possible, though? In the Schrodinger equation, does multiplying or dividing by a constant do anything? Well, the Schrodinger equation here you can just glance at it and see that multiplying and dividing by a constant doesn't do anything. The Schrodinger equation is I h bar partial derivative with respect to time of psi equals minus h bar squared over 2m second derivative of psi with respect to position plus the potential times psi. Now, if I made the substitution psi went to some multiple or some constant a multiplied by psi, you can see what would happen. Here I would have psi times a, here I would have psi times a, and here I would have psi times a. So I would have an a here, an a here, and an a here. So I could divide through this entire equation by a, and all of those a's would disappear, and I would just get the original Schrodinger equation back. What that means is that if psi solves the Schrodinger equation, a psi does too. I'll just say a psi works. Now this is only if a is a constant. Does not depend on time, does not depend on space. If a depended on time, I would not be able to divide it out of this partial derivative because the partial derivative would act on that a. Same goes for if a was a function of space. If a was a function of space, I wouldn't be able to divide it out of this partial derivative with respect to x. So this only holds if a is a constant. That means that I might run into some problems with time evolution. I can choose a constant and I can multiply psi by that constant such that psi is properly normalized at, say, time t equals 0, but will that hold for future times? It's a question of normalization and time evolution. What we're really interested in here is the integral from minus infinity to infinity of psi of x and time squared dx. If this is going to always be equal to 1, supposing it's equal to 1 at some initial time, what we really want to know is what the time derivative of this is. If the time derivative of this is equal to 0, then we'll know that whatever the normalization of this is, it will hold throughout the evolution of the wave function. Now I'm going to make a little bit of simplifying notation here, and I'm going to drop the integral limits since it takes a while to write. And we're going to manipulate this expression a little bit. We're going to use the Schrodinger equation. We're going to use the rules of complex numbers. We're going to use the rules of differential calculus. And we're going to get something that will show that indeed this does hold. So let's step through that. Manipulations of the Schrodinger equation like this are a little tricky to follow, so I'm going to go slowly, and if it seems like I'm being extra pedantic, please bear with me. Some of the details are important. So the first thing that we're going to do, pretty much the only thing that we can do with this equation, is we're going to exchange the order of integration and differentiation. Instead of differentiating with respect to time the integral with respect to x, we're going to integrate with respect to x of the time derivative of this psi of x and t quantity squared. Basically, I've just pushed the derivative inside the integral. Now, notationally speaking, and I'm going to move some stuff around here, give myself a little more room. Notationally, oops, didn't mean to change the colors. Notationally speaking here, the d dt became a partial derivative with respect to time. The total derivative, d by dt, is now a partial. What the notation is keeping track of here is just the fact that this is a function only of time, since you've integrated over x and you've substituted in limits. Whereas this is a function of both space and time. So whereas this derivative is acting on something that's only a function of time, I can write it as a simple d by dt, the total derivative. In this case, since what the derivative is acting on is a function of both position and time, I have to treat this as a partial derivative now. So the next thing that we're going to do, aside from after pushing this derivative inside and converting it to a partial derivative, is rewrite this squared absolute magnitude of psi as psi star times psi. Now the squared absolute magnitude of a complex number is equal to the complex number times its complex conjugate. It's just simple complex analysis rules there. So what we've got is the integral of the partial derivative with respect to time of psi star times psi, integral dx. Now we have a time derivative applied to a product. We can apply the product rule from differential calculus. And what we end up with is the integral of the partial derivative with respect to time of psi star times psi plus psi star partial derivative of psi with respect to time. That's integrated dx. Now what I'm going to do is I'm going to notice these partial derivatives with respect to time. And I'm going to ask you to bear with me for a minute while I make a little more space. It's probably a bad sign if I'm running out of space on a computer where I have effectively infinite space. But bear with me. The partial derivatives with respect to time appear in the Schrodinger equation. I h bar d by dt of psi equals minus h bar squared over 2m partial derivative, second partial derivative of psi with respect to position plus potential times psi. These are the time derivatives that I'm interested in. I can use the Schrodinger equation to substitute in, say, the right-hand side for these time derivatives, both for psi star and for psi. So first I'm going to manipulate this by dividing through by I h bar, which gives me d partial psi partial time equals I h bar over 2m, second partial of psi with respect to x, minus, where did it go? I v over h bar psi. So that can be substituted in here. I also need to know something for the complex conjugate of psi, so I'm going to take the complex conjugate of this entire equation. What that looks like is partial derivative of psi star with respect to time. Now I'm taking the complex conjugate of this, so I have a complex part here. The sign of that needs to be flipped. And I have a complex number here. that needs to be complex conjugated, since the complex conjugate of a product is the product of the complex conjugates. What that means is this is going to become minus I h bar over 2m d squared psi star dx squared, sorry I forgot the squared there, plus I v over h bar psi. So I've just gone through and changed the signs on all of the imaginary parts of all these numbers. Psi became psi star, I became minus I became I. And this can be substituted in for that. And what you get when you make that substitution, this equation isn't really getting simpler, is it? It's getting longer. What you get is the integral of something. I'll put an open square brackets at the beginning here. I've got this equation, minus I h bar over 2m, second partial derivative of psi star partial x squared, plus I v over h bar psi star, that's multiplied by psi from here. So I just substituted in this expression for this. Now the next part I have plus psi star and whatever I'm going to substitute in from this, which is what I get from this version of the Schrodinger equation here. I h bar over 2m second partial derivative of psi with respect to x minus I v over h bar psi. Close parentheses, close square brackets, and I'm integrating dx. Now, this doesn't look particularly simple, but if you notice what we've got here, this term, if I distributed this psi in, would have I v over h bar psi star times psi. This term, if I distributed this psi star in, it would have an I v over h bar psi star and psi. This term has a plus sign, this term has a minus sign. So these terms actually cancel out. What we're left with, then, to rewrite things, both of the terms that remain have this minus I h bar over 2m out front. So we're going to have equals to I h bar over 2m. And here I have a minus second partial derivative of psi star with respect to x times psi. And here I have plus psi star times the corresponding second partial of psi with respect to x. And this is integrated dx. Is that all right? Yes. Now, what I'd like you to notice here is that we've got d by dx and we've got an integral dx. We don't have any time anymore. So we're making progress. And we're actually almost done. Where did we get so far? We started with the time derivative of this effective total probability, which should have been equal to 1, which would be equal to 1 if this were a proper probability distribution, but we're just considered with the time evolution, since we know that whatever psi is, we can multiply it by some constant to make it properly normalized at a particular time. Now we're interested in the time evolution. We're looking at the time derivative of this, and we've gone to this expression, which has complex conjugates of psi and second partial derivatives with respect to x. Now, what I'd like you to do, and this is a check your understanding question, is think about why this statement is true. This is the partial derivative with respect to x of psi star d psi dx minus d psi star dx. So, sorry, I'm saying d, I should be saying partial. These are partial derivatives. This is true, and it's up to you to figure out why. But since this is true, what we're left with is we have our I h bar over 2m, an integral over minus infinity to infinity of this expression, partial with respect to x of psi star partial psi partial x minus partial psi star partial x psi. we're integrating dx now. And this is nice because we're integrating dx of a derivative of something with respect to x. So that's easy. Fundamental theorem of calculus. We end up with I h bar over 2m psi star partial psi partial x minus partial psi star partial x psi, evaluated at the limits of our integral, which are minus infinity to infinity. Now, if psi is going to be normalizable, we know something about the value of psi at negative and positive infinity. If psi is normalizable, psi has to go to 0 as x goes to negative and positive infinity. What that means is that when I plug in the infinity here, psi star, d psi dx, and psi, everything here is going to be 0. So when I enter in my limits, I'm just going to get 0 and 0. So the bottom line here, after all of this manipulation, is that this is equal to 0. What that means is that the integral from negative infinity to infinity of the squared absolute magnitude of psi as a function of both x and time is equal to a constant. Put another way, time evolution does not affect normalization. What that means is that I can take my candidate wave function, not normalized, integrate it, find out what I would have to multiply or divide it by to make it normalized, and if I'm successful, I have my normalized wave function. I don't need to worry about how the system evolves in time. The Schrödinger equation does not affect the normalization. So this is that check your understanding question I mentioned. The following statement was that crucial step in the derivation, and I want you to show that this is true, explain why in your own words. Now, to do an example here, normalize this wave function. What that means is that we're going to have to find a constant, and I've already put the constant in the wave function, a, such that the integral from minus infinity to infinity of the squared absolute magnitude of psi of x, in this case I've left the time dependence out, is equal to 1. And same as in the last problem, the first thing we're going to do is substitute the squared absolute magnitude of psi for psi star times psi. The other thing I'm going to do before I get started is notice that my wave function is 0 if the absolute value of x is greater than 1, meaning for x above 1 or below negative 1. So instead of integrating from minus infinity to infinity here, I'm just going to focus on the part where psi is non-zero and integrate from minus 1 to 1. Integral from minus 1 to 1 of psi star, which is going to be a, e to the ix is going to become e to the minus ix, and 1 minus x squared is still going to be 1 minus x squared. Now, I haven't complex conjugated a because part of the assumption about normalization constants like this is usually that you can choose them to be purely real. So I'm not going to worry about taking the complex conjugate of a, just to make my life a little easier. Psi, well, that's just right here, a e to the ix, 1 minus x squared. And I'm integrating dx. This is psi star, this is psi, integral dx from minus 1 to 1, should be equal to 1. So let's do this. We end up with a squared times the integral from minus 1 to 1 of e to the minus ix and e to the ix. What's e to the minus ix times e to the ix? Well, thinking about this in terms of the geometric interpretation, we have e to the ix, which is cosine theta plus I sine theta. You can think about that as being somewhere on the unit circle at an angle theta. Minus ix, or minus I theta, would just be in the exact opposite direction. So when I multiply them together, I'm going to get something that has the product of the magnitudes. The magnitudes are both 1, and it's purely real. You can see that also by looking at just the rules for multiplying exponentials like this. E to the minus ix times e to the plus ix is e to the minus ix plus ix, or e to the 0, which is 1. So I can cancel these out. And what I'm left with is 1 minus x squared, quantity squared, dx. Plugging through the algebra a little further, a squared, integral minus 1 to 1, of 1 minus 2x squared plus x to the 4th dx. You can do this integral equals a squared to, x minus 2/3 x cubed plus x to the 5th over 5 between minus 1 and 1, which when you substitute in the limits becomes a squared. This x part is going to be 1 minus the other limit, minus 1, which is 1 minus minus 1, which is 2. So going to give me a 2, minus 2/3 of whatever I get from the x cubed, which is again going to be 1 minus a minus 1, or 2, plus 1/5 of x to the 5th, 1, minus 1 to the 5th, and 1 to the 5th. Again, this is all, basic algebra. Hopefully this is not too confusing by this point. This ends up being a squared times 16 over 15. Now, going up here, if a squared 16 over 15 is going to be equal to 1, a has to be equal to the square root of 15 over 16. That's what it means to normalize a wave function. You have something that you think might be your wave function, but it's not properly normalized yet. So you guess that there's going to be some constant multiplied in, and you write down the normalization condition, integrating your wave function absolute magnitude squared, which usually you will write as the wave function times its complex conjugate. Typically the complex parts of the wave function will drop out, and you'll end up with just something that you can integrate. Proceeding through the integral, you'll end up with some expression that tells you what that constant is. So that's the wave function and how it's normalized. The time evolution of the normalization and the fact that it's not affected by the Schrodinger equation is really a nice feature of quantum mechanics. Otherwise, quantum mechanics would be completely unworkable. A lot of what we've talked about in this lecture has just been how to manipulate the Schrodinger equation, or how to use the Schrodinger equation in manipulations of the wave function. And this is the sort of math that quantum mechanics is all about. There's calculus, there's partial derivatives, total derivatives, integrals. Keeping track of everything is tricky. Well, the result that we've got for normalization here helps. I'm rambling though. At any rate, that's about it for wave functions and normalization. And this is nice because all of the pieces that we've described today all fit together and support this statistical interpretation of the wave function as being related to a probability distribution. We know in quantum mechanics that all of the information about the physical system is encapsulated in the wave function psi. Psi then ought to be related to physical quantities for for example, position, velocity, and momentum of the particle. We know a little bit about the position. We know how to calculate things like the expected value of the position, and we know how to calculate the probability that the particle is within a particular range of positions. But what about other dynamical variables like velocity or momentum? The connection with velocity and momentum brings us to the point where we really have to talk about operators. Operators are one of our fundamental concepts in quantum mechanics, and they connect the wave function with physical quantities. But let's take a step back first and think about what it means for a quantum system to move.
The position of the particle, we know, say, the integral from a to b of the squared magnitude of the wave function dx gives us the probability that the particle is between a and b. And we know that the expected position is given by a similar expression, the integral from minus infinity to infinity of psi star of x times psi of x dx. Now these expressions are related, by the fact that the squared magnitude of psi is the probability density function describing position, and this is really just the calculation of the expected value of x given that probability density function. Now what if I want to know what the motion of the particle is? One way to consider this is, suppose I have a box, and if I know the particle is, say, here, at time t equals 0, what can quantum mechanics tell me about where the particle is later? Physically speaking, you could wait until, say, t equals 1 second, and then measure the position of the particle. And maybe it would be here. You could then wait a little longer and measure the particle again. Maybe at that point it would be here. That's, say, t equals 2 seconds. Or if I wait a little bit longer and measure the particle yet again at, say, t equals 3 seconds, maybe the particle would be up here. Now, does that mean that the particle followed a path that looked something like this? No. We know that the position of the particle is not something that we can observe at any given time with impunity because of the way the observation process affects the wave function. Back when we talked about measurement, we talked about having a wave function that looked something like this, a probability density that looked something like that, and then after we measure the position of the particle, the probability density has changed. If we say measure the particle to be here, the new wave function has to accommodate that new probability density function. The fact that measurement affects the system like this means that we really can't imagine repeatedly measuring the position of a particle in the same system. What we really need is an ensemble. That's the technical term for what we need. What an ensemble means in this context is that you have many identically prepared systems. Now, if I had many identically prepared systems, I could measure the position over and over and over and over again, once per system. If I have, 100 systems, I could measure the position 100 times, and that would give me a pretty good feel for what the probability density for position measurements is at the particular time when I'm making those measurements. If I wanted to know about the motion of the particle, I could do that again, except instead of taking my 100 measurements all at the same time, I would take them at slightly different times. So instead of this being the same system, these would all be different systems that have been allowed to evolve for different amounts of time. And as such, the motion of the particle isn't going to end up looking something like that. It's going to end up looking like some sort of probabilistic motion of the wave function in space. What we're really interested in here, oh, sorry, I should make a note of that. Single measurement per system. This notion of averaging over many identically prepared systems is important in quantum mechanics because of this effect that measurement has on the system. So what we're interested in now, in the context of something like motion, is, well, can we predict this? Can we predict where the particle is likely to be as a function of time? And yes, we can. And what I'd like to do to talk about that is to consider a quantum mechanical calculation that we can actually do, the time derivative of the expected value of position. This time derivative tells us how the center of the probability distribution, if you want to think about it that way, how the center of the wave function moves with time. So this time derivative, d by dt of the expected value of x, that's d by dt of, let's just write out the expected value of x, integral from minus infinity to infinity of x times psi star of x, psi of x, where this is the probability density function that described or given by the wave function, and this is x. We're integrating dx. Now, if you remember when we talked about normalization and whether the normalization of the wave function changed as the wave function evolved in time, we're going to do the same sort of calculation with this. We're going to do some calculus with this expression. We're going to apply the Schrodinger equation. But as before, the first thing we're going to do is move this derivative inside the equation. This is a total time derivative of something that's a function of, in principle, position and time. I should write these as functions of x and t. And what you get when you push that in is, as before, the integral, or the total derivative becomes a partial derivative. Since x is just the coordinate x in these contexts of functions of both space and time, the total time derivative will not affect the coordinate x, even when it becomes a partial derivative. So what we'll end up with is x times the partial time derivative of psi star psi, integral dx. I'm not going to write the integral from minus infinity to infinity here just to save myself some time. Now, if you remember this expression, the integral, or sorry, not the full integral, just the partial time derivative of psi star psi, that was what we worked with in the lecture on normalization. So if we apply the result from the lecture on normalization, and it's equation 126, yes, in the book, if we apply that, you can simplify this down a lot right off the bat. And what you end up with is I h bar over 2m times this integral x, and then what we substitute in. The equation 126 gives an expression for this highlighted part here in orange. And what you get is the partial derivative with respect to x of psi star partial of psi with respect to x minus partial of psi star with respect to x times psi. Integral still with respect to dx, of course. Now, if we look at this equation, we're making the same sort of progress we made when we did the normalization derivation. We had time derivatives here. Now we have only space derivatives. And we have only space derivatives in an integral over space. So this is definitely progress. Now we can start thinking about what we can do with integration by parts. The first integration by parts I'm going to do has the non-differential part just being x, and the differential part being dv is equal to, I'm not going to have space to write this here. I'm going to move stuff around a little bit. So the differential part is dv is the partial derivative, well, what's left of this equation, the partial derivative with respect to x of psi star d psi dx minus d psi dx psi, d psi star dx psi. And then there's the dx from the integral. Sorry, I'm running out of space. This differential part here is just this part of the equation. Now I can take this derivative, du dx, in my integration by parts procedure, du equals dx, and dv here is easy to integrate because this is a derivative. So when I integrate the derivative there, I'll just end up with v equals psi star d psi dx minus d psi star dx psi. Now when I actually apply those, that integration by parts, the boundary term here without the integral in it is going to involve these two. So I'm going to have x times psi star partial x minus partial psi star, partial x psi. And that's going to be evaluated between minus infinity and infinity, the limits on my integral. The integral part, which comes in with a minus sign, is going to be composed of these bottom two terms. Integral of psi star partial x minus partial psi star partial x psi, and its integral dx from minus infinity to infinity. Now what's nice, I forgot something here. What did I forget? My leading constants. I still have this I h bar over 2m out there. I h bar over 2m is multiplied by this entire expression. Now, the boundary terms here vanish. The boundary terms in integration by parts in quantum mechanics will often vanish because if you're evaluating something at, say, infinity, psi has to go to 0 at infinity, so this term is going to vanish. Psi star has to go to 0 at infinity, so this is going to vanish. So even though x is going to infinity, psi is going to 0. And if you dig into the mathematics of quantum mechanics, you can show convincingly that the limit as x times psi goes to infinity is going to be 0. So this boundary term vanishes, both at infinity and at minus infinity. And all we're left with is this. Yes. All you're left with is that. So I'll write that over. I h bar over 2m times the integral of psi star partial x minus partial psi star partial x psi integral dx. I'm actually going to split that up into two separate integrals. So I'll stick another integral sign in here, and I'll put a dx there. And I'll put parentheses around everything so my leading constant gets multiplied in properly. And now I'm going to apply integration by parts again, but this time just to the second integral here. So here, we're going to say u is equal to psi, and dv is equal to, again, using the fact that when we do this integral, if we can integrate a derivative, that potentially simplifies things. So this is going to be partial psi star partial x dx. So when we take the derivative of this, we're going to get du is equal to partial psi partial x. And when we integrate this, we're going to get v equals psi star. Now, when we do the integration, when we write down the answer from this integration by parts, the boundary term here, psi star times psi, is going to vanish, again, because we're evaluating it at a region where both psi star and psi, vanish. So the boundary term vanishes. And you notice I have a minus sign here. When we do the integration by parts, the integral term has a minus sign in it here. So we're going to have the partial psi with respect to x and psi star with a minus sign coming from the integration by parts and a minus sign coming from the leading term here. So we're going to end up with a plus sign there. So we get a minus from the integral part. What that means, though, is that I have psi star and partial psi partial x. In my integration by parts, I end up with partial psi partial x and psi star. It's the same. And the fact that I had a minus and another minus means I get a plus. So I have two identical terms here. The result of this, then, is I h bar over m. I'm adding a half and getting 1, basically, times the integral of psi star partial psi partial x dx. And this is going to be something that I'm going to call now the expectation of the velocity vector, the velocity operator. This is the sort of thing that you get out of operators in quantum mechanics. You end up with expressions like this. And this I'm sort of equating just by analogy with the expectation of a velocity operator. This is not really a probability distribution anymore, at least not obviously. We started with a probability distribution due to psi, the absolute magnitude of psi squared, and we end up with the partial derivative on one of the psi's. So it's not obvious that this is a probability distribution anymore, and well, it's the probability distribution in velocity, and it's giving you the expected velocity. in some sense, in a quantum mechanical sense. So this is really a more general sort of thing. We have the velocity operator, the expectation of the velocity operator. Oh, and operator-wise, I will try to put hats on things. I will probably forget. I don't have that much attention to detail when I'm making lectures like this. The hat notation means operator. If you see something that you're really sure is an operator but it doesn't have a hat, that's probably just because I made a mistake. But this expression for the expectation of the velocity operator is the one we just derived, minus I h bar over m times the integral of psi star partial derivative of psi with respect to x integral dx. Now it's customary to talk about momentum instead of velocity. Momentum has more meaning because it's a conserved quantity under most physics. So we can talk about the momentum operator, the expectation of the momentum operator. And I'm going to write this momentum operator expression in a slightly more suggestive way. The integral of psi star times something in parentheses here, which is minus I h bar, partial derivative with respect to x, and I'm going to close the parentheses there, put a psi after it, and a dx for the integral. You have the same sort of expression for the position operator. We were just writing that as the expected value of position without the hat earlier. But that's going to be the integral of psi star. What goes in the parentheses now is just x psi dx. So this you recognize as the expectation of the variable x, subject to the probability distribution given by psi star times psi. This is slightly more subtle. You have psi star and psi, which looks like a probability distribution, but what you have in the parentheses now is very obviously an operator that does something. It does more than just multiply by x. It multiplies by minus I h bar and takes the derivative of psi. Operators in general do that. We can write them as, say, x hat equals x times, where there's very obviously something that has to go after the x in order for it to be considered an operator. Or we can say the same for v hat. It's minus I h bar over m times the partial derivative with respect to x, where there obviously has to be something that goes here. Likewise for momentum, minus I h bar partial derivative with respect to x. Something has to go there. Another example of an operator is the kinetic energy operator. Usually that's written as T. And that's minus h bar squared over 2m. You can think of it as the momentum operator squared. It's got a second derivative with respect to x. And again, there very obviously has to be something that goes there. The operator acts on the wave function. That's what I said back when I talked about the fundamental concepts of quantum mechanics, and this is what it means for the operator to act on the wave function. The operator itself is not meaningful. It's only meaningful in the context when it's acting on a wave function. In general, wrong color. In general, the expectation value of some operator, which I'll just call Q, is going to be the integral of psi star Q psi dx, where Q acts on the psi. And this is what allows us to, say, predict the expected value of really any physical quantity. You need to know how to write that physical quantity in terms of operators, and typically this Q hat here will be written as, something with x hat, the position operator, and p hat, the momentum operator. So the operators can in principle be quite complicated, but they're generally expressed in terms of simpler operators like position and momentum. To give an example of how this is actually used, suppose I want to find the expected value of the momentum for the wave function given by psi. Psi here is that wave function that I talked about back in the normalization example, where I found what the value of a was to normalize this wave function properly. I'm just going to leave it as a for now and deal with the wave function part. It's also important to note that this wave function has no time dependence and it has no complex part. So I'm simplifying things a lot. You will work with wave functions that look a lot like this under specific conditions, but know that this isn't a general wave function. This isn't a solution to any particular Schrodinger equation. This is just something that I'm cooking up as an example. It is a valid wave function, at least if you consider it at, say, t equals 0. The goal is to find p hat, expected value. And the expected value of something, you know, expected value of p hat is given by the integral of psi star p hat psi dx, which is the integral, and this integral will be from minus infinity to infinity, but since my wave function is 0 for absolute value of x greater than 1, I'm going to drop the condition here and make my integral only go from minus 1 to 1. And for psi star, I have a, complex conjugate of a, assuming it's real, 1 minus x squared, complex conjugate of 1 minus x squared, x is real, no complex conjugate, or complex conjugate has no effect here, times the momentum operator, which is going to be I h bar minus I h bar, partial derivative with respect to x, of psi, without the complex conjugate, a, 1 minus x squared, all integrated dx. Now I can simplify this a little bit. You end up with the integral from minus 1 to 1. Oh, sorry, let me pull my I h bar out front. Minus I h bar, integral from minus 1 to 1 of, I can pull out the a squared as well. Integral from minus 1 to 1 of 1 minus x squared times the derivative now of 1 minus x squared. Well, the derivative of 1, or this is a sum, so I can push the derivative in. So the derivative of 1 is 0, and the derivative of minus x squared is minus 2x. So I'm going to have a minus 2x here. I'll just write 2x, and I'll put a plus sign out front to compensate for the minus sign. And this is integrated dx. This then is I h bar, let's say 2 I h bar, I can pull the 2 out as well, a squared, integral from minus 1 to 1 of x minus x cubed dx. Now right away, hopefully you can look at this and say x minus x cubed. This is an odd function, meaning if I actually plotted this, it would look something like this. This is my coordinate system, x minus x cubed. It's going to look something like this, where f of x equals minus f of minus x. What that means is when I integrate this from minus 1 to 1 over an interval that starts equally far into the negative side as it goes into the positive side, I'm going to get 0. So you can just write down, just by looking at this, that the integral is going to be 0. You can also, of course, plug this in. You'll get x squared over 2 and x to the 4th over 4 for these integrals, and then you'll plug in minus 1 and 1 and find out that minus and plus doesn't make any difference for x squared and x to the 4th, and you'll end up with 0 that way as well. But the bottom line here is that the expected value of momentum is equal to 0. And this makes sense. The reason this makes sense is that my wave function is symmetric. If that's a coordinate system, we can say this is the x-axis. If this is going to be my wave function, could look, don't want the ruler, my wave function would look something like this, where it goes from minus 1 to 1, and it's 0 outside of that range. Now, if you had an expected value of momentum that was non-zero here, that would suggest the wave function was on average moving. And if you look at this wave function, psi, it doesn't really seem to be moving. There's no preferred direction to this. If you showed me this psi and asked, is it moving to the left or to the right, I wouldn't be able to tell you. And it makes sense then that the expected value of the momentum is 0. The wave function is effectively not moving, or the particle represented by this wave function has no momentum on average. Now, this doesn't mean that if you measure the momentum of the particle as described by this wave function, you would always get 0. It just means you would get 0 on average. So that's a little bit about operators, and we'll be working with operators much more in the future. The basic concepts that I want you guys to take away from this lecture is that the expected value of some general operator is what you get if you take psi star and psi and sandwich your operator in between them and integrate. And then know that the operator may actually do something to psi. It's not just a multiplication. So I cannot say that this q hat is equal to the integral of q hat psi star psi dx. I can't just move the q around. I'm not allowed to do that because q is acting on this psi. Really, this is just reasoning by analogy right now. There is no rigorous formal proof. We'll come back to discuss the math of quantum mechanics quite a lot later on. But that's it for this lecture. As a check your understanding, I'd like you to find the expected value of the kinetic energy operator for this wave function. Remember that the kinetic energy operator T hat is equal to minus h bar squared over 2m times the second derivative with respect to x. And I almost wrote a psi there, but I'm not supposed to write a psi. The operator has to act on psi. So there should be some space here for psi to go. So go back to that same formula for the expectation. Use the kinetic energy operator instead and calculate the expected value of the kinetic energy for this wave function.
As an introduction to the uncertainty principle, we're going to talk about waves and how waves are related to each other. We'll get into a little bit of the context of Fourier analysis, which is something we'll come back to later. But the overall context of this lecture is the uncertainty principle. And the uncertainty principle is one of the key results from quantum mechanics, and it's related to what we discussed earlier in the context of the boundary between classical physics and quantum physics. Quantum mechanics has these inherent uncertainties that are built into the equations, built into the state, built into the nature of reality that we really can't surmount. And the uncertainty principle is one way in which those, or is the mathematical description. It's those relationships that I gave you earlier. Delta p, delta x is greater than about equal to h bar over 2. I think I just said greater than about equal to h bar earlier. We'll do things a little more mathematically here, and it turns out there's a factor of 2 there. To start off, though, conceptually think about position and wavelength. And this really is now in the context of a wave. So say I had a coordinate system here, something like this. And if I had some wave with a very specific wavelength, you can just think about it as a sinusoid. If I asked you to measure the wavelength of this wave, you could take a ruler and you could plop it down there and say, okay, well, how many inches are there from peak to peak, or from zero crossing to zero crossing? Or if you really wanted to, you could get a tape measure and measure many wavelengths, 1, 2, 3, 4 wavelengths in this case. That would allow you to very accurately determine what the wavelength was. If, on the other hand, the wave looked more like this, give you another coordinate system here, the wave looked something like this, you wouldn't be able to measure the wavelength very accurately. You could, as usual, put your ruler down on top of the wave, for instance, and count up the number of inches or centimeters from one side to the other, but that's just one wavelength. It's not nearly as accurate as, say, measuring 4 wavelengths, or 10 wavelengths, or 100 wavelengths. You can think of some limiting cases. Suppose you had a wave with many oscillations. It looks like I'm crossing out the wave underneath there, so I'm going to erase this in a moment. But if you had a wave with many wavelengths, and you could measure the total length of many wavelengths, you would have a very precise measurement of the wavelength of the wave. The opposite is the case here. You only have one wavelength. You can't really measure the wavelength very accurately. What you can do, however, is measure the position very accurately. Here, I can say pretty certainly the wave is there, plus or minus a very short spread in position. The other hand, here, I cannot measure the position of this wave accurately at all. If this thing continues, I can't really say where the wave is. It's not really a sensible question to ask, where is this wave? This wave is everywhere. These are the sorts of built-in uncertainties that you get out of quantum mechanics. Where is the wave? The wave is everywhere. It's a wave. It doesn't have a local position. It turns out, if you get into the mathematics of Fourier analysis, that there is a relationship between the spread of wavelengths and the spread of positions. If you have a series of waves of all different wavelengths and they're added up, the spread in the wavelength is related to the spread in positions of the sum. And we'll talk more about Fourier analysis later, but for now, just realize that this product is always going to be greater than or equal to about 1. Wavelength is something with units of inverse length, and the position, of course, is something with units of length. So the dimensions of this equation are sort of a guideline. Wavelength and position have this sort of relationship, and this comes from Fourier analysis. So how do these waves come into quantum mechanics? Well, waves in quantum mechanics really first got their start with Louis de Broglie. I always thought his name was pronounced de Broglie, but it's, well, he's French, so there's all sorts of weird pronunciations in French. De Broglie is my best guess at how it would probably be pronounced. De Broglie proposed that matter could travel in waves as well. And he did this with an interesting argument on the basis of 3 fundamental equations that had just recently been discovered when he was doing his analysis. This was in his PhD thesis, by the way. E equals mc squared. You all know that equation. You all hopefully also know this equation, E equals hf. Planck's constant times the frequency of a beam of light is the energy associated with a quanta of light. This was another one of Einstein's contributions, and it has to do with his explanation of the photoelectric effect. The final equation that de Broglie was working with was C equals f lambda. The speed of light is equal to the frequency of the light times the wavelength of the light. And this is really not true just for light. This is true for any wave phenomenon. The speed, the frequency, and the wavelength are related. Now, if these expressions are both equal to waves, or are both equal to energy, then I ought to be able to say mc squared equals hf. And this expression tells me something about f. It tells me that f equals c over lambda. So I can substitute this expression in here and get mc squared equals hc over lambda. Now I can cancel out one of the c's, and I'm left with mc equals h over lambda. Now what de Broglie said was this is like momentum. So I'm going to write this equation as p equals h over lambda. And then I'm going to wave my hands extraordinarily vigorously and say, while this equation is only true for light, and this equation is only true for waves, this is also true for matter. How actually this happened in the context of quantum mechanics, in the early historical development of quantum mechanics, is de Broglie noticed that the spectrum of the hydrogen atom, these bright line spectra that we were talking about, where a hydrogen atom emits light of only very specific wavelengths. Intensity as a function of wavelength looks something like this. That could be explained if he assumed that the electrons were traveling around the nucleus of the hydrogen atom as waves, and that only an integer number of waves would fit. The one that I just drew here didn't end up back where it started, so that wouldn't work. If you had a wavelength that looked something like this, going around, say, 3 full times in a circle, that would potentially account for these allowed emission energies. That was quite a deep insight, and it was one of the things that really kicked off quantum mechanics at the beginning. The bottom line here, for our purposes, is that we're talking about waves, and we're talking about matter waves. So that uncertainty relation, or the relationship between the spreads of wavelengths and the spreads in positions that I mentioned in the context of Fourier analysis, will also potentially hold for matter. And that gets us into the position-momentum uncertainty relation. The wave-momentum relationship we just derived on the last slide was p equals h over lambda. This tells you that the momentum and the wavelength are related. From 2 slides ago, when we were talking about waves and whether or not you could say exactly where a wave was, we had a relationship that was something like delta lambda, the spread in wavelengths, times the spread in positions of the wave, is always greater than about equal to 1. Combining these relationships together in quantum mechanics, and this is not something that I'm doing rigorously now, I'm just waving my hands, gives you delta p delta x is always greater than about equal to h bar over 2. And this is the correct mathematical expression of the Heisenberg uncertainty principle that we'll talk more about and derive more formally in Chapter 3. But for now, just realize that the position of a wave, the position of a particle, are uncertain quantities, and the uncertainties are related by this, which in one perspective results from consideration of adding many waves together in the context of Fourier analysis, which is something we'll talk about later as well, extended through the use of, or the interpretation of matter as also a wave phenomenon. To check your understanding, here are 4 possible wave packets, and I would like you to rank them in 2 different ways. 1, according to the uncertainties in their positions, and 2, according to the uncertainties in their momenta. So if you consider, say, wave B to have a very certain position, you would rank that one highest in terms of the certainty of its position. Perhaps you think wave B has a very low uncertainty in position, you would put it on the other end of the scale. I'm looking for something like the uncertainty of B is greater than the uncertainty of A is greater than the uncertainty of D is greater than the uncertainty of C for both position and momentum. The last comment I want to make in this lecture is on energy-time uncertainty. This was the other equation I gave you when I was talking about the boundary between classical physics and quantum physics. We had delta P delta X is greater than or equal to h bar over 2, and now we also had excuse me for a moment here, delta E, delta T, greater than about equal to h bar over 2. Same sort of uncertainty relation, except now we're talking about spreads in energy and spreads in time. And I'd like to make an analogy between these 2 equations. Delta P and delta X. Delta P, according to de Broglie, is related to the wavelength, which is sort of a spatial frequency. It's the frequency of the wave in space. Delta X, of course, is just, well, I'll just say that's a space. And these are related, according to this equation. In the context of energy and time, we have the same sort of thing. Delta T, well, that's pretty clear, that's time. And delta E, well, that then, therefore, by analogy here, has to have something to do with the frequency of the wave now in time. And that's simple, that's just the frequency. The fact that these are also related by an uncertainty principle tells you that there's something about energy and frequency in time. And this is something that we'll talk about in more detail in the next lecture when we start digging into the Schrödinger equation. The time-dependent Schrödinger equation and deriving the time-independent Schrödinger equation, which will give us the relationship exactly. But for now, position and momentum, energy and time, are both talking about sort of wave phenomenon, except in the context of position and momentum, you're talking about wave length, frequency of the wave in space, whereas energy and time, you're talking about the frequency of the wave in time, how quickly it oscillates. That's about all. The uncertainty principle, as I've said, is something that we'll treat in much more detail in Chapter 3. But for now, the uncertainty principle is important because you have these equations, and these are fundamental properties of the universe, if you want to think of them that way. And they're something that we're going to be working with as a way of checking the validity of quantum mechanics throughout the rest of throughout Chapter 2. That's all for now. You just need to conceptually understand how these wave lengths and positions or frequencies and times are interrelated. The last few lectures have been all about the wave function, psi. And since psi is such an important concept in quantum mechanics, really the first entire chapter of the textbook is devoted to the wave function and all of its various properties. Since we've reached the end of Chapter 1 now is a good opportunity to go and review the key concepts of quantum mechanics, in particular the wave function and how it is related to the rest of quantum mechanics. The key concepts, as I stated them earlier, were operators, the Schrödinger equation, and the wave function. Operators are used in the Schrödinger equation and act on the wave function. Your friend and mine, psi. What we haven't really talked about a lot yet is how to determine the wave function, and the wave function is determined as solutions to the Schrödinger equation. That's what Chapter 2 is all about, solving the Schrödinger equation for various circumstances. The key concepts that we've talked about so far, operators and the wave function, conspire together to give you observable quantities. Things like position or momentum, or say the kinetic energy of a particle. But they don't give us these properties with certainty. In particular, the wave function really only gives us probabilities. And these probabilities don't give us really any certainty about what will happen. Uncertainty is one of the key concepts that we have to work with in quantum mechanics. So let's take each of these concepts in turn and talk about them in a little more detail, since now we have some actual results that we can use, some mathematics. We can put more meat on this concept map than just simply the concept map. First, the wave function. The wave function, psi, does not tell us anything with certainty. And it's a good thing, too, because psi, as a function of position and time, is complex. It's not a real number. And it's hard to imagine what it would mean to actually observe a real number. So the wave function is already on somewhat suspect ground here. But it has a meaningful connection to probability distributions if we more or less define the squared modulus, the absolute magnitude of the wave function, to be equal to a probability distribution. And this is the probability distribution for what? Well, it's the probability distribution for outcomes of measurements of position, for instance. You can think about this as a probability distribution for where you're likely to find the particle should you go looking for it. This interpretation as a probability distribution requires the wave function to be normalized. Namely, that if I integrate the squared magnitude of the wave function over the entire space that I'm interested in, I have to get 1. This means that if I look hard enough for the particle everywhere, I have to find it somewhere. The probability distributions, as I mentioned earlier, don't tell you anything with certainty. In particular, there is a good deal of uncertainty, which we express as a standard deviation or a variance. For instance, if I'm interested in the standard deviation of the uncertainty, or standard deviation of the position, it's most easy to express as the variance, which is the square of the standard deviation. And the square of this standard deviation, or the variance, is equal to the expectation value of the square of the position minus the square of the expectation value of the position. And we'll talk about expectation values in a moment. Expectation values are calculated using expressions with operators that look a lot like these sorts of integrals. In fact, I can re-express this as the expectation of the square in terms of a probability distribution is just the x squared times multiplied by the probability distribution with respect to x, integrated over all space. This is the expectation of x squared. I can add to that, or subtract from that, the square of the expectation of x, which has a very similar form. And that gives us our variance. So our wave function, which is complex, gives us probability distributions, which can be used to calculate expectation values and uncertainties. This probabilistic interpretation of quantum mechanics gets us into some trouble pretty quickly. I'm going to move this up now. give myself some more space. Namely with the concept of wave function collapse. Now, collapse bothers a lot of people, and it should. This is really a philosophical problem with quantum mechanics, that we don't really have a good interpretation of what quantum mechanics really means for the nature of reality. But the collapse of the wave function is more or less a necessary consequence of the interpretation of the wave function as a probability distribution. If I have some states, some space, some coordinate system, and I plot on this coordinate system the squared magnitude of psi. This is related to our probability distribution with respect to position. If I then measure the position of the particle, what I'm going to get is, say I measure the particle to be here. Now, if I measure the position of the particle again immediately, I should get a number that's not too different than the number that I just got. And this is just sort of to make sure that if I repeat a measurement, it's consistent with itself, that I don't have particles jumping around truly randomly. If I know the position, I know the position. That's a reasonable assumption. What that means is that the new probability distribution for the position of the particle after the measurement is very sharply peaked about the position of the measurement. If this transition from a wave function, for instance, that has support here, to a wave function that has no support here, did not happen instantaneously, it's imaginable that if I tried to measure the particle's position twice in very rapid succession, that I would have one particle measured here and another particle measured here. Does that really mean I have one particle, or do I have two particles? These particles could be separated by quite a large distance in space, and my measurements could be not separated by very much in time, so I might be getting into problems with special relativity and the speed of light. And these sorts of considerations are what leads to the Copenhagen interpretation of quantum mechanics, which centers on this idea of wave functions as probability distributions and wave function collapse as part of the measurement process. Now, I mentioned operators in the context of expectation values. Operators are our second major concept in quantum mechanics. What about operators in the wave function? Well, operators, let's just write a general operator as q hat. Hats usually signify operators. Operators always act on something. You can never really have an operator in isolation. And what the operators act on is usually the wave function. We have a couple of operators that we've encountered, namely the position operator, x hat, which is defined as x times. And what's it multiplied by? Well, it's multiplied by the wave function. We also have the momentum operator, p hat, and that's equal to minus I h bar times the partial derivative with respect to x of what? Well, of the wave function. We also have the kinetic energy, which I'll write as ke hat. You could also write it as t hat. That operator is equal to minus h bar squared over 2m times the second derivative with respect to position of what? Well, of the wave function. And finally, we have h hat, the Hamiltonian, which is an expression of the total energy in the wave function. It's a combination of the kinetic energy operator here, which you can see, first of all, as p squared. We have a second derivative with respect to position at minus h bar squared. This is just p squared divided by 2m. P squared over 2m is a classical kinetic energy. The analogy is reasonably clear there. You add a potential energy term in here, and you get the Hamiltonian. Now, expectation values of operators like this are calculated as integrals. The expectation value of q, for instance, is the integral of psi star times q acting on psi over all space. This bears a striking resemblance to our expression, for instance, for the expectation of the position, which was the integral of just x times rho of x, where rho of x is now given by the absolute magnitude of psi squared, which is given by psi star times psi. Now, basically, the pattern here is you take your operator and you sandwich it between psi star and psi. And you can think about this position as being sandwiched between psi star and psi as well, because we're just multiplying by it. It doesn't really matter where I put it in the expression. The sandwich between psi star and psi of the operator is more significant when you have operators with derivatives in them. But I'm getting a little long-winded about this. Perhaps suffice it to say that operators in the wave function allow us to calculate meaningful physical quantities, like x, the expectation of position. This is more or less where we would expect to find the particle. Or the expectation of p, and I should be putting hats on these since technically they're operators. The expectation of p is more or less the expected value of the momentum, the sorts of momenta that the system can have. Or the expectation value of h, the typical energy the system has. And all of these are tied together in the context of uncertainty. For instance, if I wanted to calculate the uncertainty in the momentum, I can do that with the same sort of machinery we used when we were talking about probability, that I calculate the expectation of p squared and I subtract the expectation of p squared. So the expectation of the square minus the square of the expectations is directly related to the uncertainty. So that's a little bit about operators and a little bit about the wave function and a little bit about how they're used. Operators acting on the wave function calculating expectations in the context of the wave function being treated as a probability distribution. Now, where are we all going with this? We're going towards the Schrödinger equation. And the Schrödinger equation, to write it out, is I h bar partial derivative with respect to time of the wave function, and that's equal to minus h bar squared over 2m second partial derivative with respect to position of the wave function, plus some potential function of x, times the wave function. Now the wave function psi here, I've left it off as a function of position and time. So this is really the granddaddy of them all. This is the equation that we will be working with throughout Chapter 2. We will be writing this equation for various scenarios and solving it, and describing the properties of the solutions. So hopefully now you have a reasonable understanding of the wave function and enough understanding of operators to understand what to do with the wave function. The sorts of questions you can ask of the wave function are things like, what sorts of energy does this system have? How big is the spread in momenta? Where am I likely to find the particle if I went looking for it? But all of that relies on having the wave function, and you get the wave function by solving the Schrödinger equation. So that's where we're going with this. And that's all of the material for Chapter 1. And without further ado, moving on to the next lecture, we'll start solving the Schrödinger equation. We're going to move now into actually solving the Schrödinger equation. This is really the main meat of quantum mechanics. And in order to start tackling the Schrödinger equation, we need to know a little bit about how equations like the Schrödinger equation are solved in general. One of those solution techniques is separation of variables, and that's the solution technique that we're going to be applying repeatedly to the Schrödinger equation. First of all, though, let's talk a little bit about ordinary and partial differential equations. The Schrödinger equation is a partial differential equation, which means it's a good deal more difficult than an ordinary differential equation. But what does that actually mean? First of all, let's talk about ordinary differential equations. What an ordinary differential equation tells you is how specific coordinates change with time. At least that's most applications. So you have something like x as a function of time, y as a function of time, sorry, not y as a function of x, y as a function of time, z as a function of time. For example, the position of a projectile moving through the air could be determined by three functions, x, y, and z. If you're only working in 2 dimensions, for instance, let me drop the z, but we might have a velocity as well, say vx of t and vy of t. These 4 coordinates, position in 2 dimensions and velocity in 2 dimensions, fully specifies the state of a projectile moving in 2 dimensions. What an ordinary differential equation might look like to govern the motion of this projectile would be something like the following. dx dt is vx, dy dt is vy. Nothing terribly shocking there. The position coordinates change at a rate of change given by the velocity, while the velocities change, dvx dt
is given by, let's say, minus kvx, and dvy dt is minus kvy, sorry, kv subscript y now, kvy minus g. This tells you that, well, where I got these equations, this is effectively damped frictional motion in the plane xy, where gravity is pulling you down. So in the absence of any velocity, gravity leads to an acceleration in the negative y direction, and the rest of this system evolves accordingly. What that tells you, though, in the end, is the trajectory of the particle. If you launch it as a function of time, tick, 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 as the projectile moves through the air in, say, x, y space. Partial differential equations, on the other hand, PDEs, you have several independent variables. So where in an ordinary differential equation we only had time, and everything was a function of time, in a partial differential equation, what you're trying to solve for will have several independent variables. For example, the electric field, the vector electric field in particular, as a function of x, y, and z. The electric field has a value, both a magnitude and a direction, at every point in space, so x, y, and z potentially vary over the entire universe. Now you know how, excuse me, you know a few equations that pertain to the electric field that maybe you could use to solve to determine what the electric field is. One of these is Gauss's law, which we usually give an integral form. The integral of the electric field dotted with an area vector over a closed surface is equal to the charge enclosed by that surface over epsilon naught. Now hopefully you also know there is a differential form for Gauss's law, and it usually is written like this. This upside down delta is read as del, so you could say this is del dot E, and this is a vector differential operator. I'm going to skip the details of this because this is all electromagnetism, and if you go on to take advanced electromagnetism courses, you will learn about this in excruciating detail. Perhaps suffice to say here that most of the time when we're trying to solve equations like this, we don't work with the electric field, we work with the potential, let's call that V, and this system of equations here, if you treat the electric field as minus the gradient of the potential, gives you this equation gives you the Laplace equation. Del squared V equals rho over epsilon naught. What that actually writes out to, if you go through all of the vector algebra, is the second derivative of V with respect to x plus the second derivative of V with respect to y plus the second derivative of V with respect to z, and I've left off all my squareds in the denominator here, is equal to rho over epsilon naught. This is a partial differential equation, and if we had some machinery for solving partial differential equations, we would be able to determine the potential at every point in space. And that would then allow us to determine the electric field at every point in space. This is just an example. Hopefully you're familiar with some of the terms I'm using here. The main solution technique that is used for partial differential equations is separation of variables. And separation of variables is fundamentally a guess. Suppose we want to find some function. In the case of electromagnetism, it's the potential x, y, and z. The potential is a function of x, y, and z. Let's make a guess that v of x, y, and z can be written as x of x times y of y times z of z. So instead of having one function of three variables, we have the product of three functions of one variable each. Does this guess work? Well, it's astonishing how often this guess actually does work. This is a very restrictive sort of thing, but under many realistic circumstances, this actually tells you a lot about the solution. For example, the wave equation. The wave equation is what you get mathematically if you think about, say, having a string stretched between two solid objects.
Now, under those circumstances, if you zoom in on, if you say, pluck the string, you know it's going to vibrate up and down. Mathematically speaking, if you zoom in on a portion of that string, say it looks like this, you know the center of this string is going to be accelerating downwards. And the reason it's going to accelerate downwards is because there's tension in the string, and the tension force pulls that direction on that side and that direction on that side. So it's being pulled to the right and pulled to the left, and the net force then ends up being in the downward direction. If the string curved the other direction, you would have effectively a net force pulling up and to the right, and a net force pulling up into, or a force pulling up into the right, a force pulling up into the left, and your net force would be up. This tells you about forces in terms of curvatures, and that thought leads directly to the wave equation. The acceleration, as a result of the force, is related to the curvature of the string. And how we express that mathematically is with derivatives. The acceleration is the second derivative of the position. So if we have the position of this string is u as a function of position and time, then the acceleration of the string at a given point and at a given time is going to be equal to some constant, traditionally written c squared, times the curvature, which is the second derivative of u with respect to x. Again, u being a function of position and time. So this is the wave equation. I should probably put a box around this, because the wave equation shows up a lot in physics. This is an important one to know. But let's proceed with separation of variables. U, as a function of position and time, is going to be x, a function of, not time, x a function of position, and t a function of time. So capital X and capital T are functions of a single variable each, and their product is what we're guessing will reproduce the behavior of u. So if I substitute this u into this equation, what I end up with is the second derivative of x, t of t, with respect to time, equals c squared times the second derivative of x, t of t, with respect to position. So this hasn't really gotten us anywhere yet, but what you notice here is we have derivatives with respect to time, and then we have this function of position. Since these are partial derivatives, they're derivatives taken with everything else other than the variable that you're concerned with held constant, which means this part here, which is only a function of position, can be treated as a constant and taken outside of the derivative. The same sort of thing happens here. We have second derivatives, partial second derivatives with respect to position, and here we have only a function of time, effectively a constant for this partial derivative, which means we can pull things out. And what we've got then is capital X. I'm going to drop the parentheses x, because you know capital X is a function of lowercase x. So you've got big X, second partial derivative with respect to time of big T, equals c squared, big T, second partial derivative of big X with respect to x. That's nice, because you can see we're starting to actually be able to pull x and t out here. And the next step is to divide both sides of this equation by xt, by basically dividing through by u. In order for this to work, we need to know that our solution is non-trivial, meaning if x and t are everywhere 0, dividing through by this will do bad things to this equation. But what you're left with after you divide by this is 1 over t, second partial of t, big T with respect to little t, and c squared 1 over big X, second partial of big X with respect to little x. This is fully separated. What that means is that the left-hand side here is a function only of t. And the right-hand side is a function only of x. That's very interesting. Suppose I write this function of t as, say, f of t. This part, let's call that g of x. I have two different functions of t and x. Normally you would say, oh, I have f of t and I have g of x, and I know what those forms are. I could, in principle, solve for t as a function of x. But that isn't what you're going to do, and the reason that's not the case is that this is a partial differential equation. Both x and t are independent variables. All of this analysis, in order for separation of variables to work, must hold at every point in space, at every x and at every time. So suppose this relationship held for a certain value of t and for a certain value of x. I ought to be able to change x and have the relationship still hold. So if I change x without changing t, the left-hand side of the equation isn't changing. If changing x led to a change in g of x, then my relationship wouldn't hold anymore. So effectively what this means is that g of x is a constant. In order for this relationship to hold, both f of t and g of x have to be constant. Essentially, what this is saying in the context of the partial differential equation is that if we look at the x part here, when I change the position, any change in the second derivative of the position function is mimicked by this 1 over x, such that the overall function ends up being a constant. That's nice, because that means I actually have two separate equations. F of t is a constant and g of x is a constant. What these equations actually look like. This was my f of x, and this was my f of t, and this was my g of x. That constant, which I've called a here, and the notation is arbitrary, though you can in principle save yourself some time by thinking ahead and figuring out what might be a reasonable value for a. What's especially nice about these is that this equation is now only an ordinary differential equation. Since big T is only a function of little t, we just have a function of a single variable. We only have a single variable here. We don't need to worry about what variables are being held constant and what variables aren't being held constant. So we can write this as total derivative with d instead of partial derivative with the partial derivative symbol. So we've reduced our partial differential equation into two ordinary differential equations. This is wonderful. And we can rearrange these things to make them a little more recognizable. You've got d squared t dt squared equals a t, and c squared d squared big X d little x squared equals a times big X, multiplying through by big T in this equation and big X in this equation. And these are equations that you should know how to solve. If not, you can go back to your ordinary differential equations books, and solution to ordinary differential equations like this are very commonly studied. In this case, we're taking the second derivative of something and we're getting the something back with a constant out front. Anytime you take the derivative of something and get itself, or itself times a constant, you should think exponentials. And in this case, the solution is t equals e to the square root of a times time. If you take the second derivative of this, you'll get two square roots of a factors that come down, e times e to the root at, which is just big T. You can, in principle, also have a normalization constant out front. And you end up with the same sort of thing for x. Big X is going to be e to the square root of a over c x, with, again, in principle, a normalization constant out front. What that means is, if I move things up a little bit, get myself some space, u of x and t, what we originally wanted to find, is now going to be the product of these two functions. So I have a normalization constant in front, then I have e times root a t, and e times root a over c x. Now, if this doesn't look like a wave, and that surprises you because I told you this was the wave equation, it's because we have, in principle, some freedom for what we want to choose for our normalization constant and for what we want to choose for our separation constant, this constant A. And the value of that constant will in principle be determined by the boundary conditions. A and A are determined by boundary conditions. The consideration of boundary conditions and initial conditions in partial differential equations is subtle, and I don't have a lot of time to fully explain it here. But if what you're concerned with is why this doesn't look like a wave equation, what actually happens when you plug in to your initial conditions and your boundary conditions to find your normalization constants and your actual value for the separation constant, you'll find that A is complex. And when you substitute in the complex value for A into these expressions, you'll end up with e to the I omega t sort of behavior, which is going to give you effectively cosine of omega t, up to some phase shifts as determined by your normalization constant and your initial conditions. So this is how we actually solve a partial differential equation. The wave equation in particular separates easily into these two ordinary differential equations, which have solutions that you can go and look up pretty much anywhere you want. Finding the actual value of the constants that match this general solution to the specific circumstances you're concerned with can be a little tricky, but in the case of the wave equation, if what you want is, say, a traveling wave solution, you can find it. There are appropriate constants that produce traveling waves in this expression. So, to check your understanding, what I'd like you to do is go through that exercise again, performing separation of variables to convert this equation into, again, two ordinary differential equations. This equation is called the heat equation, and it's related to the diffusion of heat throughout a material. If you have, say, a hot spot and you want to know how that hot spot will spread out with time. Since this is a quantum mechanics course, let's move on to the time-dependent Schrödinger equation. This is the full Schrödinger equation in all of its glory, except I've just written it in terms of the Hamiltonian operator now. H hat is the Hamiltonian. The Hamiltonian is related to the total energy. I evidently can't spell total energy of the system. Meaning it's, kinetic energy plus potential. And we have a kinetic energy operator, and we have, we will soon have a potential energy operator. What H hat actually looks like is it's the kinetic energy operator, which, if you recall correctly, is minus h bar squared over 2m times the second derivative with respect to position. And the potential energy operator is just it looks a lot like the position operator. It's just multiplying by some potential function, which here I'll consider to be a function of x. Now this is an operator, which means it acts on something, so I need to substitute in a wave function here. And when you do that in the context of the Schrödinger equation, you end up with the form that we've seen before. I h bar d psi dt equals minus h bar squared over 2m d squared psi dx squared plus v of x psi. So that's our Schrödinger equation. How can we apply separation of variables to this? Well, we make the same sort of guess as we made before. Namely, psi is going to be xt, where big X is a function of position and big T is a function of time. If I substitute psi equals xt into this equation, you get pretty much what you would expect. I h bar. Now, when I substitute xt in here, big X, big T, big X is a function only of position, so I don't need to worry about the time derivative acting on big X. So I can pull big X out, and what I'm left with then is a time derivative of big T. This is then going to be equal to minus h bar squared over 2m times the same thing. When I substitute xt in here, the second derivative with respect to position is not going to act on the time part. So I can pull the time part out. T, second derivative of big X with respect to position. And substituting an xt here doesn't really do anything. There's no derivatives here, so this is not a particularly interesting term. So we were getting v x t. All right. Now the next step in separation of variables is to divide through by your solution, xt, assuming it's not 0, that's okay. And you end up with I h bar 1 over big X, 1 over big T, canceling out the X, and you're just left with big T, 1 over T, partial of T dt. And then on the right-hand side, we have minus h bar over 2m, h bar squared over 2m, 1 over big X, second partial of X with respect to position, plus V. X and T are fully canceled out in this term. Now, as before, this is a function of time only, and this is a function of space only, which means both of these functions have to be constant. And in this case, the constant we're going to use is E. And you'll see why once we get into talking about the energy in the context of the wave function. So we have our two equations. One, I h bar over t, first partial derivative of big T with respect to time, is equal to E. And on the right-hand side, from the right-hand side, we get minus h bar squared over 2m, 1 over big X, second partial of big X, with respect to position, plus V is equal to the energy. So these are our two equations. Now, I've written these with partial derivatives, but since, as I said before, these functions, big T and big X, are only functions of a single variable, there's effectively no reason to use partial derivative symbols. I could use d's instead of partials. Essentially, there's no difference if you only have a function of a single variable, whether you take the partial derivative or the total derivative. So, let's take these equations one by one. The first one, the time part. This we can simplify by multiplying through by big T, as before, and you end up with I h bar d big T dt equals E times T. Taking the derivative of something and getting it back, multiplied by a constant, again should suggest two exponentials. Let me move this I h bar to the other side. So we would have divided by I h bar, and 1 divided by I is minus I. So I'm going to erase this from here and say minus I in the numerator. So first derivative with respect to time of our function gives us our function back with this out front. Immediately this suggests exponentials, and indeed our general solution to this equation is some normalization constant times e to the minus I e over h bar times time. So if we know what this separation constant, capital E, is, we know the time part of the evolution of our wave function. This is good. What this tells us is that our time evolution is actually quite simple. It's in principle a complex number. T is, in principle, a complex number. It has constant magnitude. Time evolving this doesn't change the absolute value of capital T. And essentially it's just rotating about the origin in the complex plane. So if this is my complex plane, real axis, imaginary axis, wherever capital T starts, as time evolves, it just rotates around and around and around and around in the complex plane. So the time evolution that we'll be working with, for the most part, in quantum mechanics is quite simple. The space part of this equation is a little more complicated. All I'm going to be able to do now is rearrange it a little bit by multiplying through by capital X, just to get things on top, and change the order of terms a little bit to make it a little more recognizable. Minus h bar squared over 2m, second derivative of capital X with respect to position, plus v times capital X is equal to e times capital X. And this is all the better we can do. We can't solve this equation because we don't know what v is yet. V is where the physics enters this equation and where the wave function from one scenario differs from the wave function for another scenario. Essentially, the potential is where you encode the environment into the Schrodinger equation. Now, if you remember back a ways, when we were talking about the Schrodinger equation on the very first slide of this lecture, what we had was the Hamiltonian operator acting on the wave function. And this is that same Hamiltonian. This is h hat, not acting on psi now, just acting on x. So you can also express the Schrodinger equation as h times x equals e times x. The Hamiltonian operator acting on your spatial part is the energy of, is the separation constant E, which is related to the energy, times the spatial part. So this is another expression of the Schrodinger equation. This equation itself is called the time-independent Schrodinger equation, or TISE if I ever use that abbreviation. And this is really the hard part of any quantum mechanics problem. To summarize what we've said so far, starting with the Schrodinger equation, which is this: time derivatives with complex parts in terms of Hamiltonians and wave functions gives you this, substituting in the actual definition of the Hamiltonian, including a potential v. And applying separation of variables gets us this pair of ordinary differential equations. The time part here gave us numbers that just basically spun around in the complex plane. Not the imaginary part. This is traditionally the real part, and this is the imaginary part. So the time evolution is basically rotation in the complex plane. And the spatial part, well, we have to solve this equation being the time-independent Schrodinger equation. We have to solve this for a given potential. The last comment I want to make in this lecture is a comment about notation. My notation is admittedly sloppy, and if you read through the chapter, Griffiths calls my notation sloppy. In Griffiths, since it has the luxury of being a book and not the handicap of having my messy handwriting, they use capital psi to denote the function of x and time. And when they do separation of variables, they re-express this as lowercase psi as a function of position and lowercase phi as a function of time. So for this, I used capital X. Sorry, I should put things in the same order. I used capital T of t and capital X of x, because I have a better time distinguishing my capital letters from my lowercase letters than trying to, well, you saw how long it took me to write that symbol. I'm not very good at writing capital psis. There is a lot of sloppiness in the notation in quantum mechanics, namely because, oops, geez, I have two functions of time. This is Griffiths' function of position. Sorry about that. This here and this here, these are really the interesting parts, the functions of position, the solutions to the time-independent Schrodinger equation. What that gives us, well, what that means is that a lot of people are sloppy with what they call the wave function. This is the wave function. This is the spatial part, or the solution to the time-independent Schrodinger equation. This is not the wave function. But, I mean, I've already made this sloppy mistake a couple of times in problems that I've given to you guys in class. Namely, I'll ignore the time domain part and just focus on the spatial part, since that's the only interesting part. So, perhaps that's my mistake. Perhaps I need to relearn my handwriting. But, at any rate, be aware that sometimes I, or perhaps even Griffiths, or whoever you are talking to, will use the term the wave function when they don't actually intend to include the time dependence.
And the time dependence is, in some sense, easy to add on because it's just this rotation in complex number space. But hopefully things will be clear from the context what is actually meant by the wave function. So we're still moving toward solutions to the Schrödinger equation. And the topic of this lecture is what you get from separation of variables and the sorts of properties it has. To recap what we talked about last time, the Schrödinger equation, I h bar partial derivative of psi with respect to time is equal to minus h bar squared over 2m second partial derivative of psi with respect to position plus v times psi, where this is essentially the kinetic energy and this is the potential energy as part of the Hamiltonian operator. We were able to make some progress towards solving this equation by writing psi, which is in principle a function of position and time, as some function of position multiplied by some function of time. Why did we do this? Well, it makes things easier. We can make some sort of progress, but haven't we restricted our solution a lot by writing it this way? Well, really we have, but it does make things easier, and it turns out that these solutions that are written as products that result from solving the ordinary differential equations you get from separation of variables with the Schrödinger equation can actually be used to construct everything that you could possibly want to know. So let's take a look at the properties of these separated solutions. First of all, these solutions are called stationary states. What we've got is psi as a function of position and time is equal to some function of position multiplied by some function of time. And I wrote that as capital T on the last slide, but if you remember from the previous lecture, the time evolution equation was solvable, and what it gave us was a simple exponential, e to the, I times e times t divided by h bar. So this is our time evolution part, and this is our spatial part. What does it mean for these states to be stationary? Well, consider, for instance, the probability density for the outcome of position measurements. Hopefully you remember this is equal to the squared absolute magnitude of psi, which is equal to the complex conjugate of psi times psi. Now if I plug this in for psi and its complex conjugate, I end up with the complex conjugate of big X as a function of position times the complex conjugate of this. And the only part that's complex about this is the I here in the exponent, so we need to flip the sign on that. And we'll have e to the I, positive I now, e t over h bar. That's for the complex conjugate of psi. And for the psi itself, well, x of x e to the minus I e t over h bar. Now, multiplying these things together, there's nothing special about the multiplication here, and this are complex conjugates of each other, so they multiply together to give the magnitude of, the squared magnitude of each of these numbers together, which, since these are just complex exponentials, is magnitude 1. So what we end up with here is x star x, essentially the squared magnitude of just the spatial part of the wave function. There's now no time dependence here, which means the probability density here does not change as time evolves. So that's one interpretation of these, or one meaning of these things being called stationary states. The fact that I can write a wave function as a product like this, and the only time dependence here comes in a simple complex exponential, means that that time dependence drops out when I find the probability distribution. Another interpretation of these things as stationary states comes from considering expectation values. Suppose I want to calculate the expectation value of some generic operator, capital Q. The expression for the expectation of an operator is an integral of the wave function
times the operator acting on the wave function. So complex conjugate wave function, operator, wave function. Now I'm going to go straight to the wave function as expressed in terms of x and t parts. So complex conjugate of the spatial part times the complex conjugate of the time part, which from the last slide is e to the plus I e t over h bar. Our operator gets sandwiched in between the complex conjugate of the wave function and the wave function itself. So this is again, no stars anymore, come on Brent, just x and then e to the minus I e t over h bar. And this is all integrated dx. So this is psi star, and this is psi. And this is our operator sandwiched between them, as in the expression for the expectation. Now, provided this operator does not act on time, it doesn't have anything to do with the time coordinate, and that will be true for basically all of the operators we will encounter in this course, has no time derivatives. What that means is that I can push this time part past the operator. The operator will not act on the time part, so that's okay. And what that means is, as before, these two guys will just end up directly multiplied by each other, and you will end up with just 1 as a result. Integral of x star q hat x dx will be what results. Again, the time part drops out if, q has no partial time derivatives, which is true for basically all of the operators we'll meet. Position, x hat, that's just multiplying by x. Momentum, that has to do with differentiation with x. And then kinetic energy, that again has second derivatives with respect to position. There's no time derivatives in any of these physical sorts of operators that we'll be talking about here. What that means is that, again, the time dependence drops out, and the expectation value of this q operator, and q can be anything here, again, has no time dependence. So our expectation values are constant. If our physical system is described by a wave function that separates like this, then our expectation values have no time dependence. The next topic I'd like to address is the energy of a stationary state, which also happens to have a very nice expression. The spatial part of the Schrödinger equation that resulted from our separation of variables was something I call the time-independent Schrödinger equation. The time-independent Schrödinger equation, which could be written simply as the Hamiltonian operator acting on the spatial part of the wave function was equal to the separation constant times the spatial part of the wave function. H times x equals e times x, where h is now an operator, so I shouldn't say time. I should say the Hamiltonian operator acting on x is equal to the separation constant e time just multiplied by the spatial part of the wave function. So suppose I want to calculate the expectation of the Hamiltonian operator. Now the Hamiltonian operator, is related to the energy of the system, so if I calculate an expectation here, it should have something to do with the energy of the system. It's not immediately obvious that h acting on the wave function gives you the energy multiplied by the wave function, but calculating an expectation value like this makes the connection much stronger. So let's write out that expression. We have an integral, and then we have the wave function itself, x star e to the I times the energy times the time over h bar times our Hamiltonian, and then the non-complex conjugated wave function itself, e to the minus I e t over h bar, integral dx. Now we know the Hamiltonian operator, that has partial derivatives with respect to x and multiplication by the potential. So again, this operator isn't going to have any time dependence, same as what we reasoned when we were calculating expectation values. These time dependences drop out for the same reason here as they did in the previous slide in general. We're just left then with the integral of x star h hat x integrated dx. But I know this. That's this. So I can make that substitution. Knowing this spatial part of the wave function solves the time-independent Schrodinger equation allows me to simplify this. I just end up with the integral x star e x integrated dx. Now these x's are not coordinates, they're functions of the x coordinate, just to be clear about my notation. But this e now, that's just a constant. It can be pulled out of the integral entirely, and we're just left with e times the integral of x star x, should make it clear these are capitals, dx. And this, if we've properly normalized our wave function, is 1. So what that tells us is that the expectation of the Hamiltonian operator is our separation constant, E, that we got when we applied separation of variables to the time-dependent Schrodinger equation. The Hamiltonian operator is something we expect to be related to the energy, so it's reasonable to identify the separation constant E with the energy associated with this particular state. So now what this tells us is that the energy of the wave function, the expectation of our Hamiltonian is the energy of the wave function. Now we know there's some uncertainty in quantum mechanics, so is there uncertainty in our energy? If we actually measure the energy of our wave function, do we ever get E, the separation constant? Well, in order to calculate the uncertainty in something, we need to calculate effectively the standard deviation or the variance. Let's write it as the variance, the squared sigma sub E. Or E perhaps now refers to the energy. So let me write this as sigma sub h hat. If we want to calculate this, what we have to calculate, well, sigma sub h hat squared, that's equal to the expectation value of h squared minus the expectation value of h quantity squared, the expectation squared. This expectation of the square minus the square of the expectation. Hopefully you remember that back from when we talked about variance. Now, if I write out this expression, now I just calculated this was equal to E. So this term here is just going to give us E squared. This term is going to give us E squared. So that's easy enough. Let's work with this term then, the expectation of the Hamiltonian squared. This is again going to be an integral, and I'll drop the time-dependent parts here. Actually, you know what? I'll drop all of this. We don't need to actually express everything as an integral. You know what's going to happen in this integral. The expectation of any operator is the integral of psi star times the operator times psi, integrated over the domain, in this case x. So if I substitute the Hamiltonian squared into this, in the context of the discussion we've had over the last few minutes about how the time dependence drops out, what we're effectively going to end up with, needing to consider, is this. And this is going to end up looking like h hat squared times just the spatial part, x. Now h hat squared times the spatial part x, well that's h hat times h hat acting on h hat acting on x. It's the definition of squaring an operator. You just apply the operator twice. Now, as before, I know this. This is E times x, since I know x satisfies the time-independent Schrodinger equation. So this is going to be h acting on E x. There's nothing special about E, it's just a number, so I can pull it out. The Hamiltonian operator won't do anything to that number. And I'll just be left with E and h hat acting on x. Well, again, h hat acting on x, that's E times x. So I'm going to end up with E squared times x. Now back in the integral equation, this E squared, just being a constant, can be pulled out front. And what we would end up with is E squared times the integral of x star x dx. And again, if we've properly normalized this, this will just be 1, and we'll end up with e squared. So, this is interesting. What we got for our expectation of Hamiltonian squared was e squared. So what this tells us is that sigma sub h hat squared, our variance, or our squared uncertainty in the energy of the system, is equal to e squared from this term minus e squared from this term, which is 0. Stationary states like this that solve the time-independent Schrödinger equation have energy given by the separation constant E and no uncertainty in energy. They essentially have exactly E amount of energy. What exactly does that mean? Well, we'll talk about that in a moment. Just to summarize things, for these stationary states, the probability density has no time dependence. The time-dependent part cancels itself out when you're calculating the probability density. Expectation values of any operator that we're going to be concerned with in this class also have no time dependence. And the energy is specified exactly that separation constant E in, for instance, the time-independent Schrödinger equation h hat x equals E x. This is our energy. That's nice. It has some physical significance. But there's not going to be no uncertainty in energy. These states have defined energy, and it's exact, which means if we measured the energy of the system, we would always get the same thing. Now, just to comment very briefly on what that actually means. What does it mean for a system to have no energy uncertainty? If you remember back when I talked about the difference between quantum physics and classical physics and where the boundary between classical and quantum physics fell, well, I gave you an energy-time uncertainty relation where the uncertainty in the energy and the uncertainty in the time always had to be greater than about h bar over 2. Now, what does that mean if we have no energy uncertainty? Well, delta E is 0. So 0 times something, it has to be greater than h bar. Now, h bar is really small, but h bar is not 0, so there's mathematically some problem here. And what actually happens is that delta T has to be infinity. What does that mean? Why is that a meaningful statement? Well, essentially, this delta T here in the energy-time uncertainty relationship tells you about when the state exists, the duration of the process. Essentially, it's the answer to the question, how accurately can you tell me when this state exists? And for something like a stationary state, it always exists. There's no time dependence. You could run the clock backwards, you could run the clock forwards, all the way before the beginning of the universe, technically, since none of that beginning of the universe stuff is covered in this course. Essentially, this state always exists. So the answer to the question when, well, always, whenever you want, forever, however you want to put it. Essentially, these stationary states always exist. They have no time dependence, and they're constant forever. Now, that's not the most realistic state in the world, but they are the sorts of things that we get from the Schrödinger equation, and they actually have some really, really nice mathematical properties that we'll start talking about in the next lecture and in the lectures after that. But that's a stationary state for you. It's a result of the solution to the time-independent Schrödinger equation, possibly with the time independence added back on, depending on how sloppy I'm being with my notation at any given moment. Stationary states are really important, and they have some very nice mathematical properties. To preview a little bit, if you know the stationary states of your system, you know everything about the system, and you can find the answer to any question you might possibly ask about the quantum mechanical behavior of your system. Now, we talked about how the Schrödinger equation can be split by separation of variables into a time-independent Schrödinger equation and a relatively simple time-dependent part. What that gave us is, provided we have solutions to that time-independent Schrödinger equation, we have something called a stationary state. And it's called a stationary state because nothing ever changes. The probability densities are constant, the expectation values are constant in the state effectively, since it has a precise, exact, no uncertainty energy, has to live for an infinite amount of time. That doesn't sound particularly useful. From the perspective of physics, we're often interested in how things interact and how things change with time. So how do we get things that actually change with time in a non-trivial way? Well, it turns out that these stationary states, while their time dependence is trivial, the interaction of their time dependence when added together in a superposition is not trivial. And that's where the interesting time dynamics of quantum mechanics comes from. Superpositions of stationary states. Now we can make superpositions of stationary states because of one fundamental fact, and that fact is the linearity of the Schrödinger equation. So the Schrödinger equation, as you hopefully remember it by now, is I h bar partial derivative of psi with respect to time is equal to minus h bar squared over 2m second derivative of psi with respect to x, and that's a really ugly psi. Must fix. Second derivative of psi with respect to position plus v times psi. So this is our Hamiltonian operator applied to the wave function, and this is our time dependence part. Now, in order for an equation to be linear, what that means is that if psi solves the equation, psi plus some other psi that also solves the equation will solve the equation. So if, say, let's call it A, solves the Schrödinger equation, and B solves the Schrödinger equation, and let me write this out in a little more detail. First of all, I'm talking about A is a function of position and time, as is B. If A and B both solve the Schrödinger equation, then A plus B must also solve the Schrödinger equation. And we can see that pretty easily. Let's substitute psi equals A plus B into this equation. The first step, I h bar partial derivative with respect to time of A plus B is equal to minus h bar squared over 2m second partial derivative with respect to space of A plus B plus the potential V times A plus B. Now the partial derivative of the sum is the sum of the partial derivatives. That goes for the second partial derivative as well. And well, this is just the product of the potential with the sum is the sum of the product of the potential with whatever you're multiplying out. I'm going to squeeze things a little bit more here. So I can write that out. I h bar d by dt of A plus I h bar dB dt equals minus h bar squared over 2m second derivative of A with respect to space. Forgot my squared on the second derivative, minus h bar squared over 2m second derivative of B with respect to position, plus V times A plus V times B. That's just following those fundamental rules. Now, you can probably see where this is going. This, and this. These three terms together make up the Schrödinger equation, the time-dependent Schrödinger equation for A. For A. For A. And this, and this altogether, that's the time-dependent Schrödinger equation for B. So if A satisfies the time-dependent Schrödinger equation, which is what we supposed when we got started here, then this term, and this term will cancel out. They will obey the equality. Likewise, for the parts with B in them. So essentially, if A solves the Schrödinger equation and B solves the Schrödinger equation, A plus B also solves the Schrödinger equation. And the reason for that is the partial derivatives here. The partial derivative of the sum is the sum of the partials, and the product with the sum is the sum with the products. These are linear operations, so we have a linear partial differential equation. And the linearity of the partial differential equation means, well, essentially that if A solves and B solves, then A plus B will also solve it. That allows us to construct solutions that are surprisingly complicated. And actually, the general solution to the Schrodinger equation is psi of position and time is equal to the sum, and I'm going to be vague about the sum here. You're summing over some index j, x sub j, as a function of position. These are solutions now to the time-independent Schrodinger equation, the spatial part of the Schrodinger equation, times your time part. And we know the time part from the, well, from when we discussed the separation of variables, is minus I, e, now this is going to be e sub j, t, over h bar. So this is a general expression that says we're summing up a whole bunch of stationary state solutions to the time-independent Schrodinger equation. And we're getting psi. Now, I've left something out, and what I've left out is quite important here. We need some constant, c sub j, that tells us how much of each of these stationary states to add in. So this is actually, well, it's going to be a solution to the Schrodinger equation since it's constructed from solutions to the Schrodinger equation. And this is completely general. That's a little surprising. What that means is that this can be used to express not just a subset of solutions to the Schrodinger equation, but all possible solutions to the Schrodinger equation. All the solutions to the Schrodinger equation can be written like this. That's a remarkable fact. And it's certainly not guaranteed. You can't just write down any old partial differential equation, apply separation of variables, and expect the solutions that you get to be completely general and superposable to make any solution you could possibly want. The reason this works for the Schrodinger equation is because the Schrodinger equation is, well, just to drop some mathematical terms if you're interested in looking up information later on, the Schrodinger equation is an instance of what's called a Sturm-Liouville problem. Sturm-Liouville problems are a class of linear operator equations, for instance, partial differential equations or ordinary differential equations, that have a lot of really nice properties. And this is one of them. So the fact that the Schrodinger equation is a Sturm-Liouville equation, or the fact that the time-independent Schrodinger equation is a Sturm-Liouville equation, means that this will work. So if you go on to study, advanced mathematical analysis methods in physics, you'll learn about this. But for now, you just need to sort of take it on faith that general solutions to the Schrodinger equation look like this. Superpositions of stationary states. So if we can superpose stationary states, what does that actually get us? One example I would like to do here is, and this is just an example of the sorts of analysis you can do given superpositions of stationary states, is to consider the energy. Suppose I have two solutions to the time-independent Schrodinger equation, which I'm just going to write as h hat x1 equals e1 x1, and h hat x2 equals e2 x2. So x1 and x2 are solutions to the time-independent Schrodinger equation, and they're distinct solutions. e1 not equal to e2. I'm going to use these to construct a wave function, let's say psi, of x, and at time t equals 0, let's say it looks like this. c1 times x1 as a function of position plus c2 x2, which is a function of position. Now, at some time later, we can add on our time dependence factors, knowing what the time dependence factors look like. What that means is that psi of x and some general time, each of these spatial parts needs some time part to be inserted. So c1 x1 and then e to the minus I e1 t over h bar plus c2 x2 e to the minus I e2 t over h bar. So these complex exponential time dependencies come from the time part from our separation of variables. You can think of them as being here as well, just with time t equals 0, which makes both of these factors to be equal to 1. So if this is our wave function, let's consider the energy. In particular, let's consider the expectation value of the Hamiltonian operator. What does that look like? Well, the expectation value is going to be psi star h hat psi integrated dx, and I can substitute in this expression for psi. So I'm going to get an integral of c1 x1 star, taking complex conjugates, e to the I e1 t over h bar. Now I've got a plus sign because I took the complex conjugate, plus c2 x2 star e to the I e2t over h bar. Again, plus sign here because of taking the complex conjugate. Then your operator, and then just psi itself. So c1 x1 e to the minus I e1 t over h bar, so h bar, plus c2 x2 e to the minus I e2 t over h bar. This is all integrated dx. Now, I know what the Hamiltonian does to these time dependence parts, nothing. And I know what the Hamiltonian does to these spatial parts, since, by construction, they're solutions to the time-independent Schrödinger equation. So I can apply the operator to this expression for the wave function. And when you do that, you get c1 x, should be writing my x's bigger here, c1 x1 star e to the I e1 t over h bar. I'm just copying this expression over, plus c2 x2 star e to the I e2 t over h bar. And now after I've applied the operator to this, I get c1 e1 x1 e to the minus I e1 t over h bar. And this is just substituting e1 x1 for h hat x1, plus the same sort of term for the second part, c2 e2 x2 e to the minus I e2 t over h bar. Still integrated dx. Now, what do we actually get here? Well, as before, some of these terms are simpler than others. These two terms, when we expand out, distribute this expression, will end up with positive and negative e to the I e1t, e to the minus I e1t multiplied together is going to give us 1. Same thing is going to happen for these two terms when I multiply them together. Now I'm also going to have terms where I have, like this term, where I have e2 and e1 together. e2 and e1 mixed together like that. What I actually get is, expanding this out. Forgot what my slide said for a moment there, sorry about that. This term, the time dependence is going to go away. This term, the time dependence is going to go away. But the cross terms here, those two terms, the time dependence is not going to go away because you have e1 mixed with e2 and e2 mixed with e1. So what you get, expanding that out, is, as before, integral and c1 squared x1 star x1 times e1 with no time dependence. That's what you get from the orange terms here. c1 squared x1 star x1, and then the time dependences drop out, and we have the constant E1 also. From the blue terms here, we get C2 squared, x2 star, x2, E2, for the same sorts of reasons. Now, our cross terms, plus C1, C2, x1 star, x2, and then we have, in this case, an E2, and we have some time dependence. E to the I, E1 minus E2, T over H bar. Our other cross term looks quite similar, plus C1, C2, X2 star, X1, E1, E to the I, E2 minus E1, T over H bar. And this is all integrated dx, as before. Now, these integrals actually have some nice features. First of all, this first integral here, the first term in this integral, C1, that's a constant, E1, that's a constant, so I can pull those out, and I'm left with the integral of x1 star x1. If x1 is properly normalized, that integral is going to be 1. So we get C1 squared E1 for this first term. The second term here gives us something that looks very similar, C2 squared E2, since the integral of x2 star x2 is unity, provided we properly normalize things. Now, we're actually done. We'll talk more about this in detail later, but the integral of x1 star x2 is actually going to be 0. Everything else here, C1, C2, E2, and this time-dependent part, is a constant when we're considering an integral over x. So we're just going to be left with the integral of x1 star x2 dx. And this is a general feature of Sturm-Liouville problems. When you have distinct solutions like this, x1 and x2, the integral of their product is 0. Likewise, for x2 star x1 dx equals 0. We'll see a specific example of this in the next lectures when we're talking about the particle in a box. This is connected with Fourier analysis and Fourier series. But for now, you can think of it just as a quirk of the nice features of equations like the Schrödinger equation, that you get solutions that split up like this, where your cross terms in integrals like this vanish. So essentially what that tells us is that the expectation of the Hamiltonian is C1 squared E1 plus C2 squared E2. The energies of the states multiply together. In order to check your understanding of this, what I'd like to do is have you follow through similar sorts of analysis, given this wave function, write down in your notebook where the time dependence comes in, and write an expression for the probability distribution as a function of time. And what you need to do to really check your understanding is explain in your own words why this has non-trivial time dependence. That's not an easy question, but the non-trivial time dependence comes from the superposition. The question for you is why and how that superposition results in non-trivial time dependence. So, to summarize, classic problems in quantum mechanics, really they all start with some physical system. For instance, a box with a particle inside it. Now, what happens next depends on what exactly this situation is, but typically in quantum mechanics you will write down a potential, V of x, in the case of one-dimensional quantum mechanics. Knowing that potential will allow you to write down the time-independent Schrödinger equation. That was what we got from separation of variables. So, solving the time-independent Schrödinger equation gives you the stationary states, and it also gives you the energies of those stationary states. That's telling you not x of t, it's telling you x of x and e to the minus I e t over h bar. It's telling you what the stationary state looks like. The next step, and we'll talk about this in great detail, is the expression of the initial conditions of the system as a sum of stationary states. Now, you know superpositions are also going to be superpositions of stationary states are also going to be solutions to the Schrodinger equation. So if you can express your initial conditions as a superposition of those stationary states, you're great. You're good. The final step is to add the time dependence to each stationary state. Knowing x of x, this is the time dependence I'm referring to. You need to know the energy, but you got that. Then, basically what you have is that psi of x and t is equal to that sum over j of x sub j. Oops, sorry, I've forgotten again my constant out front. C sub j, x sub j of x, e to the minus I, e sub j, t over h bar. This is your general solution. You've properly chosen your c sub j's such that you solve your initial conditions. You're guaranteed to solve the Schrodinger equation because you're expressing things as a superposition of stationary states. And this general wave function is then something that you can use to answer meaningful physical questions. Quantum mechanics is really all about solving the Schrodinger equation. That's a bit of an oversimplification, though, because if there was only one Schrodinger equation, we could just solve it and be done with it, and that would be it for quantum mechanics. The reason this is difficult is that the Schrodinger equation isn't just the Schrodinger equation. There are many Schrodinger equations. Each physical scenario for which you want to apply quantum mechanics has its own Schrodinger equation. They're all slightly different, and they all require slightly different solution techniques. The reason there are many different Schrodinger equations is that the situation under which you want to solve the Schrodinger equation enters the Schrodinger equation as a potential function. So let's talk about potential functions and how they influence, well, the physics of quantum mechanics. First of all, where does potential appear in the Schrodinger equation? This is the time-dependent Schrodinger equation, and the right-hand side here, you know, is giving the Hamiltonian operator acting on the wave function. Now, the Hamiltonian is related to the total energy of the system, and you can see that by looking at the parts. This is the kinetic energy, which you can think of as the momentum operator squared over 2m, sort of a quantum mechanical analog of p squared over 2m in classical mechanics. And the second piece here is, in some sense, the potential energy. This v of x is the potential energy as a function of position. As if this were a purely classical system. For instance, if the particle was found at a particular position, what would be its potential energy? That's what this function v of x encodes. Now, we know in quantum mechanics we don't have classical particles that can be found at particular positions. Everything is probabilistic and uncertain, but you can see how this is related. This is the time-dependent Schrodinger equation, which is a little bit unnecessarily complicated. Most of the time, we work with the time-independent Schrodinger equation, which looks very similar. Again, we have a left-hand side given by the Hamiltonian. We have a kinetic energy here, and we have a potential energy here. If we're going to solve this time-independent equation, note now that the wave functions here are expressed only as functions of position, not as functions of time. This operator gives you the wave function itself back multiplied by e, which is just a number. This came from the separation of variables. It's just a constant. And we know from considering the expectation value of the Hamiltonian operator, which is related to the energy, for solutions to this time-independent Schrodinger equation, that we know this is essentially the energy of the state. Now, what does it mean here in this context, or in this potential context? Well, you have a potential function of position, and you have psi, the wave function. So this v of x psi of x, if that varies as a function of position, and it will, if the wave function has a large value, a large magnitude in a certain region, and the potential has a large value in a certain region, that means that there is some significant probability the particle will be found in a region with high potential energy. That will tend to make the potential energy of the state higher. Now, if psi is 0, in some region where the potential energy is high, that means the particle will never be found in a region where the potential energy is high. That means the state likely has a lower potential energy. This is all very sort of heuristic qualitative argument, and we can only really do better once we know what these solutions are and what these actual potential functions look like. What I'd like to do here before we move on is to rearrange this a little bit to show you what effect the potential energy related to the energy and how it's related to the energy of the state, what effect that has on the wave function. And in order to do that, I'm going to multiply through by this h bar squared over 2m and rearrange terms a little bit. What you get when you do that is the second derivative of psi with respect to x. There's my eraser. With respect to x being equal to 2m over h bar squared times v of x minus e psi. So this quantity here relates the second derivative of psi to psi itself. For instance, if the potential is larger than the energy of the state, you'll get one overall sign relating the second derivative in psi, whereas if energy is larger than potential, then you'll end up with a negative quantity here relating the second derivatives of psi with itself. So keep this in the back of your mind, and let's talk about some example potential functions. This is what we're going to be doing, or this is what the textbook does in all of Chapter 2. Write different potential functions and solve the Schrodinger equation. The first example potential we do, and this is section 2.2, is what I like to call the particle in a box. The textbook calls it an infinite square well. The particle in a hard box, for instance, you can think of as a potential function that looks like this. Get myself some coordinate systems here. You have a potential function v of x, oops, turn off my ruler, that looks something like this. This is v of x as a function of x. The potential goes to infinity for x larger than some size. Let's call this, minus a to a. If you're inside minus a to a, you have zero potential energy. If you're outside of a, you have infinite potential energy. It's a very simple potential function. It's a little bit non-physical, though, because, well, infinite potential energy, what does that really mean? It means it would require infinite energy to force the particle beyond a. If you had some infinitely dense material that just would not tolerate the electron ever being found inside that material, and you made a box out of that material, this is the sort of potential function you would get. Much more realistically, we have the harmonic oscillator potential. The harmonic oscillator potential is the same as what you would get in classical physics. It's a parabola. This is something, proportional to x squared. V of x being proportional to x squared is what I mean. This is what you would get if you had a particle attached to a spring connected to the origin. If you move the particle to the right, you stretch the spring. Put quantum mechanically, if you happen to find the particle at a large displacement from the origin, the spring would be stretched quite a large amount and would have a large amount of potential energy associated with it. From a more physical, down-to-earth sort of perspective, this is what happens when you have any sort of equilibrium position for a particle to be in. The particle is sitting here near the origin where there is a flat potential, but any displacement from the origin makes the potential tend to increase in either direction. This is like an electron in a particle trap, or an atom in a particle trap. Harmonic oscillator potentials show up all over the place, and we'll spend a good amount of time talking about them. The next potential that we consider is the delta function potential. And what that looks like, now I'm going to start at 0 and draw it going negative, but it's effectively an infinitely sharp, infinitely deep version of this particle in a box potential. Instead of going to infinity outside of your realm, it's at 0, and instead of being at 0 inside your realm, it goes to minus infinity there. This now continues downwards. It doesn't bottom out here. The overall behavior will be different now because the particle is no longer disallowed from being outside of the domain. There is no longer an infinite potential energy here. And we'll talk about that as well. These are all sort of weird, non-physical potentials. The particle in a soft box potential is a little bit more physical. If I have my coordinate system here, the particle in the soft box potential looks something like this. To keep things simple, it still changes instantaneously at, say, minus a and a, but the potential energy is no longer infinity. This is, for instance, a box made out of a material that has some pores in it, and the electron, or whatever particle you're considering to be in the box, doesn't like being in those pores. So there's some energy you have to add in order to push the particle in. Once it's in, it doesn't really matter where it is, you've sort of made that energy investment to push the particle into the box. And we'll talk about the quantum mechanical states that are allowed by this potential as well. Finally, we will consider what happens when there's no potential at all. Essentially, your potential function is constant. That actually has some interesting implications for the form of the solutions of the Schrödinger equation. And we'll talk about that in more detail. To map this onto textbook sections, this is section 2.2. The harmonic oscillator is section 2.3. The delta function potential is section 2.5. The particle in a box is section 2.6. Particle in a soft box is 2.6. And particle with no potential, or an overall constant potential everywhere in space, is section 2.4. So these are some example potentials that we'll be talking about in this chapter. What do these potentials actually mean, though? How do they influence the Schrödinger equation and its solutions? Well, the way I wrote the Schrödinger equation a few slides ago, second derivative of psi with respect to x is equal to 2m over h bar squared, just a constant, times v of x minus e psi. This is now the time-independent Schrödinger equation, so we're just talking about functions of position here. And E, keep in mind, is the energy of the state. If we're going to have a solution to the time-independent Schrödinger equation, this E exists, and it's just a number. So what does that actually mean? Let's think about it this way. We have a left-hand side determined by the right-hand side of this equation. And the left-hand side is just the second derivative with respect to position of the wave function. This is related to the curvature of the wave function. I could actually write this as a total derivative, since this is just psi is only a function of position now. So there's no magic going on with this partial derivatives. It's going to behave same as the ordinary derivative that you're used to from calculus class. The second derivative is related to the concavity of a function, whether something's concave up or concave down. So let's think about what this means. If you have a potential v of x that's greater than your energy, if v of x is greater than e, what does that mean? That means v of x minus e is a positive quantity. That means the right-hand side here will have whatever sign psi has. And I'm being a little sloppy since psi here is in general a complex function. But if we consider it to just be, say, positive, which isn't as meaningful for a complex number as it is for a real number, you would have psi of x. If psi of x is positive and this number is positive, then the second derivative is positive. Which means that if psi is, say, here, psi is positive, when it's multiplied by is positive, then the second derivative is positive. It curves like this. Whereas if psi is down here, psi is negative, this is positive, second derivative of psi is negative. It curves like this. What this means is that psi curves away from our axis, away from this psi equals 0 line. On the other hand, if v of x is less than the energy, this quantity will be negative, and we get the opposite behavior. If psi is up here, positive, it's multiplied by a negative number, and the second derivative is negative, you get something that curves downwards. If psi is on the other side of the axis, it curves upwards. Psi curves toward the axis. So this helps us understand a little bit about the shape of the wave function. For instance, let me do an example here in a little bit more detail. Suppose I have, I'll do it over here, coordinate system. If I have a potential function, let's do the sort of soft particle in a box. I can do better than that. Soft particle in a box. So v of x is constant outside your central region and constant inside your central region and has a step change at the boundaries of your region. Let's think about what our wave function might look like under these circumstances. So we have our boundaries of our region here. The other thing that we need to know to figure out what the wave function might look like is a hypothetical energy. And I'm just going to set an energy here. I'm going to do the interesting case. Let's say this is the energy. Now I'm plotting energy on the same axis as the potential, which is fine. This is the energy of the state. This is the potential energy as a function of position, so they have the same units. What this energy hypothetically means is that outside here, the potential energy is greater than the energy of the state, and inside here, the potential energy is less than the energy of the state. So we'll get different signed sort of behaviors, different curvatures of the wave function. So, do my wave function in blue here. If I say, start my wave function, this is all hypothetical now, this may not work. If I start my wave function here, at some point on the positive side of the axis, at the origin, we know the energy of the state is larger than the energy of, or than the potential energy. So this quantity is negative, and psi curves towards the axis. So since psi is positive here, I'm looking at this sort of curvature. So I could draw my wave function out sort of like this. Maybe that's reasonable, maybe that's not. This is obviously not a quantitative calculation. This is just sort of the sort of curvature that you would expect. Now, I only continued these curving lines out to the boundaries, since at the boundaries, things change. Outside our central region here, the potential energy is larger than the energy of the state, and you get curvature away from the axis. What might that look like? Well, something curving away from the axis. It's going to look sort of like that. But where do I start it? Do I start it going like that? Do I start it going like that? What does this actually look like? Well, if you think about this, we can say a little bit more about what happens to our wave function when it passes a boundary like this. And the key fact is that if v of x is finite, then while we might have the second derivative of psi with respect to x being discontinuous, maybe, might not be. In this case, the second derivative of psi is just set by this difference. So when we have a discontinuity in the potential, we have a discontinuity in the second derivative. The first derivative of psi will be continuous. Think about integrating a function that looks like this. I integrate it once, I get something maybe with large positive slope going to slightly smaller positive slope. There will be no discontinuity in the first derivative. What this means for psi is that it's effectively smooth. And that by that I just sort of mean no corners. The first derivative of psi won't ever show a corner like this. It will be something like that, for example. No sharp corners to it. What that means in the context of a boundary like this is that if I have psi going downwards at some angle here, I have to keep that angle as I cross the boundary. Now once I'm on the other side of the boundary here, I have to curve. And I have to curve according to the rules that we had here. So depending on what I actually chose for my initial point here and what the actual value of the energy was and what the actual value of the potential is outside in this region, I may get differing degrees of curvature. I may get something that happens like this, curves up very rapidly, or I may get something that doesn't curve very rapidly at all. Perhaps it's curving upwards very slowly, but it crosses the axis. Now, as it crosses the axis, the sign on psi here changes. The curvature is also determined by psi. As psi gets smaller and smaller, the curvature gets smaller and smaller, the curvature becoming 0 as psi crosses the axis. Then when psi becomes negative, the sign of the curvature changes, so this would start curving the other direction, curving downwards. It turns out that there is actually a state right in the middle, sort of a happy medium state, where psi curves, 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 and just kisses the axis. Comes towards the axis, and when it comes towards the axis and reaches the axis with 0 slope and 0 curvature, it's stuck. It will never leave the axis again. And these are the sorts of states that you might actually associate with probability distributions. You know, if psi is blowing up like this, going to positive infinity or to negative infinity, that your wave function will not be normalizable. But the wave function here, denoted by these green curves, has finite area, therefore is sort of normalizable. So these are the sorts of things that the potential function tells you about the wave function. In general, what direction it curves, how much it curves, and how quickly. And of course, doing this quantitatively requires a good deal of mathematics. But I wanted to introduce the math, or before I introduce the math, I wanted to give you some conceptual framework with which to understand what exactly this potential means. If the potential is larger than the energy, you expect things that curve upwards. And when you get things that curve upwards, you'll have, or curve away from the axis, you tend to have things blow up unless they just sort of go down and kiss the axis like this. So there will be a lot of things approaching the axis and never leaving, so that we have normalizable wave functions. On the other hand, if the potential energy is less than the energy of the state, you get things that curve towards. And well, if you have something that curves towards, it tends to do this. Always curving towards, always curving towards, always curving towards the axis. You get these sort of wave-like states. So that's a very hand-waving discussion of the sorts of behavior you get from, in this case, step discontinuous potential. And we'll see the sort of behavior throughout this chapter. To check your understanding, take this step discontinuous potential and tell me which of these hypothetical wave functions is consistent with the Schrödinger equation. Now, I did not actually go through and solve the Schrödinger equation here to make sure these things are quantitatively accurate. They're probably all not quantitatively accurate. What I'm asking you to do here is identify the sort of qualitative behavior of these systems. Is the curvature right? And let's see. Yeah, are the boundary conditions right? In particular, does the wave function behave as you would expect as it passes from the sort of interior region to the exterior region? We've been talking about solving the Schrödinger equation and how the potential function encodes the scenario under which we're solving the Schrödinger equation. The first real example of a solution to the Schrödinger equation and a realistic wave function that we will get comes from this example, the infinite square well, which I like to think of as a particle in a box. The infinite square well is called that because its potential is infinite and, well, square. What the potential ends up looking like is, if I plot this, going from 0 to A, the potential is infinity if you're outside the region between 0 and A, and at 0 if you're in between the region, if you're in between 0 and A. So what does this look like when it comes to the Schrodinger equation? Well, what we'll be working with now is the time-independent Schrodinger equation, the TISE, which reads minus h bar squared over 2m times the second derivative of, sorry, I'm getting ahead of myself, the second derivative of psi with respect to x plus potential as a function of x times psi is equal to the energy of the stationary state that results from the solution of this equation times psi. Now, this equation doesn't quite look right if we're outside the region. Bad things happen. You end up with an infinity here for v of x if x is not between 0 and a. The only way this equation can still make sense under those circumstances is if psi of x is equal to 0, if x is less than 0 or x is greater than a. So outside this region, we already know what our wave function is going to be. It's going to be 0, and that's just a requirement on the basis of infinite potential energy. Can't really exist in the real world. Now, what if we're inside? Then v of x is 0, and we can cancel this entire term out of our equation. What we're left with then is minus h bar squared over 2m, second partial derivative of psi, with respect to x, is equal to e times psi, just dropping that term entirely. So this is the time-independent Schrodinger equation that we want to solve. So how do we solve it? Well, we had minus h bar squared over 2m times the second derivative of psi with respect to x being equal to e times psi. We can simplify that just by rearranging some constants. What we get, minus second derivative of psi with respect to x equal to minus k squared psi. And this is the sort of little trick that people solving differential equations employ all the time. Knowing what the solution is, you can define a constant that makes a little more sense, in this case using a square for k instead of just some constant k. But in this circumstance, k is equal to root 2m times e over h bar. So this is our constant, which you just get from rearranging this equation. This equation you should recognize. This is the equation for a simple harmonic oscillator, a mass on a spring, for instance. Now, as I said before, the partial derivatives here don't really matter. We're only talking about one dimension, and we're talking about the time-independent Schrodinger equation, so the wave function here, psi, is just a function of x, not a function of x in time. So this is the ordinary differential equation that you're familiar with for things like masses on springs. And what you get is oscillation. Psi, as a function of x, is going to be a sine kx plus b cosine kx. And that's a general solution. A and b here are constants, to be determined by the actual scenario under which you're trying to solve this equation. This equation now, not the original Schrodinger equation. So these are our solutions. Sines and cosines. Sines and cosines. That's all well and good, but that doesn't actually tell us what the wave function is because, well, we don't know what A is, we don't know what B is, and we don't know what K is either. We know K in terms of the mass of the particle that we're concerned with, Planck's constant, and the E, separation constant, we got from deriving the time-independent Schrodinger equation. While that might be related to the energy, we don't know anything about these things. These are free parameters still. But we haven't used everything we know about the situation yet. In particular, we haven't used the boundary conditions. And one thing the boundary conditions here will determine is the form of our solution. Now, what do I mean by boundary conditions? Well, the boundary conditions are what you get from considering the actual domain of your solution and what you know about it, in particular at the edges. Now, we have a wave function that can only be non-zero between 0 and a. Outside that, it has to be 0. So we know right away our wave function is 0 here and 0 here. So whatever we get for those unknown constants, a, b, and k, it has to somehow obey this. We know a couple of things about the general form of the wave function. In particular, just from consideration of things like the Hamiltonian operator or the momentum operator, we know that the wave function itself, psi, must be continuous. We can't have wave functions that look like this. And the reason for that is this discontinuity here would do very strange things to any sort of physical operator that you could think of. For example, the momentum operator is defined as minus I h bar partial derivative with respect to x. The derivative with respect to x here would blow up and we would get a very strange value for the momentum. That can cause problems. By sort of contradiction then, the wave function itself must be continuous. We'll come back to talking about the boundary conditions and the wave function later on in this chapter, but for now, all we need to know is that the wave function is continuous. What that means is that since we're 0 here, we must go through 0 there, and we must go through 0 there, since we're 0 here. So, what that means, wrong color, means psi of 0 is equal to 0, and psi of a is equal to 0. What does that mean for our hypothetical solution psi of x equals a sine kx plus b cosine kx? Well, first of all, consider this one. The wave function at 0 equals 0. When I plug 0 into this, the sine of 0, k times 0 is going to be 0. The sine of 0 is 0, but the cosine of 0 is 1. So what I'll get if I plug in 0 for psi is 1 times b. So I'll get b. Now if I'm going to get 0 here, that means b must be equal to 0. So we have no cosine solutions. No cosine part to our solutions. So everything here is going to start like sines. It's going to start going up like that. That's not the whole story, though, because we also have to go through 0 when we go through a. So if I plug a into this, what I'm left with is psi of a is equal to capital A times the sine of ka. If this is going to be equal to 0, then I know something about ka. In particular, the sine function goes through 0 for particular values of particular values of its argument. Sine of x is 0 for x equals integer multiples of pi. What that actually looks like on our plot here is things like this. Our wave functions are going to end up looking like this. So let me spell that out in a little more detail. Our psi of a wave function is a times the sine of k times a. And if this is going to be equal to 0, ka has to be either 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, etc. This is just coming from all of the places where the sine of something crosses 0, crosses the axis. Now it turns out this is not interesting. This means psi is 0 everywhere, since the sine of 0 is, well, sine k times a. If ka is going to be 0, then everything. If ka is 0, k is 0. So the sine of k times x is going to be 0 everywhere. So that's not interesting. This is not a wave function that we can work with. Another fact here is that these plus or minuses the sine of minus x is equal to minus the sine of x. Sine is an odd function. Since what we're looking at here has a normalization constant out front, we don't necessarily care whether there's a plus or a minus sign coming from the sine itself. We can absorb that into the normalization constant. So, essentially what we're working with then is that Ka equals pi, 2 pi, 3 pi, etc., which I'll just write as n times pi. Now, if k times a is going to equal n times pi, we can figure out what, well, let's just substitute in for k, which we had a few slides ago was root 2m capital E over h bar. So that's k. K times a is equal to n pi. This is interesting. We now have integers coming from n here as part of our solution. So we're no longer completely free. We in fact have a discrete set of values. Now a, that's a property of the system. We're not going to solve for that. M, that's a property of the system. H bar, that's a physical constant. The only thing we can really solve for here is E. So let's figure out what that tells us about E. And if you solve this for E, you end up with n squared pi squared h bar squared over 2m a squared. This is a discrete set of allowed energies. And I'm going to put an exclamation point there because this is important. This is the quantum part of quantum mechanics. We started with a system that, by all respects, was continuous and had nothing really discrete about it. And what we ended up with, in the end, was a discrete set of allowed energies, a discrete set of solutions. Our wave functions look like psi sub n now. We don't have just any possible value, and they're going to be big A, a normalization constant, times the sine of, and if you substitute all of this back in, Ka is n pi. What we end up with is n pi over a times x inside our sine function. This is our wave function. The spatial part, our solution to the time-independent Schrödinger equation. There's only a discrete set of them, and that's interesting. That is the quantum in quantum mechanics. One more detail to nail down here is the normalization. We know the integral from minus infinity to infinity of psi star psi dx has to equal 1. Well, in this case, we know that's going to reduce to the integral from 0 to a of psi star psi, where I should write it here, psi n equals a times the sine of n pi over lowercase a x. So I can write down psi star psi now, and that's going to give me a squared sine squared n pi over a times x, integrating dx. There's no real reason for complex conjugates here, since this is a purely real function. So the integral just ends up looking like this. And this has to equal 1 if the wave function is going to be treated as a probability distribution. Now, integrating sine squared over an interval like this, you need to be a bit careful that the interval you're integrating over has a certain minimum number of cycles. In this case, it has an even number of cycles. Not an even number. It has a specific integer number of cycles. And if you're integrating over an integer number of cycles of sine squared effectively averages out to a half. If you want to do the integral here more rigorously, you can make the substitution that sine squared of x is a half minus a half cosine of 2x. And the integral of cosine you can do. But for now, I'm just going to simplify this and say this averages out, the sine squared part here averages out to a half. And what we end up with then is a squared times a half of the actual interval we're integrating over, 0 to a. So technically this should be a minus 0, but you get the idea. The integral must equal 1 in order for things to be normalized, which tells us that a is equal to the square root of 2 over a. Big A is the square root of 2 over little a. So that determines our normalization constant. Now we know everything about our solutions. Psi sub n of x is root 2 over a times the sine of n pi over a x. That's our wave function, normalized and ready for use. So these are our solutions, and these are the energies associated with those solutions, and we only got a discrete set of them. In order to better visualize this, I'm going to draw a diagram for you, and this is a common sort of diagram to draw in quantum mechanics, though it does abuse the system of units a little bit. If this is our x-axis, we know our wave function is only defined, only non-zero, I mean, in between 0 and a. So we have this region that we're interested in. Now I want you to think about this y-axis now as a hybrid energy wave function axis. Now treating it as an energy axis, I'm going to make some marks here. Yeah, maybe you can go up to 16 there. And each of these marks represents sort of one unit of energy. I'll label this lowestmost tick mark E1, what I get if I substitute 1 in for n in this expression for the energy. Essentially, pi squared h bar squared over 2ma squared is this value. Now, E1, consider a line at E1. Now treat this as an axis for a plot of the wave function. Now we know what the wave function looks like for E1. If we substitute 1 in for n here as well, we just get sine pi over a times x with the normalization constant. Just to show the shape of this wave function, we don't really care about the normalization constant. And it looks something like that. Now, if I continue up to E2, E2 here, if I substitute 2 in for this, means I'm going to be getting a 4 here, so it's 4 times bigger than E1. So I go up to 4 for E2. I draw a second line across. Now I can plot the wave function psi2. We're going to have a 2 here, so we're going to effectively go from 0 to 2 pi as x goes from 0 to a. So what that means is going to look like, it's a full cycle. I'm not doing a very good job drawing it. Full cycle of a sine wave. I can keep going now. If I substituted 3 in here, I would get 9 times what I get if I substitute 1 in here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. We're up to here. 5, 6, 7, 8, 9 here. It's going to be E3. And I can draw a line across here. Consider that now as the x-axis for the wave function psi3. And that's going to be 3 half cycles of a sine wave. And you can continue on. If I go up to, say, 4, E4 is going to be at 16 times E1. It's going to be somewhere up here. It's going to look something like that. So, half a cycle, 2 half cycles, 3 half cycles, 4 half cycles, gradually moving up in energy from effectively 1 to 4 to 9 to 16, going up as n squared. So this is what our wave functions look like, and they have a lot of nice properties that we'll talk about later. But just to highlight one, if you look at the middle of the interval here, a over 2, either the wave function has a maximum or it has a 0. Maximum, 0. And the trend continues. Maximum 0, maximum 0, maximum 0, maximum 0, as you continue to go up in energy. If you center yourself at the midpoint of this interval, your wave function is either even or odd, and it's alternatingly even and odd. even about the midpoint, odd about the midpoint, even about the midpoint, odd about the midpoint. And this sort of general structure and the degree of symmetry we have here leads to some really nice mathematical properties that connect this analysis with Fourier analysis, Fourier series in particular, which is what we'll talk about next. For now, to check your understanding, here are two arguments about what we did over the last couple of slides that disagree with what we did, and your job is to figure out what's wrong with these arguments. I keep talking about solutions to the time-independent Schrödinger equation and how they have nice mathematical properties. What that actually means is, well, what I'm referring to are the orthogonality and completeness of solutions to the time-independent Schrödinger equation. What that actually means is the topic of this lecture. To recap, first of all, these are what our stationary states look like for the infinite square well potential. This is the potential such that v of x is infinity if x is less than 0 or x is greater than a, and 0 for x in between 0 and a. So if this is our potential, you express the time-independent Schrödinger equation, you solve it, you get sine functions for your solutions. You properly apply the boundary conditions, namely that psi has to go to 0 at the ends of the interval because the potential goes to infinity there. And you get n pi over a times x as your argument to the sine functions. And you normalize them properly, you get a square root of 2 over a out front. The energies associated with these wave functions, and this energy now is the separation constant in the conversion from the time-dependent Schrödinger equation to the time-independent Schrödinger equation, are proportional to n, that index. The wave functions themselves look like sine functions, and they have an integer number of half wavelengths, or half cycles, in between 0 and a. So this orange curve, this is n equals 1. The blue curve is n equals 2. The purple curve is n equals 3. And the green curve is n equals 4. If you calculate the squared magnitude of the wave functions, they look like this. 1 hump for n equals 1. 2 humps for the blue curve, n equals 2. 3 humps for the purple curve, n equals 3. And 4 humps for the green curve, n equals 4. So you can see just by looking at these wave functions that there's a lot of symmetry. One thing we talked about in class is that these wave functions are either even or odd about the middle of the box, and this is a consequence of the potential being an even function about the middle of the box. If I draw a coordinate system here, going between 0 and a, either the wave functions have a maximum or they have a 0 at the middle of the box. So for n equals 1 we have a maximum, for n equals 2 we have a 0. And this pattern continues. The number of nodes is another property that we can think about. And this is the number of points where the wave function goes to 0. For instance, the blue curve here for n equals 2 has 1 node. This trend continues as well if I have a wave function that, for instance, let me draw it in some absurd color, has 1, 2, 3, 4, 5, 6, 7 nodes. You know this would be for n equals 8. This would be sort of like the wave function for n equals 8. These symmetry properties are nice. They help you understand what the wave function looks like, but they don't really help you calculate. What helps you calculate are the orthogonality and completeness of these wave functions. So what does it mean for two functions to be orthogonal? Let's reason at this from a perspective which you're more familiar, the orthogonality of vectors. We say two vectors are orthogonal if they're at 90 degrees to each other, for instance. So if I had a two-dimensional coordinate system, and one vector pointing in this direction, let's call that A, and another vector pointing in this direction, let's call that B, I would say those two vectors are orthogonal if they have a 90-degree angle separating them. Now that's all well and good in 2 dimensions. It gets a little harder to visualize in 3 dimensions, and, well, what does it mean for two vectors to be separated by 90 degrees if you're talking about a 17-dimensional space? In higher dimensions like that, it's more convenient to define orthogonality in terms of the dot product. And we say two vectors are orthogonal in that case if the dot product of those two vectors is 0. Now in two dimensions, you know the dot product is given by the x components of both vectors, ax times bx, plus the y component of those two vectors multiplied together, ay times by. If this is 0, we say these two vectors are orthogonal. In three dimensions, we can say plus az times bz. And if this is equal to 0, we say the vectors are orthogonal. And you can continue this, multiplying together like components, or same dimension of the components of vectors in each dimension, multiplying them together. a1, b1, a2, b2, a3, b3, a4, b4, all added up together. And if this number is 0, we say the vectors are orthogonal. We can extend this notion to functions. But what does it mean to multiply two functions like this? In the case of vectors, we were multiplying like components, both x components, both y components, both z components. In the case of functions, we can multiply both functions' values at particular x coordinates and add all those up. And what that ends up looking like is an integral. Say the integral of f of x, g of x, dx. So I'm scanning over all values of x instead of scanning over all dimensions. And I'm multiplying the function values at each individual point, at each individual x, together, and adding them all up, instead of multiplying the components of each vector together at each individual dimension and adding them all up. The overall concept is the same, and you can think about this as, in some sense, a dot product of two functions. Now in quantum mechanics, since we're working with complex functions, it turns out that we need to put a complex conjugate here on f in order for things to make sense. This should start to look familiar now. You've seen expressions like the integral of psi star of x times psi of x dx is equal to 1, our normalization condition. This is essentially the dot product of psi with itself. Psi, of course, is not orthogonal to itself, but it is possible to make a pair of functions that are orthogonal. And we say functions are orthogonal if if and only if the integral over the domain of the functions now, which I'm leaving off, there are limits on this integral, but I'm leaving them off, f star of x, g of x, dx is equal to 0. As a brief side note here, we can also make a connection with the magnitude of a vector, or the norm. For instance, we say if a vector dot a vector is equal to 1, we call this a unit vector. And in the case of functions like this, if, for instance, the integral of psi star psi dx is equal to 1, then we say psi is normalized. So both of these concepts, like dot products and unit vectors, dot products and normalized functions, or inner products of functions, you may hear that term as well, can be generalized. Orthogonality turns out to be really useful because integrals like this appear a lot in quantum mechanics, and it's very handy when we can look at an integral and say, oh, it's 0. In the case of the particle in a box, or the infinite square well potential, we got sine functions. So what does this actually look like in real life? Well, sine functions obey an orthogonality condition, and this is the orthogonality integral. Now I'm just going between 0 and a, and I have the sine of n pi over a times x, sine of m pi over a times x. And right now I'm going to stipulate that m is not equal to m. m is not equal to n. You'll see where this comes in later. This integral can be done reasonably easily if you remember your trig identities. And I certainly don't remember my trig identities. I have to go and look them up all the time. But sine of x times sine of y, this is a product identity for sine, is equal to 1/2 of cosine x minus y minus the cosine of x plus y.
if you apply this identity to this product, what you end up with is a half out front, the integral from 0 to a, as before, and now we have two cosine terms. And we're going to have a cosine of n minus m pi x over a plus cosine of n plus m pi x over a, all integrated dx. This is now an integral you can do. It's just an integral of cosine. And what you get, if n is not equal to m, this term is non-zero, this term is non-zero. Both of these just work out fine. And we end up with, for our integral, where did it go? A half out front, as before, a over n minus m pi times the sine of n minus m pi x over a plus, is there a plus? Sorry, I've gotten the sign backwards here. This sign should be minus, same as this sign. The sign should be minus here as well. A over n plus m pi sine n plus m pi x over a. And this whole thing is evaluated between 0 and a. Now, I can do the evaluations. If I plug in a for this, I'm going to be plugging in an a here for this x. So the a's are going to cancel, and I'm just going to be left with n minus m pi. This is going to be a half, ugly half, going to be a half of, actually let's pull the a out front, since I have an a here and an a here. Let's pull the pi out front as well. So I've got a over 2 pi out front, and then I'm going to have sine of n minus m pi over n minus m minus the sine of n plus m pi over n plus m. This is evaluated at a, and if I evaluate it at 0, well, I get 0. Because if I substitute 0 in for x here or 0 in for x here, the whole argument of sine is 0, and sine of 0 is 0. So this is our answer. But we know that sine of n and m both being integers, the sine of an integer times pi is also 0. So these are 0 as well. The sine term here goes to 0, the sine term here goes to 0. And what we're left with is just 0. Which means, subject to our assumption that m is not equal to m, the sine of n and m, these two sine functions of n pi x over a and n m pi x over a, are orthogonal. In the case of normalized wave functions, these constants out here end up canceling out, and what you end up with is the integral of psi star psi. Now I'll write out the dependence. The integral of psi sub n star of x and psi sub m star of x integral dx. Now the integral is from 0 to a, is equal to, I'm going to write this in terms of something called the Kronecker delta, delta mn, where delta mn is defined to be 1 if m equals n, and 0 if m is not equal to n. So these are the sort of orthogonality conditions we'll be working with in quantum mechanics, and writing them out in terms of the Kronecker delta is a handy way of doing things. That's what orthogonality actually looks like for the solutions to the time-independent Schrödinger equation for the infinite square well potential, the particle in a box. If I move forwards a little bit, where are we going with this? These orthogonality conditions are really handy, thanks to something called Fourier's trick, what your textbook, what Griffiths calls Fourier's trick. And the trick goes like this. Suppose I have some general function of x. I'm going to hypothetically say, I'm going to write this function, f of x, as an infinite sum of constants multiplied by sine functions. If this were possible, how would I find the Cn c sub n necessary to actually necessary to write this. And it turns out that you can do this pretty easily. What you do is take f of x, which is equal to the sum over n equals 1 to infinity of c sub n sine n pi x over a, and from the left, I'm going to integrate both equations, but before I integrate them, I'm going to multiply them by sine m pi x over a, sine m pi x over a. And these are both integrals dx, which I can make some space for. So I'm taking this original equation, and I'm multiplying it from the left by sine m pi x over a, and I'm integrating from 0 to a dx, both sides of this equation. If I do this, there's not much I can do with the left side since I don't know what f of x is, but I can work with the right-hand side. So let's look at the right-hand side here. The right-hand side, first thing I'm going to do is I'm going to exchange the order of summation and integration, and I'm going to pull the constant c sub n out of the integral. So what I have on the far left then is the sum from n equals 1 to infinity, c sub n times the integral of from 0 to a of sine m pi x over a times this sine n pi x over a dx. Now, you know what this integral looks like. This looks like the orthogonality condition we were working with on the last page. So it turns out this is going to be equal to 0 if n is not equal to m. So if you imagine this sum as being this term repeated over and over and over again for different values of n, all of those terms are going to vanish except for the one term when n equals m. So what that means is that we no longer have a sum here, we have only a single term, and that single term is given by Cm, integral from 0 to a, of sine of m pi x over a times the sine of m pi x over a, since n is now equal to m. I'm just going to write this as sine squared dx. And this looks like our normalization condition. We know how to do this integral. This just comes out to a over 2. So we've done all of our integrals, and we've made our sum go away, which is a pretty neat trick. We have our left-hand side over here, and our right-hand side is just Cm times a over 2. So we can solve for Cm, and what you get is that Cm is equal to 2 over a times the integral from 0 to a of f of x sine m pi x over a dx. This tells us that if this is possible, to write f of x as a sum like this, it gives us a formula for what numbers to use in the sum. So that's all well and good. But does that actually work? This is nice because it allows us, or it hypothetically allows us to express any function. In the context of the Schrodinger equation, this would be any initial conditions to the Schrodinger equation. And it allows us to express that as a sum of, these are now going to be our stationary states. So our initial conditions maybe we can express them as a sum of stationary states. You know, superpositions of stationary states are also solutions to the Schrodinger equation. So this is good. It allows us to construct whatever sort of wave function we want in terms of the functions that we have. If we follow this formula, maybe it will work. Does it work? That's the other property that's really nice about solutions to the time-independent Schrodinger equation. They form what's called a complete basis. They are a complete basis set. This is like having a set of unit vectors with which you can express any other unit vector. For instance, x hat, y hat, and z hat. unit vectors pointing in the x, y, and z directions form a basis for 3D space. If we have a set of solutions to the Schrodinger equation, for instance, the solutions to the Schrodinger equation for the infinite square well potential, our sine function, they actually form a complete basis for functions. Which means this formula for expressing some function f of x in terms of a sum of sine functions, where the numbers used in the sum are calculated by this Fourier's trick sort of integral, this actually works for damn near any f of x. Not quite any, just for the sake of being mathematically rigorous. This is really only going to work for smooth square integrable functions. Eesh. If f of x blows up to infinity, this isn't going to work. And if f of x has a lot of corners and discontinuities, this isn't going to work either. But for smooth square integrable functions, which happens to be what we really care about for quantum mechanics, this works. How does this actually work out? Why does this actually work out? Just to say very briefly, conceptually, how this works. This works because it is possible to write sum of c sub n sine of n pi x over a, such that if I plotted this as a function of x between 0 and a, I can make functions that look like this. I can make functions that are very sharp and very tall. And I can make these functions wherever I want by suitable choices of this Cn. So if I change Cn, I can change the position of this spike. And I can make this spike as sharp as I want, and I can make it as tall or as short as I want. And what that means is I can make whatever function you want. For instance, suppose the function you want looks something like this. I can make it by adding up a bunch of spikes. I can have a little spike here, and a little spike here, and a little spike here, a little spike here, etc. If I effectively fill this whole space with these very sharp spikes going up to the value of the function, I can recreate whatever function you want, no matter what shape it is. Provided it's reasonably well behaved and square integrable, this actually works really well. What this looks like graphically is shown here. This is some hypothetical f of x. F of x is shown in black now, and it runs from down here to up here. It's just a straight line. Now, if I only include the first term in this long sum, remember now we're expressing f of x as the sum of n equals 1 to infinity of c sub n times sine of n pi x over a. If I only let the sum go from n equals 1 to 1, I get the blue curve here. So there's only one term in this sum, you just get a sinusoid. It's not a very good approximation to the straight black curve. But if I let n become larger, in this case I think I have n equals 20 here for the purple curve, you can see the purple curve drops very rapidly, wiggles, but is mostly going straight along the black curve. It's having some difficulty matching the black curve at the endpoints here, and that's because part of this assumption here that we're working with sine functions, these are from the solutions to the Schrodinger equation, not from a rigorous treatment of Fourier series or Fourier expansions of functions. So since we're requiring our purple curve here to go through 0, of course it's going to have to give up on fitting the function near the endpoints. But if you include a lot of terms in this, you can make this approximation quite good. Generally, the more terms you add, the closer you get to your function. So, to sum up, the solutions to the time-independent Schrodinger equation for the particle in a box are these sine functions, and these sine functions obey an orthogonality condition. And that orthogonality condition allows you to find out relatively easily what constants to use in an expression of any function as a sum of sine functions, as a sum of stationary states. So if we have some initial conditions for our wave function, we can express it as a sum of stationary states.
we then know the way stationary states evolve with time. We know then everything about how our wave function will evolve forwards in time. To check your understanding, here are two relatively straightforward problems to use Fourier's trick and the orthogonality conditions for sine to determine, for instance, C2, C3, and C4 for this f of x, or C2 for this f of x. So, we've been working with solutions to the time-independent Schrödinger equation for the infinite square well potential, the particle in a box case. How do these things actually work, though? In order to give you guys a better feel for what the solutions actually look like and how they behave, I'd like to do some examples and use a simulation tool to show you what the time evolution of the Schrödinger equation in this potential actually looks like. So, the general procedure that we've followed or will be following in this lecture is, once we've solved the time-independent Schrödinger equation, we get the form of the stationary states. Knowing the boundary conditions, we get the actual stationary states, the stationary state wave functions and their energies. These can then be normalized to get true stationary state wave functions that we can actually use. These stationary state wave functions will, for the most part, form an orthonormal set, psi sub n of x. We can add the time part, knowing the time-dependent Schrödinger equation, or the time part that we got when we separated variables in the time-dependent Schrödinger equation. We can then express our initial conditions as a sum of these stationary state wave functions, and use this sum then to determine the behavior of the system. So what does that actually look like in the real world? Not like very much, unfortunately, because the infinite square well potential is not very realistic, but a lot of the features that we'll see in this sort of potential will appear in more realistic potentials as well. So, this is our example. These are our stationary state wave functions. This is what we got from the solution to the time-independent Schrödinger equation. This was the form of the stationary states, these were the energies, and then this was the normalized solution with the time dependence added back on, since the time dependence is basically trivial. The initial conditions that I'd like to consider in this lecture are the wave function evaluated at 0 is either 0 if you're outside the, this should be A. If you're outside the domain, you're 0. If you're inside the domain, you have this properly normalized wave function. We have an absolute value in this, which means this is a little difficult to work with. But what the plot actually looks like, if I draw a coordinate system here, going from 0 to A, is this. It's just a tent, a properly built tent with straight walls going up to a nice peak in the middle. Our general procedure suggests that we express this initial condition in terms of these stationary states with their time dependence, and that will tell us everything we need to know. One thing that will make this a little easier to work with is getting rid of the absolute values we have here. So let's express psi of x time t equals 0 as a three-part function. First, we have root 3 over a, 1 minus. Now what we should substitute in here is what we get if, say, 0 is less than x is less than a over 2. Sort of the first half interval going out to a over 2 here. In this case, we have something sloping upwards, which is going to end up, in this context, being 1 minus a over 2 minus x over a over 2. So, to say another word or two about that, if x is less than a over 2, this quantity here will be negative. So I can get rid of the absolute value if I know that this quantity in the numerator is positive. So I multiply the quantity in the numerator by a minus sign, which I can express more easily just by writing it as a over 2 minus x. A over 2 minus x. That will then ensure that this term here is positive for x's in this range. 1 minus that is then this term in our wave function. For the other half of the range, root 3 over a, 1 minus something, and this is now from a over 2 is less than x is less than a, the second half of the interval. For the second half of the interval, x is larger than a over 2, so x minus a over 2 is positive. So I can take care of this absolute value just by leaving it as x minus a over 2. I don't need to worry about the absolute value in this range. So this is x minus a over 2 all over a over 2. And of course, if we're outside that, we get 0. This technique of splitting up absolute values into separate ranges makes the integrals a little easier to express and a little easier to think about. So that is our initial conditions. How can we express these initial conditions as a sum of stationary state wave functions evaluated at time t equals 0? This is where Fourier's trick comes in. If I want to express my initial conditions as a sum of stationary state wave functions, I know I can use this sort of an expression. This is now my initial conditions, and my stationary state wave functions are being left multiplied, complex conjugated, integrated over the domain, and that gives us our constants, C sub n, that go in this expression for the initial conditions in terms of the stationary state wave functions. The notation here is that if psi appears without a subscript, that's our initial condition. That's our actual wave function. And if psi appears with a subscript, it's a stationary state wave function. So what does this actually look like? Well, we know what these functions are. First of all, we know that this function, which has an absolute value in it, is best expressed if we split it up in two. So we're going to split this integral up into one going from 0 to a over 2 and one going from 0 to a. So let's do that. We have c sub n equals the integral from 0 to a over 2 of our normalized stationary state wave function, which is root 2 over a times the sine of n pi x over a. That's this psi sub n star, evaluated at time t equals 0. I'm ignoring time for now, so even if I had my time parts in there, I would be evaluating e to the 0, where time is 0. So I would get 1 from those parts. Then you have psi, our initial conditions, and our initial conditions for the first half of our interval was root 3 over a, 1 minus a over 2 minus x over a over 2. And I'm integrating that dx. The second half of my integral from a over 2 to a, looks much the same. Root 2 over a sine n pi x over a. That part doesn't change. The only part that changes is the fact that we're dealing with the second half of the interval, so the absolute value gives me a minus sign up here more or less. Root 3 over a, 1 minus x minus a over 2 over a over 2 dx. So, substitute in for n and do the integrals. This, as you can imagine, is kind of a pain in the butt. So what I'd like to do at this point is give you a demonstration of one way that you can do these integrals without really having to think all that hard. And that's doing them on the computer. You can of course use Wolfram Alpha to do these. You can of course use Mathematica. But the tool that I would like to demonstrate is called Sage. Sage is different than Wolfram Alpha and Mathematica in that Sage is entirely open source and it's entirely freely available. You can download a copy, install it on your computer, and work with it whenever you want. It's a very powerful piece of software. Unfortunately, it's not as good as the commercial alternatives, of course, but it can potentially save you a couple $100. The interface to this software that I'm using is their notebook webpage. So you can use your Google account to log into this notebook page, and then you have access to this sort of an interface. So, if I scroll down a little bit here, I'm going to start defining the problem. A, here, that's our domain. Our domain goes from 0 to a. H bar, I'm defining to be equal to 1, since that number is a whole lot more convenient than 10 to the minus 31st. N, x, and t, those are just variables, and I'm defining them as variables given by these strings, n, x, and t. Now we get into the physics. The energy, that's a function of what index you have, which particular stationary state you're talking about. This would be psi sub n. This would be E sub n. E sub n is equal to n squared pi squared h bar squared over 2ma squared. That's an equation that we've derived. Psi of x and t, psi sub n of x and t in particular, is given by this. It's square root of 2 over a times this sine function times this complex exponential, which now uses the energy, which I just defined here. Psi star is the complex conjugate of psi, which I've just done by hand by removing the minus sign here. More or less just a copy-paste. G of x is what I've defined the initial conditions to be, which is square root of 3 over a times this 1 minus absolute value expression. And c sub n here, that's the integral of g of x times psi from 0 to a over 2 plus g of x times psi going from a over 2 to a. That's all well and good. Now I've left off the psi stars, but since I'm evaluating at time t equals 0, it doesn't matter. Psi is equal to psi star at t equals 0. I did have to split up the integral from 0 to a over 2 and a over 2 to a, because otherwise Sage got a little too complicated in terms of what it thought the integral should be. But given all this, I can plot, for instance, g, and if I click evaluate here, momentarily a plot appears. This is a plot of g of x as a function of x. Now I defined a to be equal to 1, so we're just going from 0 to 1. This is that tent function I mentioned. If I scroll down a little bit, we can evaluate c of n. This is what you would get if you plugged into that integral that I just wrote on the last slide. You can make a list evaluating c of n for x going from 1 to 10, and this is what you get. You get these sorts of expressions. 4 times square root of 6 over pi squared, or minus 4 root 6 over pi squared divided by 9, 4 root 6 over pi squared over 25, 4 root 6 over pi squared over 49. You can see the sort of pattern that we're working with. Some number divided by an odd number raised to the nth power, or squared. We can approximate these things just to get a feel for what the numbers are actually like. And we have 0.99 minus 0.11 plus 0.039, etc. Moving on down. So that's the sort of thing that we can do relatively easily with Sage. Get these types of integral expressions and their values. You can see I've done more with this Sage notebook, and we'll come back to it in a moment. But for now, these are the sorts of expressions that you get for c sub n. So our demo with Sage tells us c sub n equals some messy expression. And it can evaluate that messy expression and tell us what we need to know. Now, the actual form of the evaluated c sub n was not actually all that complicated. And if we truncate our sum, instead of summing from, now this is expressing psi of x t, our wave function, as an infinite sum, n equals 1 to infinity, of c sub n psi sub n of x and t. If I truncate this sum at, say, n equals 3, I'll just have a term from psi 1 and psi 3. Recall back from the Sage results that psi 2, the coefficient of psi 2, c sub 2, was equal to 0. So let's find the expectation of x squared. Knowing the form of these functions, and now knowing the values of these c sub n from Sage, you can write out what x squared should be. This is the expected value of x squared, and it's going to be an integral of these numbers, 4 root 6 over pi squared times psi 1, which was root 2 over a sine, not n, so we're just dealing with psi 1 now. We have pi x over a. We have to include the time dependence now, since I'm looking for the expected value of x squared as a function of time now. And we have e to the, where'd it go, minus I times pi squared h bar squared t over 2ma squared, all divided by h bar, or I could just cancel out one of the h bars here. That's our first term.
in our first term of our expression. The next term we have 4 root 6 over 9 pi squared from this coefficient. Now psi 3 is root 2 over a sine of 3 pi x over a times, again, complex exponential, e to the minus I pi squared h bar squared t over 9 pi squared h bar squared t over 2m a squared, all divided by h bar. Now, what is this? This whole thing needs to be complex conjugated, because this is psi star. What's next? Well, I need to multiply this by x squared, and I need to multiply that by the same sort of thing, e to the plus this minus same sort of thing, e to the plus this. So this is the term in orange brackets here is psi star. This is our x. The term in blue brackets here is our psi. So we're just using the same sort of expression, only you see just how messy it is. This is the integral of psi star x squared psi. This is psi star, this is x squared, and this stuff is psi. We have to integrate all of this dx from 0 to a. This is pretty messy as well. Messy, but doable. Now, since I was working with Sage anyway, I thought, let's see how the time dependence in this expression plays out in Sage. So, going back to Sage, we know these c sub n's. These are the c sub n's that I chose for c sub 1 and c sub 3. And c sub n of x gives me some digits. C sub n evaluated gave me these numbers in just in decimal form. Now I can use these c sub n's to express that test function where I truncated my sum at psi sub 3. So this is our test function. If you evaluate it, it's a lot more simple when you plug in the numbers, sine 3 pi x and sine pi x. When h bar is 1 and a is 1, these expressions are a lot easier to work with, which gives you a feeling for why quantum mechanics often we assign h bar equal to 1. The expected value of x squared here is then the integral of the conjugate of my test function times x squared times my test function, integrated from 0 to a. And Sage can do that integral. It just gives you this. Sage can also plot what you get as a result. Now you notice Sage has left complex exponentials in here. If you take this expression and manually simplify it, you can turn this into something with just a cosine. There is no complex part to this expression. But Sage isn't smart enough to do that numerically, so I have to take the absolute value of this expression to make the complex parts, the tiny, tiny complex parts, go away. And if I plot it over some reasonable range, this is what it looks like. It's a sinusoid, or a cosinusoid actually. And what we're looking at here on the y-axis is the expected value of x squared. This is related to the variance in x. So it's a measure of more or less the uncertainty in position. So our uncertainty in position is oscillating with time. What does this actually look like in the context of the wave function? Well, the wave function itself is going to be a sum, c sub 1 times psi 1, c sub 3 times psi 3, c sub 5 times psi 5, c sub 7 times psi 7, etc. I can do that in general by making this definition of a function, where I just add up all of the c sub n's and all the psi sub n's for n in some range. F of x, if I go out to 7, looks like this. You can get a feel for what it would look like if I added more terms as well. Now the plot that I'm showing you here is a combination of 4 things. First, it's the initial conditions shown in red.
That's the curve that's underneath here, the tent. I'm also showing you this approximate wave function when I truncate the sum at 2, just the first term. That's this poor approximation here, smooth curve. The function, if I truncate the approximation at 4, that will include psi 1 and psi 3. That's this slightly better approximation here, this one. And if I continue all the way up to 20, that's this quite good approximation, the blue curve here, that comes almost all the way up to the peak of the tent. So that's what our approximate wave functions look like, but these are all evaluated at t equals 0. What does that look like, for instance, in terms of the probability density and as a function of time? So let's define the probability density, rho of xt, as the absolute value of our approximate function, and I'll carry the approximation all the way to n equals 20, absolute value squared. And I'm getting the approximate form with this dot n at the end. So this is our approximate form of the probability density calculated with the first 20 stationary state wave functions. This plot then shows you what that time dependence looks like. I'm plotting the probability density at time t equals 0, probability density at time t 0.04, 0.08, 0.12, 0.16. We start with blue, dark blue. That's this sort of peaked curve, which should be more or less what you expect, because we did a problem like this for this sort of wave function in class. Then you go to dark green, which is under here, underneath the yellow. It seems to have lost the peak, and it's spread out slightly. Red is at time 0.08, and if I scroll back up to our uncertainty as a function of time plot, 0.08 is here. So it's pretty close to the maximum uncertainty. You expect the uncertainty, the width, to start decreasing thereafter. If I scroll back down here, this red curve then is more or less as wide as this distribution will ever get. And if we continue on in time, now going to 0.12, that was the orange curve here. And the orange curve is back on top of the green curve. The wave function has effectively gotten narrower again. And if you keep going all the way up to 0.16, you get the cyan curve, the light blue curve, which is more or less back on top of the dark blue curve. So the wave function sort of spilled outwards and then sloshed back inwards. You can sort of imagine this as ripples in a tank of water radiating out and then coming back to the center. This is what the time evolution would look like as calculated in SAGE. You can make definitions of functions like this, you can evaluate them, you can plot them, and you can do all of that relatively easily. Now I'll give you all a handout of this worksheet so that you get a feel for the syntax. If you're interested in learning more about SAGE, please ask me some questions. I think SAGE is a great tool, and I think it has a promising future, especially in education like this. For students, the fact that this is free is a big deal. So that's what the time variability looks like. We had our wave function, which started out sort of sharply peaked, our probability density, rho of x, which I should actually write as rho of x and t, which sort of got wider and then sloshed back in. So we sort of had this outwards motion followed by inwards motion, where our expectation of x squared related to our uncertainty oscillated. Oh, sorry. It didn't oscillate about x equals 0. It oscillated about some larger value. It didn't oscillate about 0. It oscillated about some larger value. So there's some sort of mean uncertainty here. Sometimes you have less uncertainty, sometimes you have more uncertainty. That's the sort of time dependence you get from quantum mechanical systems. To get an even better feel for what the time variability looks like, there's a simulation that I'd like to show you. And this comes from Falstad.com, which, as far as I can tell, is a guy who was sick of not being able to visualize these things, so he wrote a lot of software to help him visualize them. So here's the simulation, and I've simplified the display a little bit to make things easier to understand. These circles on the bottom here, each circle represents a stationary state wave function. And he has gone all the way up to stationary state wave functions that oscillate very rapidly, in this case. But this is our ground state. This is our first excited state, second excited state, third excited state, etc. N equals 1, 2, 3, 4, 5, 6, 7, etc. Now, in each of these circles, there may or may not be a line. The length of the line represents the magnitude of the time part of the evolution of that particular stationary state. And the angle going around the circle here represents the phase as that evolution proceeds. So if I unstop this simulation, you can see this slowly rotating around. You're also probably noticing the color here changing. The color of this represents the phase. The vertical size of this represents the probability density, and the color represents the phase. So it's a representation of where you're likely to find it, and a sort of color-based representation of how quickly it's evolving. The vertical red line here in the center tells you what the expectation value for position is. And in this case, it's right down the middle. If I freeze the simulation and add a second wave function, this is now adding some component of the first excited state. And by moving my mice around here, I can add varying amounts, either adding none or a lot, and I can add it at various phases. I'm going to add a lot of it, an equal amount as the ground state, and I'm going to do it at the same phase. And I'm going to release and let that evolve. So you can see now the probability density is sort of sloshing to the left and sloshing back to the right. And if you look at our amplitude and phases, you can see the ground state is still rotating. The first excited state is rotating, but the first excited state is rotating 4 times faster. So when they align, you have something on the right. When they anti-align, something on the left. They're aligned, they're anti-aligned. And this sloshing back and forth is one way where we can actually get motion out of stationary states. You notice the phase is no longer constant. You have some red parts, some purple parts, and things are sort of moving around in an awkward way. The colors are hard to read, but you know now that the phase of your wave function is no longer going to be constant as a function of position. So those exponential time parts may be giving you a wave function that's purely real here and purely imaginary here, or some combination of purely real and imaginary, some general complex number. And that complex number is not simply e to the I omega t. It's e to the I omega something that's a function of position as well as time. It's complicated. I can, of course, add some more wave functions here, and you get even more complicated sorts of evolution. Our expected value of x is now bouncing around fairly erratically. Our phase is bouncing around even more erratically. But what we're looking at here is just the sum of the first 1, 2, 3, 4, 5, 6 stationary states, each evolving with the same amplitude and different phases. Now I'm going to stop the simulation and clear it now. Another thing I can do with this simulation tool is put a Gaussian into the system. So I'm going to put a Gaussian in here. So this is sort of our initial conditions, and the simulation has automatically figured out, well, I want this much, I want a lot of the ground state, psi 1, a lot of psi 3, a lot of psi 5, a lot of psi 7, a little bit of psi 9, a little bit of psi 11, etc. And if I play this, I'll slow this down a little bit first. If I play this, you see the wave function gets wide, becomes 2, gets narrower again, and sloshes back where it started. If you watch these arrows down here, you can tell when it comes back together, the arrows are all pointing in the same direction, and when it's dispersed, the arrows are sort of pointing in opposite directions. Since our initial conditions were symmetric, there's no reason to expect the expected value to ever be non-zero,
ever move away from the center of this well. But as your, say, psi 1, psi 3, psi 5, psi 7, etc., oscillate at their own rates in time, the superposition results in a relatively complicated dynamics for the overall probability density. And of course, I can make some ridiculously wacky excited initial conditions that just sort of oscillate all over the place in a very complicated way. There are a lot of contributions to this wave function now, and no one contribution is particularly winning, but you can occasionally see little flashes of order in the wave function. I highly encourage you to play with these simulations just to get a feel for how time evolution in the Schrödinger equation works. There are a lot more than just the square well here. There's a finite well, harmonic oscillator, a pair of wells. There are lots of things to play with, so you can get a reasonably good feel with how the Schrödinger equation behaves in a variety of physical circumstances. So that's our simulation, and hopefully you have a better feel now for what solutions to the Schrödinger equation actually look like. To check your understanding, explain how these two facts are related. Time variability in quantum mechanics happens at frequencies given by differences of energies, whereas in classical physics, you can set the reference level for potential energy to whatever you want, sort of equivalent to saying, I'm measuring gravitational potential from ground level versus from the bottom of this well. The system we're considering in this lecture is the quantum harmonic oscillator. There are a few ways to solve the Schrödinger equation for the quantum harmonic oscillator, but what we're going to do in this lecture is a solution more or less by pure cleverness. The solution is called the solution by ladder operators, and we'll see what that means in a few minutes. Just to set the stage, the potential that we're working with here is the potential of a harmonic oscillator. The amount of energy, essentially, that you get if you displace a particle attached to a spring from equilibrium. If you remember spring potential energy, the potential as a function of x is 1/2 the spring constant times the displacement x squared. But it's traditional to write this instead in terms of the angular frequency. The angular frequency of the oscillations that result when a mass m is on a spring with spring constant k is the square root of the spring constant divided by the mass of the particle. And if you substitute this in here and mess around with the simplification a little bit, you end up with 1/2 m omega squared x squared. So this is the form of the potential that we'll be using. What this looks like, if I plot it, is a parabola. Not the world's prettiest parabola, but you get the idea. And we know a little bit about what solutions to the Schrödinger equation should look like under circumstances like this. Let me draw this a little lower so I have room. If I have some energy E in this combined energy wave function axis, making a diagram of what the wave function looks like, if I start my wave function here, you know in this region the energy is above the potential, so the Schrödinger equation solutions have to curve downwards. And what they end up looking like is, well, something like this, say. Now in the regions outside here, where the potential is above the energy, the Schrödinger equation solutions curve upwards. In the case of the harmonic oscillator solutions, they curve just down to kiss the axis. And you end up with a nice sort of hump-shaped wave function. If you have a higher energy, say up here, it's entirely possible to get solutions that look different. Suppose I started my wave function here, pointed at some angle. The energy now is higher relative to the potential, so the wave function is going to curve more, and it's possible to make it curve down to the point where when it reaches this point now where the potential is higher than the energy and it starts curving back upward, you again get a wave function that just smoothly joins in with the axis, giving you a sort of nice normalizable wave function. So these are the sorts of solutions that we expect to get. If you want to get these solutions just by, well, like drawing them, like I just did, you can conceptually understand what they look like, but
Quantitatively, you'll have to do a lot of fine-tuning to get these energy levels exactly right and to get the initial conditions here. I just started my wave function. How high up should I start my wave function? Or in this case, should I start it at the middle? Should I displace it? What should this angle here be? Fine-tuning like that is hard, and we'll see how to do that in the next lecture. But in this case, we're going to make a solution by cleverness instead of fine-tuning. To set that up, let's go back to the time-independent Schrodinger equation. This is the general time-independent Schrodinger equation, where now we're going to be substituting in the harmonic oscillator potential, 1/2 m omega squared x squared. That means the harmonic oscillator time-independent Schrodinger equation that we actually have to work with minus h bar squared over 2m times partial derivative of psi with respect to x squared plus 1/2 m omega squared x squared psi is equal to E psi. So this here is the Hamiltonian operator. The time-independent Schrodinger equation is also often just written as H psi equals E psi, and that's fine. Let's take a closer look at this Hamiltonian operator. Maybe we can do something with it. The cleverness comes in this step. Consider factoring the Hamiltonian. Well, I can simplify this a little bit by pulling out, for instance, a 2m here, and writing this as the momentum operator squared. This is essentially p squared over 2m, the kinetic energy part. This is the potential energy part. If I pull out 1 over 2m, what I get, 1 over 2m, p hat squared plus m omega x, quantity squared. This is suggestive. If we had numbers, and I had something like a squared plus b squared, I could factor that over the complex numbers as ia plus b times minus ia plus b. If you expand this out, you'll end up getting a plus a squared from multiplying these, a plus b from multiplying these, and similar to the cross terms in, say, a minus b times a plus b, the cross terms end up canceling out, and we would end up with what we started. Now, this is suggestive. You can't actually factor operators like this because they're not numbers, they're operators, and operators don't necessarily behave the same way numbers behave. We'll see what that means in a minute, but for now, let's just suggest looking at things like this. Plus or minus I times the momentum operator plus m omega x, where x now is the position operator. Now x, the position operator, just entails multiplying by x, so perhaps I should put a hat here, perhaps I shouldn't. Doesn't really matter. This is what we're considering now. I haven't justified this in any way beyond saying it kind of looks like maybe it would factor. Well, does it factor? These things are called ladder operators, and they're traditionally defined, just to make the notation a little bit simpler, a hat, and there's either a plus or a minus on this. Let me draw this a little bigger. A hat, plus or minus in the subscript, and these are defined to be 1 over the square root of 2 h bar m omega. The constant just makes things more nice overall, times minus or plus I p hat plus m omega x. This is now the position operator x hat. So this is the traditional definition. Let's see. If we have something that properly factors, what we should have is that a hat minus times a hat plus is our Hamiltonian. Is this true? This is an operator algebra problem, and operator algebra problems are tricky to do without test functions, but initially we can just write this out. We have two a's being multiplied together, so we're going to have a 1 over 2 h bar m omega out front, and then we're going to have I p hat plus m omega x times minus I p hat plus m omega x. Once again, hats on the x's if you prefer. So far, we've just written down our operators in order. Now, if I actually tried to expand these out, 1 over 2 h bar m omega. Now, this term, I times minus I, that's just plus 1. So we would get p hat squared. So far, so good. For this term, this is okay as well, plus m squared omega squared x hat squared. That's still okay. We're still on track. This was more or less what our Hamiltonian looked like. The cross terms get a little more interesting, though. We have a term like this, which gives us, let's see, we're going to end up with a minus I from this, minus I m omega, and we have x hat p hat. We're going to end up with something very similar from this term. We're going to have an I, we're going to have an m, we're going to have an omega, except in this case we're going to have p hat x hat, not x hat p hat, as we had here. So I'm going to factor the constants out and do that in the right color. That means we're going to have minus p hat x hat here. So this is what we get when we expand this out. This part here looks a lot like the Hamiltonian. So we're on the right track. It's actually like 1 over h bar omega times the Hamiltonian. This part, though, this is a little more difficult to work with. And it turns out that this piece right here, this sort of thing appears a lot in quantum mechanics, and we have a name for it and a notation for it. And the notation is x hat comma p hat in square brackets. This is called a commutator. And fundamentally, the fact that I can't just subtract these two things from each other and get 0 is one of the most fundamental parts of quantum mechanics, one of the most fundamental features of quantum mechanics. So, let's talk about commutators in a little more detail. The commutator in general is defined for two operators A and B to be what you just saw on the last page. First, I have A, B, and then I subtract the opposite order, B, A. So if I acted on this, or if I used this operator, this combined operator, to act on a wave function, I would first let A act and then let B act. And I would subtract that from what I get if I let B act and then A act. Just to make that a little more explicit, if I had A, B minus B, A acting on some wave function, I would say that's A, B, psi minus B, A, psi. You don't necessarily get the same answer for both of these things because the order in which operators act is important. So let's look then at our commutator. The commutator we had in the last slide was x and p. The commutator of x and p is x hat p hat minus p hat x hat. And let's allow this to act on some wave function psi. In order to make my notation correct, I ought to have the same sort of psi here. So if I allow this to act on psi, first we're going to have x hat p hat psi minus p hat x hat psi. And what this means is x hat is acting on p hat acting on psi, and this is p hat acting on x hat acting on psi. We have definitions for these things. X hat is just x multiplied by something, and p hat is minus I h bar times the derivative of something, in this case psi. Our second term here is minus I h bar times the derivative of, with respect to x, of x times psi. when I apply the derivative here, I have to use the product rule since I have a product of two terms. I'll have to hit x in one term and psi in the other term. So, on the leftmost term here is easy to deal with, though. It's just minus I h bar x d psi dx. Actually, let's factor out a minus I h bar from both terms, since they both have it. So x d psi dx is my first term here. Then I have minus, if I use the derivative on the x, derivative of x with respect to x is just 1. So all I'll be left with is the psi remaining untouched in the product rule. And if I let the derivative hit the psi, I'll leave the x untouched, and I'll have the derivative of psi with respect to x. This is good because here I have an x d psi dx minus x d psi dx. So I can let these terms subtract out and cancel. And what I'm left with, I have a minus I h bar times minus psi, which is just going to be I h bar psi. So I started with the commutator acting on the wave function, and I just got constant multiplied by the wave function. So I can drop my hypothetical wave function now and just write an equation involving the operators again. The commutator of x and p is I h bar. It's a weird-looking equation, but you can see, if you recall from the last slide, what we're going to end up with. When we evaluated a minus hat, a plus hat, we ended up with 1 over h bar omega times the Hamiltonian, plus some constants. And if you flip back a slide, the I h bars end up actually canceling out, and we just end up with plus a half for our constant. So while we did not succeed in fully factoring the Hamiltonian, we did get the Hamiltonian back, plus a constant. And if you reverse the order and repeat the algebra, a hat plus a hat minus, you end up with the same sort of thing. It looks very similar. You get 1 over h bar omega times the Hamiltonian minus a half instead. What this means is we can express the Hamiltonian in terms of these ladder operators and these constants. What we get for the Hamiltonian, h hat, is h bar omega times a minus a plus operators minus a half. Or alternatively, the Hamiltonian is equal to h bar omega a plus a minus plus a half. So these are the sorts of things that we got from our operator algebra after attempting to factor the Hamiltonian. That was pretty clever, but it didn't actually get us a solution. It just got us a different expression of the problem. The cleverness really comes in considering ladder operators and energy. The time-independent Schrodinger equation here is h hat psi equals e psi. So suppose we have some solution psi to the Schrodinger equation. We can then express the Hamiltonian in terms of these ladder operators, h bar omega times a plus a minus operators plus 1/2 acting on the wave function should be equal to e times the wave function. The clever part is this. What if I consider h hat times a plus psi? What happens to the wave function if I allow a plus to act on it before I allow the Hamiltonian to act on it? Now, assuming this is the case, maybe we can manipulate our expressions here involving the Hamiltonian and the ladder operators to get something with which we can apply our solution. Let's see what happens. Expressing the Hamiltonian now as ladder operators, h bar omega a hat plus a hat minus plus 1/2, now acting on a plus hat psi. Forgot my hat there, sorry. Looking at this, you can take a plus psi and distribute it in to the expression in parentheses here. H bar omega a plus hat a minus hat a plus hat psi plus a half psi. Put another way, I'm really just distributing the operator in. And that's actually a more convenient way to look at it. So I'm going to erase my psi's here, and I'm going to leave my psi outside the expression. Oops, and I forgot an a plus hat here. Sorry about that. Just distributing the a plus in here, you'll end up with plus minus plus, and just plus on the 1/2. Now, you notice I have an a plus here, and an a plus here. If you think about factoring this out to the left, that's actually allowed as well. I can rewrite this as h bar omega a plus hat in front of the expression a minus hat a plus hat plus 1/2, all acting on psi. That's okay. What's nice about this is if you look, we have here now an h bar omega and an a minus a plus. If I had the appropriate constant here, which would turn out to be minus a half, I would have the Hamiltonian back. And getting the Hamiltonian back means we might be able to apply our Schrodinger equation. So let's rewrite this as h bar omega a plus hat times a minus a plus minus a half plus 1. I haven't changed anything now, except this piece. This is my Hamiltonian. I had two expressions for the Hamiltonian that I got from calculating the product of ladder operators. One if I did a plus first and then a minus, one if I did a minus first and then a plus, and they were different by the sign that appeared here. So the fact that this is the Hamiltonian allows me to rewrite things a little bit. It turns out I can rewrite this whole expression as a plus hat acting on the Hamiltonian, and you have to distribute the h bar omega in, Hamiltonian operator plus h bar omega acting on psi. So I'm starting to lose my ladder operators, which is a good sign because I don't actually want expressions with lots of ladder operators in them. I'd like expressions with things that I know in them. And it turns out you know what happens when the Hamiltonian acts on psi. So if I distribute psi in here, I'll just have psi times h bar omega and the Hamiltonian acting on psi. But you know the Hamiltonian acting on psi is E times psi. So we're definitely making progress now. This is going to become a plus hat times E plus h bar omega psi. This now is all constant. So it doesn't matter if I put it in between the ladder operator and the wave function or not. So I can pull that out and make this E plus h bar omega times ladder operator a plus acting on the wave function psi. If I rewrite my entire equation then, I end up with h hat acting on ladder operator psi, a plus psi, is equal to E plus h bar omega ladder operator acting on psi, a plus acting on psi. This looks a lot like the Schrodinger equation for a wave function given by a plus psi. So, if psi is a solution to the time-independent Schrodinger equation, a plus psi is also a solution to the time-independent Schrodinger equation with this new energy. That's really the clever part. If psi is a solution, a plus psi is also a solution. That's really quite interesting. What that means is if I have one solution psi, I can apply the ladder operator, which I've just been writing as a plus hat here. But we know what the ladder operator a plus is. It's a combination of the momentum operator and multiplication by x with appropriate constants thrown in. We know about a plus psi. If we knew the wave function, we could actually do this. It would involve taking some derivatives and multiplying by some constants. We can do that. So this gives us some machinery for constructing solutions from other existing solutions. We haven't actually solved the system yet. There's a little bit of cleverness left. And this has to do with ladder operators and the ground state. what we showed on the last slide was that if psi was a solution, then A plus hat psi was a solution with energy E plus h bar omega. It turns out A minus hat psi, you can follow through the same algebra, is also a solution, but it has energy E minus h bar omega. So suppose we have some solution, psi, and I'll call it psi sub n now. If we apply the ladder operator, A plus psi, we'll end up with some wave function psi n plus 1. It's another solution to the Schrodinger equation. It has a slightly higher energy. The energy has been increased by the amount h bar omega here. I can repeat that process, and I'll get, say, something I would call psi n plus 2. And you can keep applying the ladder operator over and over and over, and you'll generate an infinite number of solutions with higher and higher and higher energies. We can also apply the ladder operator A minus hat, and you'll get something I'll call psi sub n minus 1 with slightly lower energy. The energy has been lowered by an amount h bar omega. You can apply the ladder operator A minus hat as many times as you want, of course, as well, and you'll get psi sub n minus 2, or psi sub n minus 3, or psi sub n minus 4, psi sub n minus 5. Every time you apply the lowering operator, the ladder operator A minus hat, you get another solution with lower and lower and lower energy. But we know if we have a wave function with very, very low energy, it's going to behave very strangely. If your potential, for instance, is your harmonic oscillator potential, it looks like this, and your energy, E, is below your potential V of x, then if I start my wave function, say, anywhere, really, let's start it here. The fact that the energy is below the potential for the entire domain of the potential means that over the entire domain of the wave function is going to be curving away from the axis. The wave function is going to be blowing up. That's a problem. I cannot have solutions with arbitrarily low energy. What that means, cannot have solutions with very low energy. What that means is that if I apply this lowering operator over and over and over again, sooner or later I have to get something that I can no longer apply the lowering operator to. Something will no longer give me a meaningful solution. And it turns out the best way of thinking about that is there is some wave function such that A minus acting on that wave function is equal to 0. If we have a state like this, this will be our lowest energy state, and I'll call it psi sub 0. This is a necessary condition for getting a normalizable wave function. If we did not have this condition, we'd be able to keep applying the lowering operator, and we would sooner or later get solutions that were not allowed. That's a problem. So let's figure out what this actually implies. We know what the lowering operator is. We know what 0 is. We ought to be able to solve this. This is going to be an ordinary differential equation just given by the definition of the ladder operator. 1 over 2m h bar omega in a square root times the momentum operator h bar d by dx plus m omega x acting on psi sub 0 is equal to 0. This we can solve. This is a relatively easy ordinary differential equation to solve, in fact, because it's actually separable. If you mess around with the constants, you can convert this into the differential equation d psi dx is equal to minus m omega over h bar x psi. And these are now psi zeros, sorry. This can be directly integrated. I can rewrite this as d psi over psi is equal to minus m omega over h bar x dx. And if I do this integral, integrating both sides of this equation, what you end up with, after you simplify, is that psi sub 0 is equal to e to the minus m omega over 2 h bar x squared. E to the minus x squared for our ground state, for our lowest energy psi sub 0, for our lowest energy solution. There's a normalization constant here, and I'll save you the trouble of calculating the normalization constant out. It's m omega over pi h bar to the 1/4 power. So this is our ground state. Now it's off to the races. By consideration of the Hamiltonian, and attempting to factor it, and defining ladder operators, and exploring the consequences of these ladder operators, in particular that we ended up with any single solution giving us an infinite number of solutions by repeatedly applying a plus and a minus, the necessity of a normalizable wave function, the necessity of having a lowest energy state, meant that we got an equation that was simple enough that we could solve it with just simple ordinary differential equations. Now, there's really no such thing as a simple ordinary differential equation, but this was a lot easier to solve than some ordinary differential equations. What that ended up giving us in the end was psi 0, our lowest energy state. We can then apply the raising operator, a plus, over and over and over again to construct an infinite number of states. To summarize, here's a slide with all of the definitions. The raising and lowering operators, the ladder operators, a plus and a minus, the expressions that you get from simplifying the Hamiltonian in terms of the ladder operators. I want to highlight these two expressions because I have not completely derived them. I have argued that the ladder operator a plus applied to some wave function psi sub n gives you psi sub n plus 1, but I haven't told you anything about the normalization. You could apply this operator over and over again and renormalize all of the wave functions you get as a result, but it turns out there's a pattern to them, and that pattern is that what you get by applying the ladder operator a plus to psi n is not psi n plus 1, but psi n plus 1 times this square root of n plus 1. Likewise for the lowering operator. There's a nice explanation in the textbook of how you can use still more cleverness to derive what these normalization multiplicative factors are. Our ground state we got from applying the lowering operator to some hypothetical wave function, which when we solve it, we ended up with this, our psi sub 0, our lowest energy wave function. Putting all of this together, you can come up with an expression for the nth wave function, psi sub n, in terms of psi sub 0. You have to apply a plus n times. This superscript n here means to apply a plus n times. For instance, a plus hat cubed would be a plus, a plus, a plus, all acting on, say, if there's a psi in here, all acting on the psi, just one after the other. And if you calculate the energies that we get, applying the Hamiltonian to our lowest energy wave function, and then knowing that the raising the operator a plus gives you a new solution with an energy that's increased by the amount h bar omega, you end up with the energies. So we actually know everything about the solutions now. We know the lowest energy solution, we have a procedure for calculating higher energy solutions, and we know the energies of all of these solutions. So that's wonderfully good. To give an example of how these things are actually used, let's calculate psi 1. We know psi 1, black a little easier to read, psi 1 is going to be equal to a plus acting on psi 0, and there's that normalization constant, the square root of n plus 1, except in this case n is 0, so this is just going to be 1. If I substitute in the definition of the operator a plus, that's 1 over that square root of 2 h bar m omega minus I p hat plus m omega x, where p hat now is minus I h bar d by dx. This is my raising operator. That's all acting on psi sub 0. And we know psi sub 0, given in normalized form, m omega
over pi h bar to the 1/4 power e to the minus m omega over 2 h bar x squared. We just have to evaluate this, taking derivatives of this exponential and multiplying it by x. So let's continue with that. Moving our normalization constant out front, m omega over pi h bar to the 1/4 power over this square root factor, 2 h bar m omega. Simplifying this expression out, we end up with minus h bar d by dx plus m omega x, all acting on e to the minus m omega over 2 h bar x squared. Now, this term with the m omega x, that's going to be easy. The derivative here is going to be relatively straightforward as well. And what we end up with is the constants we had out front, and taking the derivative of an exponential, we're just going to get the exponential back. So we're going to have an h bar e to the minus m omega over 2 h bar x squared times the inner derivative, the derivative of what's in the exponent itself, which is minus 2x, sorry, let me actually write this out, minus m omega over 2 h bar times 2x. That's okay. The minus sign here and the minus sign I had out front will end up canceling out. I can simplify, I can cancel out my 2's, I can cancel out an h bar. That's all I'm going to do with that term for now. The other term is easy. M omega x e to the minus m omega over 2 h bar x squared. So that's our result. We have an e to the m minus m omega, etc., over x squared in both of these terms. So I'm going to pull that out to the right. And if I pull my constants out to the left, I have an m omega and an m omega in both of these terms, so I can factor that out. And what you end up with at the end, after all is said and done, the only step I'm skipping now is to simplify the constants. What you end up with is m omega over pi h bar to the 1/4 power. There isn't much we can do about that. Square root of 2 m omega over h bar x e to the minus m omega over 2 h bar x squared. Both of these terms had x and x in them. So these terms just add up, and this is what we end up with at the end. This is your expression for psi 1. The algebra here gets a little bit complicated, but fundamentally what we're doing is calculus, taking derivatives, multiplying, manipulating functions, applying the chain rule, and turning the crank, more or less. The formula we started with here does give us machinery that we can use to calculate any wave function that we might want as a solution to the time-independent Schrodinger equation for the quantum harmonic oscillator. To check your understanding, here is an operator algebra problem. Given that x hat is the position operator and t hat is the kinetic energy operator, essentially p squared over 2m, calculate the commutator of x and t. That's just defined as this. The one tip I have for you here is to be sure to include a test function when you expand out these terms, and when you take second derivatives, do it as a sequence of 2 steps. Don't just try and take the second derivative twice in one step. You may have to apply the product rule. This is the story all about how the Schrodinger equation applies to the free particle. What do we mean by a free particle? Imagine an electron, for instance, floating in the vacuum of space. It never encounters anything. It never runs into anything. How that enters the Schrodinger equation is that there is effectively no potential anywhere. So the time-independent Schrodinger equation, we're back to one dimension now, so don't think about a particle floating around in the vacuum of 3-dimensional space. It's floating around in the vacuum of 1-dimensional space. The left-hand side of our time-independent Schrodinger equation is the Hamiltonian operator applied to the wave function. This is in some sense the total energy,
which breaks down into a kinetic energy component here with the momentum of the particle squared divided by twice the mass, and a potential energy part here, where V of x is the potential energy that the particle would have to be found at a particular location. In the context of the free particle, where there is no potential, what that means is that V of x is equal to 0 everywhere. That means we can just cross out this term entirely. We don't have to worry about it. What we're left with then for our time-independent Schrodinger equation is minus h bar squared over 2m times the second partial derivative of psi with respect to x equal to e psi. Now, we have some constants here, and we have a constant here, so let's lump them all together. And I'm going to shift the signs around a little bit as well, so that what we've got is the second derivative of psi with respect to x is equal to minus 2me over h bar squared times the wave function. So just lumped all our constants together and multiplied through by a minus sign. Now, you notice the second derivative here of the wave function, giving you the wave function back. The fact that we're taking a second derivative suggests that the constant here perhaps is squared. So what I'm actually going to write this as is the second derivative of psi with respect to x is equal to minus some constant k squared times the wave function, where k, our constant, is the square root of 2me over Planck's constant. So this is the differential equation, and we ought to be able to solve this. This is relatively simple compared to the structure of the differential equations we got from the harmonic oscillator. So how do we solve this? Well, what we have, second partial of psi with respect to x, is minus some constant squared times the wave function. Taking the second derivative gives you a constant squared. That immediately suggests we look for exponential solutions. And it turns out the general solution to this equation is some constant times e to the minus I k x plus b e to the plus I k x. If I take the second derivative of this exponential term, I'll get a minus I k squared, which you know is just minus k squared, applying the rules of complex numbers, which is what we get here. So when I take the second derivative of this term, I'll end up with minus k squared times this term. And I get the same sort of thing here. If I take plus I k squared from the second derivative, that again gives me a minus k squared. So we're okay. This is our general solution. When we include time in this, since you know this is a solution to the time-independent Schrodinger equation, it's going to have time dependence given by the time part, the time equation that we got when we did separation of variables. What you end up with is psi of x and time now is equal to a e to the minus I kx times e to the I energy t over h bar plus b times e to the I kx e to the I energy time over h bar. And I've left off my minus signs here in the energy dependence, just conventional to include minus signs there. We can rewrite this a little bit as a e to the I k. Now, what I'm doing here is substituting in the definition of k, which if you remember was the square root of 2me all over h bar, expressing energy in terms of this k. And when I do that, what I end up with is this term ends up looking like h bar k squared over 2m. Substituting that in here is what we get from manipulating our constants here. If I do that manipulation, the first term here, instead of having this product of two exponentials, I'm going to write it as a sum in the exponent, x minus h bar k over 2m t plus b times something that looks very similar, e to the minus I k x plus h bar k over 2m t. So these are our general solutions to the full Schrodinger equation. Our full wave function is a function of both position and time. And these solutions are traveling waves. You can think about this as a traveling wave in the context of looking at this as a complex number. If I look at e to the I kx, for instance, as a function of x, you know what that does in the complex plane. It just rotates around in the complex plane. If I look at this as e to the I kx, let me redo that a little. Ik times x minus h bar k over 2m t. And I treat this as a function of time. Again, we just get rotation in the complex plane. We get rotation in the other direction, but that's not really all that important. What is important is that you can visualize this in, if you want to think about it in 3 dimensions, with some real part here, and, why do I say real and then write imaginary? With, say, the real part here and the imaginary part here. What we've got is something that spirals around the 0 point. Now, if I look at this as a function of both position and time, at every time I have this spiral as a function of position, say. As time increases, what changes about this spiral is the whole thing shifts, either in the plus x direction or in the minus x direction. And you can determine how that propagates by looking at the argument here. If I look at x minus h bar k over 2m t, if I'm looking for a specific point on the spiral, say this point, and I want to know whether it moves this direction or this direction, I can look at this expression here. This specific point on the spiral, as the spiral moves, is going to be represented by a constant value of this argument. And if all I'm caring about is what direction the wave moves, I might as well set that constant equal to 0. What that means is I can write this as x equals h bar k over 2m t. And this immediately tells me that as time increases, x increases for this specific point on the spiral. So in this particular case, the wave is going to the plus x direction. For the other term here, the relative sign of x and t is different, so you end up with a wave propagating in the opposite direction. So these are our traveling wave solutions to the time-independent Schrodinger equation, or to the overall Schrodinger equation, excuse me. To check your understanding, go back and review the definitions of these traveling wave solutions, and think about how the energy enters. Do high-energy free particles move faster or slower? Is the wavelength, in a sense, the tightness of the spiral, shorter or longer? And is the time evolution, the rate at which the spiral rotates in time, faster or slower? What we did after we got our stationary state solutions to the Schrodinger equation for instance, the particle in a box or the harmonic oscillator, was examine the boundary conditions and determine whether or not we had quantization. This is where the free particle gets a little bit difficult to work with. The problem here is that v of x is equal to 0 everywhere. And I mean everywhere. There are essentially no boundaries. The fact that we have no boundaries means that we can have any value of that constant k, which means we can have any value of the energy, E. So we have no quantization here. That's a problem. It's not necessarily a problem directly, but it means that instead of what we were dealing with the particle in a box, for instance, where we had functions that were easy to represent, because there was a finite number of them, we could write a sum from n equals 1 to infinity of Cn times psi sub n. Same for the harmonic oscillator. We got a discrete set. We got a quantized solution. Now we have no quantization. So the framework that we built up for treating particles with quantized states isn't going to just directly apply. We'll have to do something a little different. The other thing that's different about the free particle is the normalization. The normalization condition we had for a wave function psi was that you multiply the complex conjugate of the wave function times the wave function itself, integrate from minus infinity to infinity, and I've left off my dx here. You should get 1. What happens when we do that here? Well, this normalization integral
if we're working with, just say, the term a times e to the, where did it go? E to the I k x minus h bar k over 2mt. If we're just working with this term, taking the complex conjugate is easy. The only complex part is this I here. And what we're going to end up with for our integral then, a being a constant, we can pull it out front, both the a star from psi star and the a from psi. We have the integral from minus infinity to infinity, dx, of the complex conjugate of psi, where we flip the sign here, and we've got e to the minus I k times something, which I'm too lazy to write. For psi, we get e to the plus I k times something that I'm too lazy to write, and it's the same something. These two terms, the arguments here, are the same, which means here I have a complex number times its complex conjugate. Since it's a complex number of modulus 1, I know this product is just going to be 1. So what I've got then is a star a times the integral from minus infinity to infinity dx, period. I'm done. And when you integrate dx from minus infinity to infinity, you get infinity. So this is a problem. These states are not normalizable. Anything I might do to try to normalize these by, say, setting this equal to 1 and solving for a, I would get a equals 1 over infinity, for instance. This is not useful. We cannot effectively normalize these states. This sounds like it has shot all of our framework in the foot, but it actually hasn't, because we can still use the framework of superposition. Superposition of these traveling wave solutions can give what are called wave packets. The bottom line, we can still write psi of x t equals 0 is a superposition of these traveling waves. We just have to be very careful about how we do the superposition. What these wave packets look like in the end, if I give myself an axis, is the wave function, the real part, might look something like this, where it's 0 for very large positive and very large negative values of x. The imaginary part might look something like this, where the full wave function only is non-zero over a specific interval, over a limited range, for instance, or a limited domain, to use the mathematical term. When psi is only non-zero over a limited range like this, we can normalize it. What's tricky is how we normalize psi by making a superposition of non-normalizable states. And that's the topic for next lecture. So to check your understanding, here's a recap of what these traveling wave stationary states look like and what their properties are. I promised in the last lecture that the solutions we got to the time-independent Schrödinger equation for the free particle, though they are not themselves normalizable and therefore cannot represent physically realizable states, could be used to construct physically realizable states. What that means is that we can take those solutions which themselves are not real and can add them up in a way that we can make something that is real. This is a little subtle. We're constructing something called a wave packet, and basically what that amounts to is adding up a bunch of infinities and getting something finite. Taking these traveling wave solutions to the time-independent Schrödinger equation for the free particle, which extend from minus infinity to infinity in the spatial domain, and from minus infinity to infinity in the temporal domain, and summing them up somehow to get something that is localized in the spatial domain. What that means is that we're making a wave packet. A wave packet, the features that we care about is that it's going to be 0 for, say, large negative values of x, 0 for large positive values of x, and only non-zero over some domain. What it might look like is, well, 0 some wave activity over a relatively limited region, and then going back to 0. We will see wave packets that look like this later on. I'll give a more concrete example and show some animations. But for now, let's think about the math. How would we go about constructing something like this? What we did in the case of the particle in a box, the infinite square well potential, was when we solved the Schrodinger equation, we got solutions. If our potential looks like this, going to infinity at regions outside of a box, our solutions looked like this. We got sinusoids with an integer number of half wavelengths fitting in our box. That was nice because it allowed us to construct our overall solution to the Schrodinger equation, psi of x and t, as an infinite sum of these stationary state wave functions. The integer number of half wavelengths fitting in the box, plus the essentially trivial time dependence that you get from the time equation when you do separation of variables with the general Schrodinger equation. This isn't going to work for the case of the free particle for a couple of reasons. First of all, instead of having a discrete sum over, states which have an index n, for instance, this is our psi sub n, where n goes from 1 to infinity, we now have wave functions psi that are continuous. We did not have quantized states. So our stationary states now are going to have to look like our traveling waves. They're going to have to look like e to the I, k, and then x minus, where did it go? h bar k over 2m t. This was our traveling wave solution from the last lecture. So instead of having our discrete set of states indexed by n, we have our continuous set where the parameter is k. K is a completely free parameter, not fixed to be an integer. The second reason our machinery for the particle in a box won't quite work is this coefficient c sub n. C sub n is also going to have to somehow become a function of k. K now being unrestricted, we can't just treat it as a set of discrete entities. We have to have some function, and that function is conventionally written as phi of k. And finally, this sum out front. Again, we can't do a sum if we have a continuous set of functions that we're working with that we want to add up. We have to do an integral. The integral now is going to be an integral over k. So our sum over n became an integral over k. Our coefficient, subscript n, became a function of k. And our discrete set of functions, psi sub n, became these traveling wave solutions with the parameter k in them. Our integral dk goes over all the possible values of k from minus infinity to infinity. And this is what the expression is overall going to look like. We have an integral, we have this continuous function, and we have our traveling wave states. The main problem with this expression is this guy. How do we know? How do we find phi of k? Phi of k is a general function. What we had done to find the analog of this was at c sub n in the case of the particle in a box. What we did for the case of the particle in a box was use Fourier's trick to collapse the sum. Instead of a sum now we have an integral, and it's not immediately clear from looking at this what it means for an integral to collapse. We'll see what that means in a second. But first of all, let's go back to what we did in the case of the particle in a box and spell out some of the details so that we can make an analogy. On the left-hand side here now we have the results for the particle in a box, whereas on the right-hand side we have the results as I have outlined what they might look like for the free particle. So the first thing we did for our particle in a box was to express the initial conditions as an infinite sum of the time t equals 0 form of our stationary state wave functions. The second thing we did in manipulating this expression to attempt to find a formula for the c sub n was to multiply on the left by a particular stationary state wave function. Not n, m. So we multiplied by root 2 over a sine m pi over a x psi of x 0. This is now looking at the left-hand side. So we multiplied by this, and we integrated from 0 to a. This integral is taken dx. It's important to note now that this is not the wave function psi, this is the complex conjugate of the wave function psi, and we'll come back to that in a moment. This integral, this is our left-hand side. If we do the same thing to the right-hand side, you end up with an integral dx that you can push inside the sum. You can pull out some constants, and all you're left with then, the only x dependence comes from the sine function here and the sine function you're multiplying in. So we ended up with a sum from n equals 1 to infinity of c sub n, our two root 2 over a factors from our two wave functions multiply together, just give us 2 over a. And what we're left with inside the integral is sine of m pi over a x sine of n pi over a x dx. So that was our expression, and the nice feature about this is that the sine functions had an orthogonality condition on them that allowed us to take this integral from 0 to a and express it as delta mn. The sine functions, if m is not equal to n, will integrate to 0 over this interval. And if m is equal to n, you just end up with 1. I should be including this factor out front in the expression for the orthogonality. What that means is that the sum collapses. The only remaining term is the term from Cm. So our right-hand side just becomes Cm. This gave us our formula for Cm being equal to the integral from 0 to a of essentially root 2 over a sine m pi over a x times our initial conditions, psi of x 0. This was a very brief overview of what we did back when we were talking about the particle in a box. Now, continuing this analogy into our free particle case, again, the first thing we're going to do is left multiply by the complex conjugate of the wave function. Now, the wave functions that we're working with now are stationary state solutions to the time-independent Schrödinger equation for the free particle. And what those look like, if I evaluate them at t equals 0, is e to the minus I kx. Now, I'm leaving off normalization constants because I don't know what they are at this point, but while I have a k in this integral, I shouldn't use k here. This is the same as saying I have an n in this sum, so I shouldn't use n in the function that I'm multiplying through. Things will just get confusing. So I'm going to call this k prime. So I've left multiplied by k prime. I have my wave function, my initial conditions, and again I'm integrating. Now I'm integrating from minus infinity to infinity, and I'm integrating dx. This is what I get for the left-hand side, just following by analogy from what we did for particle in a box. The right-hand side, in this case, now instead of having a sum over n, I have an integral over k. What I'm multiplying by from the left is again the e to the minus I k prime x, but this integral that I'm doing, that's an integral dx. So I can exchange the order of integration by k and integration by x. So I'm going to write this right-hand side now a little differently. We have the integral of minus infinity to infinity dk. Then we have phi of k, which is not a function of x, so I can pull it out of my integral over x, same as I could pull my c sub n out of this integral dx. Sorry, phi of k, not phi of x. What I'm left with then is the integral from minus infinity to infinity dx e to the minus I k prime x e to the I k x. Now, In order for this term to be meaningfully, or in order for this integral to collapse, like the sum collapsed here, we have to have some sort of orthogonality condition. The orthogonality condition for the sine functions from 0 to a was fairly straightforward. The orthogonality condition that applies here for this, where we are integrating over an infinite domain of something with a continuous parameter, k prime and k are continuous parameters that can take on any value, is not a simple Kronecker delta. It's a little different, but it looks very much the same. What you end up with here is called a Dirac delta function, and we will meet these Dirac delta functions in more detail later. If you're interested, there is a video lecture posted on the Dirac delta function and what its properties are. But for our purposes here, this expression evaluates to a Dirac delta function. A Dirac delta function is defined essentially as an infinitely narrow distribution. If you treat this as a distribution that only is non-zero at a particular value, the delta function by default is defined to be non-zero only for its argument equal to 0. This is effectively a distribution that only has non-zero values, only has support for k equal to k prime. If you treat this as a distribution, and you examine the expression integral from minus infinity to infinity dk of phi of k delta of k minus k prime, if this is a distribution, we're integrating a distribution times a function. This is the expected value of phi of k subject to the distribution given by the delta function. The delta function, acting like an infinitely narrow distribution, then simply pulls out the value that phi of k has when k equals k prime. Since this is infinitely narrow, phi of k is effectively a constant over the non-zero domain of the delta function. So it's just effectively averaging a constant over this domain. So this whole integral here is equal to phi of k prime. That's what it means for an integral to collapse. And like I said, if you're not entirely clear on how the delta function works, there's another video lecture on how to go about, or how to understand what the delta function can do for you. For now, notice that we can re-express this phi of k prime then in terms of our left-hand side. Phi of k prime is equal to the integral from minus infinity to infinity of e to the minus I k prime x psi of x0 integral dx. This completely determines phi of k. This is the real genius behind what's called Fourier analysis. What we were talking about in the case of the particle in a box was really Fourier series, and now we're talking about Fourier analysis. The way the math behind this is usually defined is in terms of something called the Fourier transform. The top two equations here are essentially definitions of the Fourier transform. We have some function of x. This is like our wave function as a function of time, and it's being expressed as an integral of some function of k multiplied by e to the ikx, integral dk. This function f, capital F of k, can be determined by essentially what we did in the previous slide. An integral from minus infinity to infinity dx of the function lowercase f of x times e to the minus ikx. The 1 over root 2 pi factors here are customary. Some authors use them, some authors define them slightly differently. It depends on the specific definition of the Fourier transform that you're using. But you can see the nice symmetry between these two equations. You have your 1 over root 2 pi in both equations. You have an integral from minus infinity to infinity in both equations. You have e to the ikx here, positive, and e to the minus ikx here, negative. That's the only difference. Then you have a function of k, integral dk, function of x, integral dx. Up to labeling x and k differently, the only difference between these two equations is the sign in the exponent. There's a lot of really nice math that comes from using Fourier transforms. Just to give a very brief example, if you're interested in processing astronomical images, for example, or any images really, treating the image as a function of this k parameter, which is a spatial frequency parameter, instead of treating the image as a function of x, as a function of which pixel you're looking at, you can do some very powerful analysis to identify features, for instance. High spatial frequency features versus low spatial frequency features. Smoothly varying backgrounds versus the boundaries between objects where the image varies rapidly will have different behavior when expressed in terms of this function of the spatial frequency. From the perspective of quantum mechanics, what we're interested in is how to express our wave function as a function of position and time. Well, using the Fourier transform definition here, we can find this phi of k by the same sort of equation. Phi of k is determined by an integral dx of our initial conditions times a complex exponential. Knowing what phi of k is, we can then determine what phi of x and t is. So again, our initial conditions determine our constant multiples essentially of our stationary states, these complex exponentials, which then gives us our overall wave function and how it behaves. To check your understanding, here is a simple example problem that requires you to apply the formulas on the previous page to go from a particular initial condition. In this case, it's a constant. Our initial wave function looks something like this. 0 everywhere except for a region between minus a and a. Your task, find the phi of k that goes with this particular function. That's about it, but before we finish talking about how to superpose these solutions, I want to look at the solutions themselves in a little more detail. Let's talk about the wave velocity in particular. This is our traveling wave solution, and we can figure out what its velocity is by looking at this argument. Which direction is this wave going? Well, if we look at a particular point on this spiral, on this e to the I kx, as time evolves, we can figure out where that point on the spiral is by setting this argument equals to a constant. Since I don't really care about what that constant is, I'm just going to set that equal to 0. So let's say kx minus h bar k squared over 2m t is equal to 0. If I continue along these lines, it's clear that in this case, if t increases, this part of this expression is getting more negative. This part of the expression has to get more positive. So that means x has to increase as well. So as t increases, x increases. That means this wave is moving to the right. The next question I can ask is how fast? How fast is it moving? And if you look at this again as setting this expression equal to 0, I can solve this and say x is equal to h bar k over 2m t. And in this case, the velocity is pretty clear. We have this constant, x equals some constant times time. Position equals something times time. This is our velocity. What this actually is, in terms of the energy of the particle, requires knowing what the definition of k is. So we have h bar over 2m, and the definition of our k was root 2me over h bar. So our h bars cancel out, and if we finish this expression, moving the 2m effectively under the square root, we get the square root of e over 2m t. So the velocity we get here is square root of e over 2m. Now, classically, what we get, we have a particle moving at some velocity and it has some energy. We know the relationship between those. It's the kinetic energy. 1/2 mv squared gives me E.
And if I solve this, I get v squared equals 2e over m, or v equals root 2e over m. These expressions are not equal to each other. That's a little strange. The velocity that we got from quantum mechanics, looking at how fast features on this wave function move, is not equal to the classical velocity. Will this hold true regardless? Do quantum mechanical particles have a different propagation behavior? That doesn't really make a lot of sense. This is actually not a problem, because what we're measuring here is the velocity of a feature on this wave. It's not actually the velocity of a wave packet. And since wave packets are the only real states that we can get, that we expect to observe in the physical universe, what we need to figure out is the wave packet velocity. In order to figure out the wave packet velocity, consider this wave packet. This is just a sum of two traveling waves with different k's, which I've now indexed k1 and k2. What I'd like you to do is think about expressing k1 and k2 as if they were near each other. So k1 is slightly less than k2, for example, or k1 is slightly greater than k2. Under these circumstances, it makes sense to rewrite these things. I'm going to define alpha as k1 plus k2 over 2, the average, times x, minus h bar k1 squared plus k2 squared over 2m t. Essentially, the sum of the argument of this and the argument of this. I'm also going to define a parameter delta, which is k1 minus k2 over 2x minus h bar k1 squared minus k2 squared over 2m t. Actually, sorry, I don't mean 2m's here. I mean 4m's here. Because I have a factor of 2 from the over 2m, and I have a 1/2 essentially from the way I'm combining the two terms. So given these definitions, you can express this as, not writing it there, as e to the I alpha plus delta plus e to the I alpha minus delta. So you see what I've done here? I've just re-expressed the arguments here as sums and differences. This is getting into the idea behind sum and difference and product identities in trig functions, except I'm doing this with complex exponentials instead. If I write this function as alpha plus delta, when I add alpha and delta, for instance, this first term gets me k1 plus k2 plus k1 minus k2. The k2's drop out, and I end up with 2k1 over 2, which is just k1 times x. Just k1x, essentially, what you want to get from this. If I express these exponentials in that way, you can factor out the alpha part. You get an e to the I alpha times an e to the I delta plus e to the minus I delta. If you're familiar with the complex exponential form of trig functions, you can probably see where I'm going with this. This is going to end up equal to e to the I alpha times cosine, actually, not just cosine, 2 cosine of delta. What this looks like in the context of our discussion of wave packets is if we have an axis there, we have this cosine factor, and it's the cosine of delta. If k1 and k2 are near each other, this will be a small number. This will also be a relatively small number. So delta evolves much more slowly with space and time than alpha. So if I was going to draw this wave function, I would have some slowly varying envelope like this, and superposed on top of that, multiplied by that slowly varying envelope, is e to the I alpha, which is the sum. So if k1 is close to k2, this is going to evolve much more rapidly. So my overall wave packet is going to look something like this, where you have zeros and areas with large amplitude, areas with small amplitude, areas with large amplitude, areas with small amplitude. As time evolves, this wave packet will propagate. And if what we're interested in is the velocity with which the overall packet propagates, you can consider a point on delta, not a point on alpha. If we're interested in the velocity with which these rapidly moving peaks, rapidly oscillating peaks evolve, then we would look at alpha. But since what we're interested in now is the wave packet, we want to look at delta. We want to look at the slowly varying envelope, how quickly the slowly varying envelope moves. Now, I haven't actually constructed a fully formed, physically realizable wave packet here because I have this cosine term, which again extends all the way from minus infinity to infinity. But hopefully, conceptually, you can think about this as a sort of rudimentary wave packet. The question then is, how fast does the rudimentary wave packet move? Well, if I look at delta, and if I assume that k1 is near k2, we can see how that works out. So what I'm looking at here is delta is equal to 0, say. The same sort of argument that I was using to determine how fast a feature on a single wave moved, setting this delta equal to a constant, not caring what the constant was, and setting it equal to 0. What I get then is k1 minus k2 over 2x being equal to h bar over 4m, and then k1 squared minus k2 squared, I'm going to look at this as the difference of two squares, which I can factor, k1 plus k2 times k1 minus k2. I can then cancel out this and this, and what I'm left with is just x over 2 equals to h over 4m k1 plus k2. If I assume that k1 is about equal to k2 then, I can pretend that this is some effective average k bar. If I write that out, sorry, this is 2 k bar, twice k bar, since I have k1 and k2, and they're added together. I can then look at this. I have a 1 over 2 here, a 1 over 4 here, and a 2 here. What I end up with at the end is just going to be x equals h bar over m times k bar. This is different than the expression we got before. K bar now is going to be our average k, h bar over m to copy that over, and our k was root 2m e bar now for k bar. Instead of k bar, I'll have e bar for my average. And then I have Planck's constant. I can cancel out Planck's constant in the denominator. I can again push my mass into the square root here, and what I'm left with then is root 2e over m times time. I forgot my times time here. All of these have a times time. So x equals something times time. This is our velocity. So here, for the wave packet velocity, we get root 2e over m. This is the classical velocity. So, problem solved. Whereas the features on each individual peak, for instance, in our wave function, traveled at one velocity, the overall wave packet traveled at another velocity. For the case of this particular wave packet, or wave packets in general, the wave packet itself travels at the velocity you would expect, except I have to be clear here now. Let me rewrite this. The velocity we get for a wave packet now, this is only approximate, so I should write it as approximately equals, and it's not twice the energy, it's twice the average energy. divided by mass in the square root. So this is not exactly the classical formula because now we don't necessarily have a single energy. If we had a single energy, we would be stuck with one of those solutions to the time-independent Schrodinger equation, which have definite energy. In the case of this free particle, those definite energy solutions extended throughout all space, and that was a problem. So we don't actually have a definite energy, so we'll have some spread in energies here. And if you have a large spread in energies, you'll effectively get a large spread in velocities. And what starts off as a wave packet will not stay a wave packet very long. It will propagate at different speeds. Different parts of the wave packet will propagate faster than others. But at any rate, what this actually looks like, to make some visuals here, and I couldn't hope to draw this accurately, but if we have some wave packet at time t equals 0, delta t, 2 delta t, and 3 delta t, it's going to propagate gradually. You can see the disturbance of this wave moving to the right. Now I've drawn solid, thick lines here behind it to designate the motion of the overall wave packet. The overall packet is moving at a speed more or less determined by the slope of these thick black lines. The thin gray lines identify features. For instance, this peak becomes this peak, becomes this peak, becomes this peak. This peak is traveling at a more slow rate than the overall wave packet and is essentially sort of falling off the back of the packet. It's decreasing in amplitude as it goes. The slopes of these lines are different, meaning the features on the waves are propagating at a different speed than the overall wave packet. This is actually a general feature of many waves. It's not something we hear about very often in everyday life because we never really think about whether there might be a difference or not. Plus, most of the common waves that we work with, like sound waves for instance, don't have this property. But if you look closely, for instance, if you drop a rock in a still pond, the small-scale ripples actually behave with this different velocity. In that case, actually, the features on the wave move faster than the overall wave packet. So in that case, you could view this as sort of time reversed, where the features start at the back of the wave packet and propagate forwards. But this is really the question of what's called group velocity and the question of phase velocity. The phase velocity refers to the features in the wave, whereas the group velocity refers to the velocity of the wave packet. This is not a wave mechanics course, but there's a lot of interesting math that can be done with this. The group velocity and the phase velocity being different is one of the more interesting features of, for instance, propagation of electromagnetic waves in plasmas in space. So if you're interested in radio astronomy, for instance, you need to know about this in very high levels of detail. To give you a better feel for what this looks like, here's an animation. What we're looking at now are the real and complex parts, shown in red and blue respectively, of a hypothetical wave packet that might represent a solution to the Schrodinger equation. It doesn't actually represent a solution to the Schrodinger equation, but this is the sort of behavior we're looking at. If I track a particular pulse, say this one, I'm moving my hand to the right as I do so. Here. But I'm not moving my hand to the right nearly as fast as the overall wave packet is propagating. So the overall wave packet is propagating at effectively twice the speed of the individual features on the wave. So this is what wave propagation might actually look like for the Schrodinger equation. You can construct wave packets like this. If you add the time dependence, then you can determine how the wave packet will propagate, how it will spread out, how the individual wave features will move, and you'll know effectively everything you need to. To check your understanding, here are a few true or false questions. Don't think that because they're true or false, they're easy. Think about these in detail. Our discussion of free particle stationary states, traveling waves that are infinite in extent and therefore not normalizable, led us to the concept of a wave packet, and the results of Fourier analysis that described how we could superpose these infinitely extended traveling wave solutions to make something that was localized and therefore normalizable. To give you a feel for what these look like, here is an example.
The initial conditions we're going to consider here are something we've seen before in class. The wave function psi evaluated at t equals 0 is given by this conditional expression. You have a normalization constant out front, and then you have values for a x between minus a and 0, between 0 and a, and everywhere else is 0. What this actually looks like is from, say, minus a to a, our wave function is a triangle. And outside of those regions, our wave function is 0. So this is now psi of x at t equals 0. If this is our wave function, hopefully you remember what the probability density as a function of position looked like at time t equals 0 as well. Between minus a and a, it sort of looked like two parabolas joined together. So how would we go about expressing this initial condition as a superposition of these infinite traveling waves? The result from Fourier analysis we're using now is the expression for the phi of k, the representation of the wave function in terms of k, where k is related to the energy and the spatial wavelengths of the traveling wave. What this actually looks like, we have to substitute in our definitions. We have a 1 over root 2 pi as before. From our initial conditions, we have the normalization of the initial conditions, 3 over 2a in a square root sign. And then our initial conditions are split up between the region minus a to 0 and 0 to a. So let's split up our integral from minus a to 0, and again from 0 to a. And we'll be adding these two integrals together. These are going to be integrals dx. I'm just splitting up this integral here. And what we actually have inside our integral, since we're looking at the t equals 0 version of the complex conjugate of the wave function here, e to the minus ikx is all we've got to work with for our traveling wave, and our initial conditions enter in from just the spatial dependent part. So we have a plus x over a from the space from minus a to 0, and then our e to the minus ikx from here. And for the space from 0 to a, we have a minus x over a, and then again e to the minus ikx dx. This is the integral that we wish to evaluate. These integrals are not as difficult as they might seem, because they're all of the form either e to the minus ikx or x e to the minus ikx. This can just be directly integrated. This is a candidate for integration by parts. So those would be the techniques that we would use, and if I had the patience to work through the page or so of algebra, what we actually end up with here are phi of k ends up being sine squared of x over x squared, related to this. It's not going to be exactly x, but this is the sort of functional dependence that we have. Sinc squared, if you're familiar with the definition of the sinc function. Here's what that looks like. This is phi of k as a function of k, or phi as a function of k. So our x-axis here is k, and our y-axis is phi of k. The sinc squared function here is symmetric between negative and positive values of k. What this means from the perspective of the traveling wave solutions is that phi of k, which tells us how much of each traveling wave solution we are going to add up to get our overall wave function, we effectively have equal contributions from left-going waves and from right-going waves. So overall, maybe we expect our wave function not to be moving. Knowing what phi of k is, we can go back through taking the inverse Fourier transform to find out what psi of x and t is, because we know the time dependence of these these traveling waves. The inverse Fourier transform then is going to give us psi of x and time, including the time dependence, in our traveling wave solutions now. So we have 1 over
2 pi times the integral from negative infinity to infinity of this phi of k that we got from the previous slide. This is going to look like sine of k, sine squared of k over k squared. So we have a function of k, we have another function of k, and the integral here, which I left off in the actual notation, is dk. So in principle, if we had something here that we could easily integrate, we could find psi as a function of t. Unfortunately, closed form integrable solutions to this equation are hard to come by. The example I've chosen here, you can probably guess that we're going to end up in trouble because the initial function that we started with, our initial conditions, was defined piecewise. And it's difficult to imagine a closed solution like this that gives us anything sensible that we can work with in the piecewise manner. So, at this point, we could in principle do this integral, but I'm lazy. So let's go and look at what the solutions actually look like. I went through and did these integrals numerically using Sage, and here's what you end up with. The initial conditions, the real part of the wave function is shown in red now, the imaginary part shown in blue. So when this animation loops, there's your initial conditions, and gradually things get smoother, decay away. You start to see things that look like traveling waves propagating to the right and propagating to the left. If I look at this instead in terms of the probability density, this is now a plot of the squared modulus of the wave function as a function of time. The initial conditions look like those joined parabolas there, but gradually things spread out, starts looking like a Gaussian, and the probability density gets broader and broader and broader and broader. So this is what wave packet solutions to the time-independent Schrodinger equation, or for the full Schrodinger equation, for the free particle actually look like. Your initial conditions are expressed as a superposition of stationary states, these traveling wave solutions, with the results from Fourier analysis. Taking the inverse Fourier transform of the representation in terms of stationary states allows us to easily add the time dependence, since we know the time dependence of each stationary state. The final solutions then are often tricky to work with, but in this case we could do something numerically relatively easily, though it did take a bit of CPU time to do these integrals, and you get a feel for what the wave function of evolution actually looks like. To check your understanding, here are a couple of questions. I've gotten sloppy with my notation. This is phi of k, the Greek letter, not phi of k. But first question, the wave function represented in terms of k is symmetric. Phi of minus k is phi of k. What does that imply about the direction of propagation of the particle, or of the wave function? And second of all, you have some spreading out in space. Does the representation of phi, or does the representation of the wave function in terms of k, which is related to the momentum, it's often called the momentum representation, also spread out as time increases?